Part 4 of Chapter 15, Pilot's Handbook. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Michael Early, Brisbane, Australia. Pilot's Handbook of Aeronautical Knowledge, Part 4 of Chapter 15 by the FAA. Flight Planning. Title 14 of the Code of Federal Regulations, 14 CFR, Part 91 states, in part, that before beginning a flight, the pilot in command, PIC, of an aircraft shall become familiar with all available information concerning that flight. For flights not in the vicinity of an airport, this must include information on available current weather reports and forecasts, fuel requirements, alternatives available if the planned flight cannot be completed, and any known traffic delays of which the pilot in command has been advised by ATC. Assembling necessary material. The pilot should collect the necessary material well before the flight. An appropriate current sectional chart and charts for areas adjoining the flight route should be among this material if the route of flight is near the border of a chart. Additional equipment should include a flight computer or electronic calculator, plotter, and any other item appropriate to the particular flight. For example, if a night flight is to be undertaken, carry a flashlight. If a flight is over desert country, carry a supply of water and other necessities. Weather check. It is wise to check the weather before continuing with other aspects of flight planning to see, first of all, if the flight is feasible, and, if it is, which route is best. Chapter 12, Aviation Weather Services, discusses obtaining a weather briefing. Use of Airport or Facility Directory, AFD. Study available information about each airport at which a landing is intended. This should include a study of the notices to airmen, NOTAMs, and the AFD, Figure 15-24. This includes location, elevation, runway and lighting facilities, available services, availability of Aeronautical Advisory Station Frequency, UNICOM, types of fuel available, used to decide on refueling stops, AFSS, FSS, located on the airport, control tower, and ground control frequencies, traffic information, remarks, and other pertinent information. The NOTAMs, issued every 28 days, should be checked for additional information on hazardous condition or changes that have been made since issuance of the AFD. The sectional chart bulletin subsection should be checked for major changes that have occurred since the last publication date of each sectional chart being used. Remember, the chart may be up to 6 months old. The effective date of the chart appears at the top of the front of the chart. The AFD generally has the latest information pertaining to such matters and should be used in preference to the information on the back of the chart if there are differences. Airplane Flight Manual or Pilot's Operating Handbook, AFM-POH. The Aircraft Flight Manual or Pilot's Operating Handbook, AFM-POH, should be checked to determine the proper loading of the aircraft, weight and balance data. The weight of the usable fuel and drainable oil aboard must be known. Also, check the weight of the passengers, the weight of all baggage to be carried, and the empty weight of the aircraft, to be sure that the total weight does not exceed the maximum allowable. The distribution of the load must be known to tell if the resulting center of gravity, CG, is within limits. Be sure to use the latest weight and balance information in the FAA-approved AFM or other permanent aircraft records, as appropriate, to obtain empty weight and empty weight CG information. Determine the takeoff and landing distances from the appropriate charts based on the calculated load, elevation of the airport, and temperature. Then compare these distances with the amount of runway available. Remember, The heavier the load and higher the elevation, temperature, or humidity, the longer the takeoff roll and landing roll, and the lower the rate of climb. Check the fuel consumption charts to determine the rate of fuel consumption at the estimated flight altitude and power settings. Calculate the rate of fuel consumption, and then compare it with the estimated time for the flight so that refueling points along the route can be included in the plan. Charting the course. Once the weather has been checked and some preliminary planning done, it is time to chart the course and determine the data needed to accomplish the flight. The following sections provide a logical sequence to follow in charting the course, filling out a flight log, and filing a flight plan. In the following example, a trip is planned based on the following data and the sectional chart excerpt in Figure 15-25. Route of flight: Chickasha Airport, direct to Guthrie Airport. True airspeed, TAS, 115 knots. Winds aloft, 360 degrees at 10 knots. Usable fuel, 38 gallons. Fuel rate, 8 gallons per hour. Deviation, +2 degrees. Steps in charting the course. The following is a suggested sequence for arriving at the pertinent information for the trip. As information is determined, it may be noted as illustrated in the example of a flight log in Figure 15-26. Errata. Figure 15-26, Pilot's Planning Sheet. Change the column label above 7 degrees east from WCA R plus L minus to mag var W plus E minus. Errata. Figure 15-26. Show an additional column labeled altitude on both the pilot's planning sheet and the visual flight log. Where calculations are required, the pilot may use a mathematical formula or a manual or electronic flight computer. If unfamiliar with the use of a manual or electronic computer, it would be advantageous to read the operation manual and work several practice problems at this point. First, draw a line from Chickasha Airport, point A, directly to Guthrie Airport, point F. The course line should begin at the center of the airport of departure and end at the center of the destination airport. If the route is direct, the course line consists of a single straight line. If the route is not direct, it consists of two or more straight line segments. For example, a VOR station, which is off the direct route, but which makes navigating easier, may be chosen. Radio navigation is discussed later in this chapter. Appropriate checkpoints should be selected along the route and noted in some way. These should be easy to locate points such as large towns, large lakes and rivers, or combinations of recognizable points such as towns with an airport, towns with a network of highways, and railroads entering and departing. Normally, choose only towns indicated by splashes of yellow on the chart. Do not choose towns represented by a small circle. These may turn out to be only a half dozen houses. In isolated areas, however, towns represented by a small circle can be prominent checkpoints. For this trip, 4 checkpoints have been selected. Checkpoint 1 consists of a tower located east of the course and can be further identified by the highway and railroad track, which almost parallels the course at this point. Checkpoint 2 is the obstruction just to the west of the course and can be further identified by Will Rogers World Airport, which is directly to the east. Checkpoint 3 is Wiley Post Airport, which the aircraft should fly directly over. Checkpoint 4 is a private, non-surfaced airport to the west of the course and can be further identified by the railroad track and highway to the east of the course. The course and areas on either side of the planned route should be checked to determine if there is any type of airspace with which the pilot should be concerned or which has special operational requirements. For this trip, it should be noted that the course passes through a segment of the Class C airspace surrounding Will Rogers World Airport, where the floor of the airspace is 2,500 feet mean sea level, MSL, and the ceiling is 5,300 feet, MSL, point B. Also, there is Class D airspace from the surface to 3,800 feet MSL surrounding Wiley Post Airport, point C, during the time the control tower is in operation. Study the terrain and obstructions along the route. This is necessary to determine the highest and lowest elevations, as well as the highest obstruction to be encountered, so that an appropriate altitude which conforms to 14 CFR Part 91 regulations can be selected. If the flight is to be flown at an altitude more than 3,000 feet above the terrain, conformance to the cruising altitude appropriate to the direction of flight is required. Check the route for particularly rugged terrain so it can be avoided. Areas where a takeoff or landing is made should be carefully checked for tall obstructions. Television transmitting towers may extend to altitudes over 1,500 feet above the surrounding terrain. It is essential that pilots be aware of their presence and location. For this trip, it should be noted that the tallest obstruction is part of a series of antennas with a height of 2,749 feet MSL, point D. The highest elevation should be located in the northeast quadrant and is 2,900 feet MSL, point E. Since the wind is no factor, and it is desirable and within the aircraft's capability to fly above the Class C and D airspace to be encountered, an altitude of 5,500 feet MSL is chosen. This altitude also gives adequate clearance of all obstructions, as well as conforms to the 14 CFR Part 91 requirement to fly at an altitude of odd 1,000 plus 500 feet when on a magnetic course between 0 and 179 degrees. Next, the pilot should measure the total distance of the course as well as the distance between checkpoints. The total distance is 53 nautical miles, and the distance between checkpoints is as noted on the flight log in Figure 15-26. After determining the distance, the true course should be measured. If using a plotter, follow the directions on the plotter. The true course is 031 degrees. Once the true heading is established, the pilot can determine the compass heading. This is done by the following formula given earlier in this chapter. The formula is TC plus or minus WCA equals TH plus or minus V equals MH plus or minus D equals CH. The WCA can be determined by using a manual or electronic flight computer. Using a wind of 360 degrees at 10 knots, it is determined that the WCA is 3 degrees left. This is subtracted from the TC, making the TH 28 degrees. Next, the pilot should locate the isogonic line closest to the route of the flight to determine variation. Figure 15-25 shows the variation to be 6.30 degrees east, rounded to 7 degrees east, which means it should be subtracted from the TH, giving an MH of 21 degrees. Next, add 2 degrees to the MH for the deviation correction. This gives the pilot the compass heading, which is 23 degrees. Now, the GS can be determined. This is done using a manual or electronic calculator. The GS is determined to be 106 knots. Based on this information, the total trip time, as well as time between checkpoints, and the fuel burned can be determined. These calculations can be done mathematically or by using a manual or electronic calculator. For this trip, the GS is 106 knots and the total time is 35 minutes. 30 minutes plus 5 minutes for climb, with a fuel burn of 4.7 gallons. Refer to the flight log in Figure 15-26 for the time between checkpoints. As the trip progresses, the pilot can note headings and time and make adjustments in headings, GS, and time. Filing a VFR flight plan. Filing a flight plan is not required by regulations. However, It is a good operating practice, since the information contained in the flight plan can be used in search and rescue in the event of an emergency. Flight plans can be filed in the air by radio, but it is best to file a flight plan by phone just before departing. After takeoff, contact the AFSS by radio and give them the takeoff time so the flight plan can be activated. When a VFR flight plan is filed, it is held by the AFSS until 1 hour after the proposed departure time, and then cancelled unless the actual departure time is received, a revised proposed departure time is received, or at the time of filing the AFSS is informed that the proposed departure time is met, but actual time cannot be given because of inadequate communication. The FSS specialist who accepts the flight plan does not inform the pilot of this procedure, however. Figure 15-27 shows the flight plan form a pilot files with the AFSS. When filing a flight plan by telephone or radio, give the information in the order of the numbered spaces. This enables the AFSS specialist to copy the information more efficiently. Most of the fields are either self-explanatory or non-applicable to the VFR flight plan, such as item 13. However, some fields may need explanation. Item 3 is the aircraft type and special equipment. An example would be C-150X, which means the aircraft has no transponder. A listing of special equipment codes is found in the Aeronautical Information Manual, AIM. Item 6 is the proposed departure time in UTC, indicated by the Z. Item 7 is the cruising altitude. Normally, VFR can be entered in this block, since the pilot chooses a cruising altitude to conform to FAA regulations. Item 8 is the route of flight. If the flight is to be direct, enter the word direct. If not, enter the actual route to be followed, such as via certain towns or navigation aids. Item 10 is the estimated time en route. In the sample flight plan, 5 minutes was added to the total time to allow for the climb. Item 12 is the fuel on board in hours and minutes. This is determined by dividing the total usable fuel aboard in gallons by the estimated rate of fuel consumption in gallons. Remember, there is every advantage in filing a flight plan, but do not forget to close the flight plan on arrival. Do this by telephone to avoid radio congestion. End of Part 4 of Chapter 15. Recording by Michael Early, Brisbane, Australia.
Part 5, Chapter 15 of the Pilot's Handbook. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Nathan Heck. The Pilot's Handbook of Aeronautical Knowledge by the FAA. Radio navigation. Advances in navigational radio receivers installed in aircraft, the development of aeronautical charts which show the exact location of ground transmitting stations and their frequencies, along with refined flight deck instrumentation, make it possible for pilots to navigate with precision to almost any point desired. Although precision in navigation is obtainable through the proper use of this equipment, beginning pilots should use this equipment to supplement navigation by visual reference to the ground, pilotage. This method provides the pilot with an effective safeguard against disorientation in the event of a radio malfunction. There are 4 radio navigation systems available for use in VFR navigation. These are VHF Omnidirectional Range, VOR, Non-Directional Radio Beacon, NDB, Long Range Navigation, LORAN-C, Global Positioning System, GPS, Very High Frequency, VHF, Omnidirectional Range, VOR. The VOR system is present in 3 slightly different navigation aids, NavAids, VOR, VOR-DME, and VORTAC. By itself it is known as a VOR, and it provides magnetic bearing information to and from the station. When DME is also installed with a VOR, the NavAid is referred to as a VOR-DME. When military tactical air navigation (TACAN) equipment is installed with a VOR, the navaid is known as a VORTAC. DME is always an integral part of the VORTAC. Regardless of the type of navaid utilized, VOR, VOR-DME, or VORTAC, the VOR indicator behaves the same. Unless otherwise noted in this section, VOR, VOR-DME, and VORTAC navaids are all referred to hereafter as VORs. The prefix omni means all, and an omnidirectional range is a VHF radio transmitting ground station that projects straight-line courses, radials, from the station in all directions. From a top view, it can be visualized as being similar to the spokes from the hub of a wheel. The distance VOR radials are projected depends upon the power output of the transmitter. The course or radials projected from the station are referenced to magnetic north. Therefore, a radial is defined as a line of magnetic bearing extending outward from the VOR station. Radials are identified by numbers beginning with 001, which is 1 degree east of magnetic north, and progress in sequence through all the degrees of a circle until reaching 360. To aid in orientation, a compass rose reference to magnetic north is superimposed on aeronautical charts at the station location. VOR ground stations transmit within a VHF frequency band of 108.0 to 117.95 MHz. Because the equipment is VHF, the signals transmitted are subject to line-of-sight restrictions. Therefore, its range varies in direct proportion to the altitude of receiving equipment. Generally, the reception range of the signals at an altitude of 1,000 feet above ground level, AGL, is about 40 to 45 miles. This distance increases with altitude. See Figure 1528. VORs and VORTACs are classed according to operational use. There are 3 classes: T, terminal; L, low altitude; H, high altitude. The normal useful range for the various classes is shown in the following table. VOR VORTAC navaids. Normal usable altitudes and radius distances. Class, terminal. Altitudes, 12,000 feet and below. Distance in miles, 25. Class, low altitude. Altitude, below 18,000 feet. Distance in miles, 40. Class, high altitude. Altitudes, below 14,500 feet. Distance in miles, 40. Class, high altitude. Altitudes, within the conterminous 48 states only, between 14,500 feet and 17,999 feet. Distance in miles, 100. Class, high altitude. Altitudes, 18,000 feet, flight level 450. Distance in miles, 130. Class, high altitude. Altitudes, 60,000 feet, flight level 450. Distance in miles, 100. The useful range of certain facilities may be less than 50 miles. For further information concerning these restrictions, refer to the Communication Navaid remarks in the AFD. The accuracy of course alignment of VOR radials is considered to be excellent. It is generally within plus or minus 1 degree. However, certain parts of the VOR receiver equipment deteriorate, and this affects its accuracy. It is particularly true at great distances from the VOR station. The best assurance of maintaining an accurate VOR receiver is periodic checks and calibrations. VOR accuracy checks are not a regulatory requirement for VFR flight. However, to assure accuracy of the equipment, these checks should be accomplished quite frequently and a complete calibration each year. The following means are provided for pilots to check VOR accuracy. FAA VOR Test Facility, VOT, Certified Airborne Checkpoints, Certified Ground Checkpoints located on airport surfaces. If an aircraft has 2 VOR receivers installed, a dual VOR receiver check can be made. To accomplish the dual receiver check, a pilot tunes both VOR receivers to the same VOR ground facility. The maximum permissible variation between the two indicated bearings is 4 degrees. A list of the airborne and ground checkpoints is published in the AFD. Basically, these checks consist of verifying that the VOR radials the aircraft equipment receives are aligned with the radials the station transmits. There are not specific tolerances in VOR checks required for VFR flight, but as a guide to assure acceptable accuracy, the required IFR tolerances can be used, plus or minus 4 degrees for ground checks and plus or minus 6 degrees for airborne checks. These checks can be performed by the pilot. The VOR transmitting station can be positively identified by its Morse code identification or by a recorded voice identification which states the name of the station followed by a VOR. Many FSS transmit voice messages on the same frequency that the VOR operates. Voice transmissions should not be relied upon to identify stations because many FSS remotely transmit over several omni ranges which have names different from that of the transmitting FSS. If the VOR is out of service for maintenance, the coded identification is removed and not transmitted. This serves to alert pilots that this station should not be used for navigation. VOR receivers are designed with an alarm flag to indicate when signal strength is inadequate to operate this navigational equipment. This happens if the aircraft is too far from the VOR, or the aircraft is too low and therefore is out of the line of sight of the transmitting signals. Using the VOR. In review, for VOR radio navigation, there are two components required: ground transmitter and aircraft receiving equipment. The ground transmitter is located at a specific position on the ground and transmits on an assigned frequency. The aircraft equipment includes a receiver with a tuning device and a VOR or omni-navigation instrument. The navigation instrument could be a course deviation indicator, CDI, horizontal situation indicator, HSI, or a radiomagnetic indicator, RMI. Each of these instruments indicates the course to the tuned VOR. Course deviation indicator, CDI. The CDI is found in most training aircraft. It consists of 1. An omni-bearing selector, OBS, sometimes referred to as the course selector, 2. A CDI needle, left-right needle, and 3. A to/from indicator. The course selector is an azimuth dial that can be rotated to select a desired radial or to determine the radial over which the aircraft is flying. In addition, the magnetic course to or from the station can be determined. When the course selector is rotated, it moves the CDI or needle to indicate the position of the radial relative to the aircraft. If the course selector is rotated until the deviation needle is centered, the radial, magnetic course from the station, or its reciprocal, magnetic course to the station, can be determined. The course deviation needle also moves to the right or left if the aircraft is flown or drifting away from the radial which is set in the course selector. By centering the needle, the course selector indicates either the course from the station or the course to the station. If the flag displays a to, the course shown on the course selector must be flown to the station. See Figure 1529. If from is displayed and the course shown is followed, the aircraft is flown away from the station. Horizontal situation indicator. The HSI is a direction indicator that uses the output from a flux valve to drive the compass card. The HSI, see Figure 1530, combines the magnetic compass with navigation signals and a glide slope. The HSI gives the pilot an indication of the location of the aircraft with relationship to the chosen course or radial. In Figure 1530, the aircraft's magnetic heading displayed on the compass card under the lubber line is 184 degrees. The course select pointer shown is set to 295 degrees. The tail of the pointer indicates the reciprocal, 115 degrees. The course deviation bar operates with the VOR localizer, VOR LOC, or GPS navigation receiver to indicate left or right deviations from the course selected with the course select pointer. Operating in the same manner, the angular movement of a conventional VOR LOC needle indicates deviation from course. The desired course is selected by rotating the course select pointer in relation to the compass card by means of course select knob. The HSI has a fixed aircraft symbol, and the course deviation bar displays the aircraft's position relative to the selected course. The to from indicator is a triangular pointer. When the indicator points to the head of the course select pointer, the arrow shows the course selected. If properly intercepted and flown, the course will take the aircraft to the chosen facility. When the indicator points to the tail of the course, the arrow shows that the course selected, if properly intercepted and flown, will take the aircraft directly away from the chosen facility. When the nav warning flag appears, it indicates no reliable signal is being received. The appearance of the HDG flag indicates the compass card is not functioning properly. The glide slope pointer indicates the relation of the aircraft to the glide slope. When the pointer is below the center position, the aircraft is above the glide slope, and an increased rate of descent is required. In some installations, the azimuth card is a remote indicating compass. However, in others, the heading must be checked occasionally against the magnetic compass and reset. Radio Magnetic Indicator, RMI. The RMI, figure 1531, is a navigational aid providing aircraft magnetic or directional gyro heading and very high frequency omnidirectional range, VOR, GPS, and automatic direction finder, ADF, bearing information. Remote indicating compasses were developed to compensate for errors in and limitations of older types of heading indicators. The remote compass transmitter is a separate unit usually mounted in a wingtip to eliminate the possibility of magnetic interference. The RMI consists of a compass card, a heading index, 2 bearing pointers, and pointer function switches. The 2 pointers are driven by any 2 combinations of a GPS, an ADF, and/or a VOR. The pilot has the ability to select the navigation aid to be indicated. The pointer indicates course to selected nav aid or waypoint. In figure 1531, the green pointer is indicating the station tuned on the ADF. The yellow pointer is indicating the course to a VOR of GPS waypoint. Note that there is no requirement for a pilot to select course with the RMI, but only the nav aid is to be indicated. Tracking with VOR. The following describes a step-by-step procedure to use when tracking to and from VOR station using a CDI. Figure 1532 and errata illustrates the procedure. First, tune the VOR receiver to the frequency of the selected VOR station. For example, 115.0 to receive Bravo VOR. Next, check the identifiers to verify that the desired VOR is being received. As soon as the VOR is properly tuned, the course deviation needle deflects either left or right. Then, rotate the azimuth dial to the course selector until the course deviation needle centers and the to from indicator indicates to. If the needle centers with a from indication, the azimuth should be rotated 180 degrees because in this case it is desired to fly to the station. Now, turn the aircraft to the heading indicated on the VOR azimuth dial or course selector 350 degrees in this example. If a heading of 350 is maintained with the wind from the right as shown, the aircraft drifts to the left of the intended track. As the aircraft drifts off course, the VOR course deviation needle gradually moves to the right of the center or indicates the direction of the desired radial or track. To return to the desired radial, the aircraft heading must be altered to the right. As the aircraft returns to the desired track, the deviation needle slowly returns to center. When centered, the aircraft is on the desired radial and a left turn must be made toward, but not to the original heading of 350, because a wind drift correction must be established. The amount of correction depends upon the strength of the wind. If the wind velocity is unknown, a trial and error method can be used to find the correct heading. Assume, for example, a 10-degree correction for a heading of 360 is maintained. While maintaining a heading of 360, assume that the course deviation begins to move to the left. This means that the wind correction of 10 degrees is too great and the aircraft is flying to the right of the course. A slight turn to the left should be made to permit the aircraft to return to the desired radial. When the deviation needle centers, a small wind drift correction of 5 degrees or a heading correction of 355 degrees should be flown. If this correction is adequate, the aircraft remains on the radial. If not, small variations in heading should be made to keep the needle centered, and consequently keep the aircraft on the radial. As the VOR station is passed, the course deviation needle fluctuates, then settles down, and the to indication changes to from. If the aircraft passes to one side of the station, the needle deflects in the direction of the station as the indicator changes to from. Generally, the same techniques apply when tracking outbound as those used for tracking inbound. If the intent is to fly over the station and track outbound on the reciprocal of the inbound radial, the course selector should not be changed. Corrections are made in the same manner to keep the needle centered. The only difference is that the omnidirectional range indicator indicates from. If tracking outbound on a course other than the reciprocal of the inbound radial, this new course or radial must be set in the course selector and a turn made to intercept this course. After this course is reached, tracking procedures are the same as previously discussed. Tips on using the VOR. Positively identify the station by its code or voice identification. Keep in mind that VOR signals are line of sight. A weak signal or no signal at all is received if the aircraft is too low or too far from the station. When navigating to a station, determine the inbound radial and use this radial. Fly a heading that will maintain the course. If the aircraft drifts, fly a heading to re-intercept the course, then apply a correction to compensate for wind drift. If minor needle fluctuations occur, avoid changing headings immediately. Wait momentarily to see if the needle recenters. If it does not, then correct. When flying to a station, always fly the selected course with a to indication. When flying from a station, always fly the selected course with a from indication. If this is not done, the action of the course deviation needle is reversed. To further explain this reverse action, if the aircraft is flown toward a station with a from indication, or away from a station with a to indication, the course deviation needle indicates in a direction opposite to that which it should indicate. For example, if the aircraft drifts to the right of the radial being flown, the needle moves to the right or points away from the radial. If the aircraft drifts to the left of the radial being flown, the needle moves left or in the direction opposite to the radial. When navigating using the VOR, it is important to fly headings that maintain or re-intercept the course. Just turning toward the needle will cause overshooting the radial and flying an S turn to the left and right of the course. End of Part 5 of Chapter 15. Recording by Nathan Heck.
Part 6 of Chapter 15 of Pilot's Handbook. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Pilot's Handbook of Aeronautical Knowledge by the FAA. Chapter 15, Part 6. Time and distance check from a station. To compute time and distance from a station, first turn the aircraft to place the bearing pointer on the nearest 90-degree index. Note time and maintain heading. When the bearing pointer has moved 10 degrees, note the elapsed time in seconds and apply the formulas in the following example to determine time and distance. See Figure 15-33. The time from station may also be calculated by using a short method based on the above formula, if a 10-degree bearing change is flown. If the elapsed time for the bearing change is noted in seconds, and a 10-degree bearing change is made, the time from the station in minutes is determined by counting off 1 decimal point. Thus, if 75 seconds are required to fly a 10-degree bearing change, the aircraft is 7.5 minutes from the station. When the bearing pointer is moving rapidly, or when several corrections are required to place the pointer on the wingtip position, the aircraft is at the station passage. The distance from the station is computed by multiplying TAS or GS in miles per minute by the previously determined time in minutes. For example, if the aircraft is 7.5 minutes from station, flying at a TAS of 120 knots or 2 nm per minute, the distance from station is 15 nm. 7.5 times 2 equals 15. The preceding are methods of computing approximate time and distance. The accuracy of time and distance checks is governed by existing wind, degree of bearing change, and accuracy of timing. The number of variables involved causes the result to be only an approximation. However, by flying an accurate heading and checking the time and bearing closely, the pilot can make a reasonable estimate of time and distance from the station. Course intercept. Course interceptions are performed in most phases of instrument navigation. The equipment used varies, but an intercept heading must be flown that results in an angle or rate of intercept sufficient to solve a particular problem. Rate of intercept. Rate of intercept, seen by the aviator as bearing pointer or HSI movement, is a result of the following factors: the angle at which the aircraft is flown toward a desired course, angle of intercept, true airspeed and wind, GS, distance from the station, angle of intercept. The angle of intercept is the angle between the heading of the aircraft, intercept heading, and desired course. Controlling this angle by selection/adjustment of the intercept heading is the easiest and most effective way to control course interceptions. Angle of intercept must be greater than the degrees from course, but should not exceed 90 degrees. Within this limit, adjust to achieve the most desirable rate of intercept. When selecting an intercept heading, the key factor is the relationship between distance from the station and degrees from the course. Each degree, or radial, is 1 nm wide at a distance of 60 nm from the station. Width increases or decreases in proportion to the 60 nm distance. For example, 1 degree is 2 nm wide at 120 nm, and 1/2 nm wide at 30 nm. For a given GS and angle of intercept, the resultant rate of intercept varies according to the distance from the station. When selecting an intercept heading to form an angle of intercept, consider the following factors: degrees from course, distance from the station, true airspeed and wind, GS. Distance measuring equipment, DME. Distance measuring equipment, DME, consists of an ultra-high frequency, UHF, navigational aid with VOR/DMEs and VOR-TACs. It measures, in nm, the slant range distance of an aircraft from a VOR/DME or VOR-TAC, both hereafter referred to as a VOR-TAC. Although DME equipment is very popular, not all aircraft are DME equipped. To utilize DME, the pilot should select, tune, and identify a VOR-TAC, as previously described. The DME receiver, utilizing what is called a paired frequency concept, automatically selects and tunes the UHF DME frequency associated with the VHF VOR TAC frequency selected by the pilot. This process is entirely transparent to the pilot. After a brief pause, the DME display shows the slant range distance to or from the VOR TAC. Slant range distance is the direct distance between the aircraft and the VOR TAC, and is therefore affected by aircraft altitude. Station passage directly over a VOR TAC from an altitude of 6,076 feet above ground level AGL would show approximately 1.0 nm on the DME. DME is a very useful adjunct to VOR navigation. A VOR radial alone merely gives line of position information. With DME, a pilot may precisely locate the aircraft on that line, radial. Most DME receivers also provide GS and time-to-station modes of operation. The GS is displayed in knots, NMPH. The time-to-station mode displays the minutes remaining to VOR TAC station passage, predicated upon the present GS. GS and time-to-station information is only accurate when tracking directly to or from a VOR TAC. DME receivers typically need a minute or two of stabilized flight directly to or from a VOR TAC before displaying accurate GS or time-to-station information. Some DME installations have a hold feature that permits a DME signal to be retained from one VOR TAC, while the course indicator displays course deviation information from an ILS or another VOR TAC. VOR/DME RNAV. Area Navigation RNAV permits electronic course guidance on any direct route between points established by the pilot. While RNAV is a generic term that applies to a variety of navigational aids, such as LORAN-C, GPS, and others, this section deals with VOR/DME based RNAV. VOR/DME RNAV is not a separate ground-based NAV-AID, but a method of navigation using VOR/DME and VOR TAC signals specially processed by the aircraft's RNAV computer. See Figure 15-34. Note: in this section, the term VOR TAC also includes VOR/DME NAV AIDs. In its simplest form, VOR/DME RNAV allows the pilot to electronically move VOR TACs around to more convenient locations. Once electronically located, they are referred to as waypoints. These waypoints are described as a combination of a selected radial and distance within the service volume of the VOR TAC to be used. These waypoints allow a straight course to be flown between almost any origin and destination, without regard to the orientation of VOR TACs or the existence of airways. While the capabilities and methods of operation of VOR/DME RNAV units differ, They are basic principles of operation that are common to all. Pilots are urged to study the manufacturer's operating guide and receive instruction prior to the use of VOR/DME, RNAV, or any unfamiliar navigational system. Operation information and limitations should also be sought from placards and the supplement section of the AFM/POH. VOR/DME based RNAV units operate in at least 3 modes: VOR, en route, and approach. A fourth mode, VOR parallel, may also be found on some models. The units need both VOR and DME signals to operate in any RNAV mode. If the NAV AID selected is a VOR without DME, RNAV mode will not function. In the VOR or non-RNAV mode, the unit simply functions as a VOR receiver with DME capability. See Figure 15-35. The unit's display on the VOR indicator is conventional in all respects. For operation on established airways or any other ordinary VOR navigation, the VOR mode is used. To utilize the unit's RNAV capability, the pilot selects and establishes a waypoint or a series of waypoints to define a course. To operate in any RNAV mode, the unit needs both radial and distance signals. Therefore, a VOR TAC or VOR/DME needs to be selected as a NAV AID. To establish a waypoint, a point somewhere within the service range of a VOR TAC is defined on the basis of radial and distance. Once the waypoint is entered into the unit and the RNAV en route mode is selected, the CDI displays course guidance to the waypoint, not the original VOR TAC. DME also displays distance to the waypoint. Many units have the capability to store several waypoints, allowing them to be programmed prior to flight, if desired, and called up in flight. RNAV waypoints are entered into the unit in magnetic bearings, radials of degrees and tenths. For example, 275.5 degrees, and distances in nm and tenths. For example, 25.2 nm. When plotting RNAV waypoints on an aeronautical chart, pilots find it difficult to measure to that level of accuracy, and in practical application, it is rarely necessary. A number of flight planning publications publish airport coordinates and waypoints with this precision, and the unit accepts those figures. There is a subtle but important difference in CDI operation and display in the RNAV modes. In the RNAV modes, course deviation is displayed in terms of linear deviation. In the RNAV en route mode, maximum deflection of the CDI typically represents 5 nm on either side of the selected course, without regard to distance from the waypoint. In the RNAV approach mode, maximum deflection of the CDI typically represents 1 1/4 nm on either side of the selected course. There is no increase in CDI sensitivity as the aircraft approaches a waypoint in RNAV mode. The RNAV approach mode is used for instrument approaches. Its narrow scale width, 1/4 of the en route mode, permits very precise tracking to or from the selected waypoint. In visual flight rules, VFR, cross-country navigation, tracking a course in the approach mode is not desirable because it requires a great deal of attention and soon becomes tedious. A fourth, lesser used mode on some units is the VOR parallel mode. This permits the CDI to display linear, not angular, deviation as the aircraft tracks to and from VOR TACs. It derives its name from permitting the pilot to offset or parallel a selected course or airway at a fixed distance of the pilot's choosing, if desired. The VOR parallel mode has the same effect as placing a waypoint directly over an existing VOR TAC. Some pilots select the VOR parallel mode when utilizing the navigation NAV tracking function of their autopilot for smoother course following near the VOR TAC. Confusion is possible when navigating an aircraft with VOR/DME based RNAV, and it is essential that the pilot become familiar with the equipment installed. It is not unknown for pilots to operate inadvertently in one of the RNAV modes when the operation was not intended by overlooking switch positions or annunciators. The reverse has also occurred with the pilot neglecting to place the unit into one of the RNAV modes by overlooking switch positions or annunciators. As always, the prudent pilot is not only familiar with the equipment used, but never places complete reliance in just one method of navigation when others are available for cross-check. Automatic Direction Finder, ADF. Many general aviation type aircraft are equipped with ADF radio receiving equipment. To navigate using the ADF, the pilot tunes the receiving equipment to a ground station known as a non-directional radio beacon, NDB. The NDB stations normally operate in a low or medium frequency band of 200 to 415 kHz. The frequencies are readily available on aeronautical charts or in the A/FD. All radio beacons except compass locators transmit a continuous 3-letter identification in code, except during voice transmissions. A compass locator, which is associated with an instrument landing system, transmits a 2-letter identification. Standard broadcast stations can also be used in conjunction with ADF. Positive identification of all radio stations is extremely important, and this is particularly true when using standard broadcast stations for navigation. NDBs have one advantage over the VOR. This advantage is that low or medium frequencies are not affected by line of sight. The signals follow the curvatures of the Earth. Therefore, if the aircraft is within the range of the station, the signals can be received regardless of altitude. The following table gives the class of NDB stations, their power, and usable range. Non-directional radio beacon, NDB. Usable radius distances for all altitudes. Class power in watts, distance in miles. Compass locator. Under 25, 15. MH. Under 50, 25. H. 50 to 1999, 50. HH. 2000 or more, 75. Service range of individual facilities may be less than 50 miles. One of the disadvantages that should be considered when using low-frequency, LF for navigation, is that low-frequency signals are very susceptible to electrical disturbances, such as lightning. These disturbances create excessive static, needle deviations, and signal fades. There may be interference from distant stations. Pilots should know the conditions under which these disturbances can occur, so that they can be more alert to possible interference when using the ADF. Basically, the ADF aircraft equipment consists of a tuner, which is used to set the desired station frequency, and the navigational display. The navigational display consists of a dial upon which the azimuth is printed, and a needle which rotates around the dial and points to the station to which the receiver is tuned. Some of the ADF dials can be rotated to align the azimuth with the aircraft heading. Others are fixed with the 0 degrees representing the nose of the aircraft, and 180 degrees representing the tail. Only the fixed azimuth dial is discussed in this handbook. See Figure 15-36. Figure 15-37 illustrates terms that are used with the ADF and should be understood by the pilot. To determine the magnetic bearing from the station, 180 degrees is added to or subtracted from the magnetic bearing to the station. This is the reciprocal bearing and is used when plotting position fixes. Keep in mind that the needle of fixed azimuth points to the station in relation to the nose of the aircraft. If the needle is deflected 30 degrees to the left for a relative bearing of 330 degrees, this means that the station is located 30 degrees left. If the aircraft is turned left 30 degrees, the needle moves to the right 30 degrees and indicates a relative bearing of 0 degrees, or the aircraft is pointing toward the station. If the pilot continues flight toward the station, keeping the needle on 0 degrees, the procedure is called homing to the station. If a crosswind exists, the ADF needle continues to drift away from 0. To keep the needle on 0, the aircraft must be turned slightly, resulting in a curved flight path to the station. Homing to the station is a common procedure, but results in drifting downwind, thus lengthening the distance to the station. Tracking to the station requires correcting for wind drift and results in maintaining flight along a straight path or bearing to the station. When the wind drift correction is established, the ADF needle indicates the amount of correction to the right or left. For instance, if the magnetic bearing to the station is 340 degrees, a correction for a left crosswind would result in a magnetic heading of 330 degrees, and the ADF needle would indicate 10 degrees to the right, or a relative bearing of 010 degrees. See Figure 15-38. When tracking away from the station, wind corrections are made similar to tracking to the station, but the ADF needle points toward the tail of the aircraft or the 180-degree position on the azimuth dial. Attempting to keep the ADF needle on the 180-degree position during winds results in the aircraft flying a curved flight, leading further and further from the desired track. To correct for wind when tracking outbound, correction should be made in the direction opposite of that in which the needle is pointing. Although the ADF is not as popular as the VOR for radio navigation, with proper precautions and intelligent use, the ADF can be a valuable aid to navigation. End of Part 6 of Chapter 15. Part 7 of Chapter 15 of Pilot's Handbook. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information, or to volunteer, please visit LibriVox.org. Pilot's Handbook of Aeronautical Knowledge by the FAA. Chapter 15, Part 7. Global Positioning System. The GPS is a satellite-based radio navigation system. Its RNAV guidance is worldwide in scope. There are no symbols for GPS on aeronautical charts, as it is a space-based system with global coverage. Development of the system is underway so that GPS is capable of providing the primary means of electronic navigation. Portable and yoke-mounted units are proving to be very popular in addition to those permanently installed in the aircraft. Extensive navigation databases are common features in aircraft GPS receivers. The GPS is a satellite radio navigation and time dissemination system developed and operated by the U.S. Department of Defense, DoD. Civilian interface and GPS system status is available from the U.S. Coast Guard. It is not necessary to understand the technical aspects of GPS operation to use it in VFR/Instrument Flight Rules, IFR, navigation. It does differ significantly from conventional ground-based electronic navigation, and awareness of those differences is important. Awareness of equipment approvals and limitations is critical to the safety of flight. The GPS navigation system broadcasts a signal that is used by receivers to determine precise position anywhere in the world. The receiver tracks multiple satellites and determines a pseudo-range measurement to determine the user location. A minimum of 4 satellites is necessary to establish an accurate 3-dimensional position. The Department of Defense, DoD, is responsible for operating the GPS satellite constellation and monitors the GPS satellites to ensure proper operation. The status of a GPS satellite is broadcast as part of the data message transmitted by the satellite. GPS status information is also available by means of the U.S. Coast Guard Navigation Information Service at 703-313-5907 or online at http://www.navcen.uscg.gov/. Additionally, satellite status is available through the Notice to Airmen (NOTAM) system. The GPS receiver verifies the integrity, usability of the signals received from the GPS constellation through Receiver Autonomous Integrity Monitoring, RAIM, to determine if a satellite is providing corrupted information. At least one satellite, in addition to those required for navigation, must be in view for the receiver to perform the RAIM function. Thus, RAIM needs a minimum of 5 satellites in view, or 4 satellites and a barometric altimeter, baro aiding, to detect an integrity anomaly. For receivers capable of doing so, RAIM needs 6 satellites in view, or 5 satellites with baro aiding, to isolate the corrupt satellite signal and remove it from the navigation solution. Baro aiding is a method of augmenting the GPS integrity solution by using a non-satellite input source. GPS-derived altitude should not be relied upon to determine aircraft altitude, since the vertical error can be quite large and no integrity is provided. To ensure that baro aiding is available, the current altimeter setting must be entered into the receiver as described in the operating manual. RAIM messages vary somewhat between receivers. However, generally there are 2 types. One type indicates that there are not enough satellites available to provide RAIM integrity monitoring, and another type indicates that the RAIM integrity monitor has detected a potential error that exceeds the limit for the current phase of flight. Without RAIM capability, the pilot has no assurance of the accuracy of the GPS position. Selective availability. Selective availability, SA, is a method by which the accuracy of GPS is intentionally degraded. This feature is designed to deny hostile use of precise GPS positioning data. SA was discontinued on May 1, 2000, but many GPS receivers are designed to assume that SA is still active. The GPS constellation of 24 satellites is designed so that a minimum of 5 satellites are always observable by a user anywhere on Earth. The receiver uses data from a minimum of 4 satellites above the mask angle, the lowest angle above the horizon at which a receiver can use a satellite. VFR use of GPS. GPS navigation has become a great asset to VFR pilots, providing increased navigation capability and enhanced situational awareness, while reducing operating costs due to greater ease in flying direct routes. While GPS has many benefits to the VFR pilot, care must be exercised to ensure that system capabilities are not exceeded. Types of receivers used for GPS navigation under VFR are varied, from a full IFR installation being used to support a VFR flight, to a VFR-only installation, in either a VFR or IFR capable aircraft, to a handheld receiver. The limitations of each type of receiver installation, or use, must be understood by the pilot to avoid misusing navigational information. In all cases, VFR pilots should never rely solely on one system of navigation. GPS navigation must be integrated with other forms of electronic navigation, as well as pilotage and dead reckoning. Only through the integration of these techniques can the VFR pilot ensure accuracy in navigation. Some critical concerns in VFR use of GPS include RAIM capability, database currency, and antenna location. RAIM capability. Many VFR GPS receivers and all handheld units have no RAIM alerting capability. Loss of the required number of satellites in view, or the detection of a position error, cannot be displayed to the pilot by such receivers. In receivers with no RAIM capability, no alert would be provided to the pilot that the navigation solution had deteriorated, and an undetected navigation error could occur. A systematic cross-check with other navigation techniques would identify this failure and prevent a serious deviation. In many receivers, an updatable database is used for navigation fixes, airports, and instrument procedures. These databases must be maintained to the current update for IFR operation, but no such requirement exists for VFR use. However, in many cases, the database drives a moving map display, which indicates special use airspace, and the various classes of airspace, in addition to other operational information. Without a current database, the moving map display may be outdated and offer erroneous information to VFR pilots wishing to fly around critical airspace areas, such as a restricted area or a Class B airspace segment. Numerous pilots have ventured into airspace they were trying to avoid by using an outdated database. If there is not a current database in the receiver, disregard the moving map display when making critical navigation decisions. In addition, waypoints are added, removed, relocated, or renamed as required to meet operational needs. When using GPS to navigate relative to a named fix, a current database must be used to properly locate a named waypoint. Without the update, it is the pilot's responsibility to verify the waypoint location referencing to an official current source, such as the A/FD, sectional chart, or en route chart. In many VFR installations of GPS receivers, antenna location is more a matter of convenience than performance. In IFR installations, care is exercised to ensure that an adequate clear view is provided for the antenna to see satellites. If an alternate location is used, some portion of the aircraft may block the view of the antenna, causing a greater opportunity to lose navigation signal. This is especially true in the case of handhelds. The use of handheld receivers for VFR operations is a growing trend, especially among rental pilots. Typically, suction cups are used to place the GPS antennas on the inside of aircraft windows. While this method has great utility, the antenna location is limited by aircraft structure for optimal reception of available satellites. Consequently, signal losses may occur in certain situations of aircraft satellite geometry, causing a loss of navigation signal. These losses, coupled with a lack of RAIM capability, could present erroneous position and navigation information with no warning to the pilot. While the use of a handheld GPS for VFR operations is not limited by regulation, modification of the aircraft, such as installing a panel or yoke-mounted holder, is governed by 14 CFR Part 43. Pilots should consult with a mechanic to ensure compliance with the regulation and a safe installation. Tips for using GPS for VFR operations. Always check to see if the unit has RAIM capability. If no RAIM capability exists, be suspicious of a GPS displayed position when any disagreement exists with the position derived from other radio navigation systems, pilotage, or dead reckoning. Check the currency of the database, if any. If expired, update the database using the current revision. If an update of an expired database is not possible, disregard any moving map display of airspace for critical navigation decisions. Be aware that named waypoints may no longer exist or may have been relocated since the database expired. At a minimum, the waypoints planned to be used should be checked against a current official source, such as the A/FD or a sectional aeronautical chart. While a handheld GPS receiver can provide excellent navigation capability to VFR pilots, be prepared for intermittent loss of navigation signal, possibly with no RAIM warning to the pilot. If mounting the receiver in the aircraft, be sure to comply with 14 CFR Part 43. Plan flights carefully before taking off. If navigating to user-defined waypoints, enter them before flight, not on the fly. Verify the planned flight against the current source, such as the current sectional chart. There have been cases in which one pilot used waypoints created by another pilot that were not where the pilot flying was expecting. This generally resulted in a navigation error. Minimize head-down time in the aircraft and keep a sharp lookout for traffic, terrain, and obstacles. Just a few minutes of preparation and planning on the ground makes a great difference in the air. Another way to minimize head-down time is to become very familiar with the receiver's operation. Most receivers are not intuitive. The pilot must take the time to learn the various keystrokes, knob functions, and displays that are used in the operation of the receiver. Some manufacturers provide computer-based tutorials or simulations of the receivers. Take the time to learn about the particular unit before using it in flight. In summary, be careful not to rely on GPS to solve all VFR navigational problems. Unless an IFR receiver is installed in accordance with IFR requirements, no standard of accuracy or integrity has been assured. While the practicality of GPS is compelling, the fact remains that only the pilot can navigate the aircraft, and GPS is one of the pilot's tools to do the job. VFR waypoints. VFR waypoints provide VFR pilots with a supplementary tool to assist with position awareness while navigating visually in aircraft equipped with area navigation receivers. VFR waypoints should be used as a tool to supplement current navigation procedures. The uses of VFR waypoints include providing navigational aids for pilots unfamiliar with an area, waypoint definition of existing reporting points, enhanced navigation in and around Class B and Class C airspace, and enhanced navigation around special use airspace. VFR pilots should rely on appropriate and current aeronautical charts published specifically for visual navigation. If operating in a terminal area, pilots should take advantage of the terminal area chart available for the area, if published. The use of VFR waypoints does not relieve the pilot of any responsibility to comply with the operational requirements of 14 CFR Part 91. VFR waypoint names for computer entry and flight plans consists of 5 letters beginning with the letters VP and are retrievable from navigation databases. The VFR waypoint names are not intended to be pronounceable, and they are not for use in ATC communications. On VFR charts, a standalone VFR waypoint is portrayed using the same 4-point star symbol used for IFR waypoints. VFR waypoint co-located with a visual checkpoint on the chart is identified by a small magenta flag symbol. A VFR waypoint co-located with a visual checkpoint is pronounceable based on the name of the visual checkpoint and may be used for ACT communications. Each VFR waypoint name appears in parentheses adjacent to the geographic location on the chart. Latitude/longitude data for all established VFR waypoints may be found in the appropriate regional A/FD. When filing VFR flight plans, use the 5-letter identifier as a waypoint in the route of flight section if there is an intended course change at that point, or if used to describe the planned route of flight. This VFR filing would be similar to VOR use in the route of flight. Pilots must use the VFR waypoints only when operating under VFR conditions. Any VFR waypoints intended for use during a flight should be loaded into the receiver while on the ground and prior to departure. Once airborne, pilots should avoid programming routes or VFR waypoint chains into their receivers. Pilots should be especially vigilant for other traffic while operating their VFR waypoints. The same effort to see and avoid other aircraft near VFR waypoints is necessary, as is the case when operating near VORs and NDBs. In fact, the increased accuracy of navigation through the use of GPS demands even greater vigilance, as off-course deviations among different pilots and receivers is less. When operating near a VFR waypoint, use whatever ATC services are available, even if outside a class of airspace where communications are required. Regardless of the class of airspace, monitor the available ATC frequency closely for information on other aircraft operating in the vicinity. It is also a good idea to turn on landing lights when operating near a VFR waypoint to make the aircraft more conspicuous to other pilots, especially when visibility is reduced. Lost procedures. Getting lost in an aircraft is a potentially dangerous situation, especially when low on fuel. If a pilot becomes lost, there are some good common sense procedures to follow. If a town or city cannot be seen, the first thing to do is climb, being mindful of traffic and weather conditions. An increase in altitude increases radio and navigation reception range, and also increases radar coverage. If flying near a town or city, it might be possible to read the name of the town on a water tower. If the aircraft has a navigational radio, such as a VOR or ADF receiver, it can be possible to determine position by plotting an azimuth from 2 or more navigational facilities. If GPS is installed, or a pilot has a portable aviation GPS on board, it can be used to determine the position and the location of the nearest airport. Communicate with any available facility using frequencies shown on the sectional chart. If contact is made with the controller, Radar vectors may be offered. Other facilities may offer direct finding, DF assistance. To use this procedure, the controller requests the pilot to hold down the transmit button for a few seconds and then release it. The controller may ask the pilot to change directions a few times and repeat the transmit procedure. This gives the controller enough information to plot the aircraft position and then give vectors to a suitable landing site. If the situation becomes threatening, transmit the situation on the emergency frequency 121.5 MHz and set the transponder to 7,700. Most facilities, and even airliners, monitor the emergency frequency. Flight diversion. There probably comes a time when the pilot is not able to make it to the planned destination. This can be the result of unpredicted weather conditions, a system malfunction, or poor pre-flight planning. In any case, the pilot needs to be able to safely and efficiently divert to an alternate destination. Before any cross-country flight, check the charts for airports or suitable landing areas along or near the route of flight. Also check for navigational aids that can be used during a diversion. Computing course, time, speed, and distance information in flight requires the same computations used during pre-flight planning. However, because of the limited flight deck space, and because attention must be divided between flying the aircraft, making calculations, and scanning for other aircraft, take advantage of all possible shortcuts and rule of thumb computations. When in flight, it is rarely practical to actually plot a course on a sectional chart and mark checkpoints and distances. Furthermore, because an alternate airport is usually not very far from your original course, actual plotting is seldom necessary. A course to an alternate can be measured accurately with a protractor or plotter, but can be measured with reasonable accuracy using a straightedge and the compass rose depicted around VOR stations. This approximation can be made on the basis of a radial from a nearby VOR, or an airway that closely parallels the course to your alternate. However, remember that the magnetic heading associated with a VOR radial or printed airway is outbound from the station. To find the course to the station, it may be necessary to determine the reciprocal of that heading. It is typically easier to navigate to an alternate airport that has a VOR or NDB facility on the field. After selecting the most appropriate alternate, approximate the magnetic course to the alternate using a compass rose or airway on the sectional chart. If time permits, try to start the diversion over a prominent ground feature. However, in an emergency, divert promptly toward your alternate. Attempting to complete all plotting, measuring, and computations involved before diverting to the alternate may only aggravate an actual emergency. Once established on course, note the time, and then use the winds aloft nearest to your diversion point to calculate a heading and GS. Once the GS has been calculated, determine a new arrival time and fuel consumption. Give priority to flying the aircraft while dividing attention between navigation and planning. When determining an altitude to use while diverting, consider cloud heights, winds, terrain, and radio reception. Chapter Summary. This chapter has discussed the fundamentals of VFR navigation, beginning with an introduction to the charts that can be used for navigation, to the more technically advanced concept of GPS, there's one aspect of navigation that remains the same. The pilot is responsible for proper planning and the execution of that planning to ensure a safe flight. End of Part 7 of Chapter 15.
Part 1 of Chapter 16 of Pilot's Handbook. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by April Walters. Pilot's Handbook of Aeronautical Knowledge by the FAA. Chapter 16. Aeromedical Factors. Introduction. It is important for a pilot to be aware of the mental and physical standards required for the type of flying done. This chapter provides information on medical certification and on a variety of aeromedical factors related to flight activities. Obtaining a medical certificate. Most pilots must have a valid medical certificate to exercise the privileges of their airman certificates. Glider and free balloon pilots are not required to hold a medical certificate. Sports pilots may hold either a medical certificate or a valid state driver's license. Acquisition of a medical certificate requires an examination by an aviation medical examiner, AME, a physician with training in aviation medicine designated by the Civil Aerospace Medical Institute, CAMI. There are 3 classes of medical certificates. The class of certificate needed depends on the type of flying the pilot plans to do. The requirements for a third-class medical certificate for a private or recreational pilot certificate are currently under review. For the latest information and requirements regarding third-class medical certificates, reference the updated Regulation 14 CFR Part 61, Section 61.23, particularly the table in paragraph D. See errata for a hyperlink. A commercial pilot requires at least a second-class medical certificate, which is valid for 1 year. First-class medical certificates are required for airline transport pilots and are valid for 6 months. The standards are more rigorous with the higher classes of certificates. A pilot with a higher class medical certificate has met the requirements for the lower classes as well. Since the required medical class applies only when exercising the privileges of the pilot certificate for which it is required, a first-class medical certificate would be valid for 1 year of exercising the privileges of a commercial certificate and 2 or 3 years, as appropriate, for exercising the privileges of a private or recreational certificate. The same applies for a second-class medical certificate. The standards for medical certification are contained in Title 14 of the Code of Federal Regulations, 14 CFR, Part 67, and the requirements for obtaining medical certificates can be found in 14 CFR Part 61. Students who have physical limitations, such as impaired vision, loss of a limb, or hearing impairment, may be issued a medical certificate valid for student pilot privileges only while learning to fly. Pilots with disabilities may require special equipment installed in the aircraft, such as hand controls for pilots with paraplegia. Some disabilities necessitate a limitation on the individual certificate. For example, impaired hearing would require the limitation not valid for flight requiring the use of radio. When all the knowledge, experience, and proficiency requirements have been met, and a student can demonstrate the ability to operate the aircraft with the normal level of safety, a Statement of Demonstrated Ability, SODA, can be issued. This waiver, or SODA, is valid as long as the physical impairment does not worsen. Contact the local Flight Standards District Office, FSDO, for more information on this subject. Health and physiological factors affecting pilot performance. A number of health factors and physiological effects can be linked to flying. Some are minor, while others are important enough to require special attention to ensure safety of flight. In some cases, physiological factors can lead to in-flight emergencies. Some important medical factors that a pilot should be aware of include hypoxia, hyperventilation, middle ear and sinus problems, spatial disorientation, motion sickness, carbon monoxide, CO, poisoning, stress and fatigue, dehydration, and heat stroke. Other subjects include the effects of alcohol and drugs, anxiety, and excess nitrogen in the blood after scuba diving. Hypoxia. Hypoxia means reduced oxygen, or not enough oxygen. Although any tissue will die if deprived of oxygen long enough, usually the most concern is with getting enough oxygen to the brain, since it is particularly vulnerable to oxygen deprivation. Any reduction in mental function while flying can result in life-threatening errors. Hypoxia can be caused by several factors, including an insufficient supply of oxygen, inadequate transportation of oxygen, or the inability of the body tissues to use oxygen. The forms of hypoxia are based on their cause: hypoxic hypoxia, hypemic hypoxia, stagnant hypoxia, and histotoxic hypoxia. Hypoxic hypoxia. Hypoxic hypoxia is a result of insufficient oxygen available to the body as a whole. A blocked airway and drowning are obvious examples of how the lungs can be deprived of oxygen, but the reduction in partial pressure of oxygen at high altitude is an appropriate example for pilots. Although the percentage of oxygen in the atmosphere is constant, its partial pressure decreases proportionately as atmospheric pressure decreases. As the airplane ascends during flight, the percentage of each gas in the atmosphere remains the same, but there are fewer molecules available at the pressure required for them to pass between the membranes in the respiratory system. This decrease in the number of oxygen molecules at sufficient pressure can lead to hypoxic hypoxia. Hypemic hypoxia. Hypemic hypoxia occurs when the blood is not able to take up and transport a sufficient amount of oxygen to the cells in the body. Hypemic means not enough blood. This type of hypoxia is a result of oxygen deficiency in the blood rather than a lack of inhaled oxygen and can be caused by a variety of factors. It may be due to reduced blood volume due to severe bleeding, or it may result from certain blood diseases such as anemia. More often, hypemic hypoxia occurs because hemoglobin, the actual blood molecule that transports oxygen, is chemically unable to bind oxygen molecules. The most common form of hypemic hypoxia is CO poisoning. This is explained in greater detail on page 16-11. Hypemic hypoxia can also be caused by the loss of blood due to blood donation. Blood can require several weeks to return to normal following a donation. Although the effects of the blood loss are slight at ground level, there are risks when flying during this time. Stagnant hypoxia. Stagnant means not flowing. And stagnant hypoxia, or ischemia, results when the oxygen-rich blood in the lungs is not moving, for one reason or another, to the tissues that need it. An arm or leg going to sleep because the blood flow has accidentally been shut off is one form of stagnant hypoxia. This kind of hypoxia can also result from shock, the heart failing to pump blood effectively, or a constricted artery. During flight, stagnant hypoxia can occur with excessive acceleration of gravity, Gs. Cold temperatures can also reduce circulation and decrease the blood supplied to extremities. Histotoxic hypoxia. The inability of the cells to effectively use oxygen is defined as histotoxic hypoxia. Histo refers to tissues or cells, and toxic means poisonous. In this case, enough oxygen is being transported to the cells that need it, but they are unable to make use of it. This impairment of cellular respiration can be caused by alcohol and other drugs, such as narcotics and poisons. Research has shown that drinking 1 ounce of alcohol can equate to about an additional 2,000 feet of physiological altitude. Symptoms of hypoxia. High-altitude flying can place a pilot in danger of becoming hypoxic. Oxygen starvation causes the brain and other vital organs to become impaired. One noteworthy attribute of the onset of hypoxia is that the first symptoms are euphoria and a carefree feeling. With increased oxygen starvation, the extremities become less responsive and flying becomes less coordinated. The symptoms of hypoxia vary with the individual, but common symptoms include cyanosis, blue fingernails and lips, headache, decreased response to stimuli and increased reaction time, impaired judgment, euphoria, visual impairment, drowsiness, lightheaded or dizzy sensation, tingling in fingers and toes, numbness. As hypoxia worsens, the field of vision begins to narrow, and instrument interpretation can become difficult. Even with all these symptoms, the effects of hypoxia can cause a pilot to have a false sense of security and be deceived into believing everything is normal. The treatment for hypoxia includes flying at lower altitudes and/or using supplemental oxygen. All pilots are susceptible to the effects of oxygen starvation, regardless of physical endurance or acclimatization. When flying at high altitudes, it is paramount that oxygen be used to avoid the effects of hypoxia. The term time of useful consciousness describes the maximum time the pilot has to make rational, life-saving decisions and carry them out at a given altitude without supplemental oxygen. As altitude increases above 10,000 feet, the symptoms of hypoxia increase in severity, and the time of useful consciousness rapidly decreases. See Figure 16-1, Time of Useful Consciousness. Altitude, 45,000 feet MSL. Time of Useful Consciousness, 9 to 15 seconds. 40,000 feet MSL. Time of Useful Consciousness, 15 to 20 seconds. 35,000 feet MSL. Time of Useful Consciousness, 30 to 60 seconds. 30,000 feet MSL. Time of Useful Consciousness, 1 to 2 minutes. 28,000 feet MSL. Time of Useful Consciousness, 2½ to 3 minutes. 25,000 feet MSL. Time of Useful Consciousness, 3 to 5 minutes. 22,000 feet MSL. Time of Useful Consciousness, 5 to 10 minutes. 20,000 feet MSL. Time of Useful Consciousness, 30 minutes or more. Since symptoms of hypoxia can be different for each individual, the ability to recognize hypoxia can be greatly improved by experiencing and witnessing the effects of it during an altitude chamber flight. The Federal Aviation Administration, FAA, provides this opportunity through aviation physiology training, which is conducted at the FAA-CMI and at many military facilities across the United States. For information about the FAA's one-day physiological training course with altitude chamber and vertigo demonstrations, visit the FAA website, www.faa.gov/pilots/airman_education/aerospace_physiology/index.cfm. Hyperventilation. Hyperventilation is the excessive rate and depth of respiration leading to abnormal loss of carbon dioxide from the blood. This condition occurs more often among pilots than is generally recognized. It seldom incapacitates completely, but it causes disturbing symptoms that can alarm the uninformed pilot. In such cases, increased breathing rate and anxiety further aggravate the problem. Hyperventilation can lead to unconsciousness due to the respiratory system's overriding mechanism to regain control of breathing. Pilots encountering an unexpected stressful situation may subconsciously increase their breathing rate. If flying at higher altitudes, either with or without oxygen, a pilot may have a tendency to breathe more rapidly than normal, which often leads to hyperventilation. Since many of the symptoms of hyperventilation are similar to those of hypoxia, it is important to correctly diagnose and treat the proper condition. If using supplemental oxygen, check the equipment and flow rate to ensure the symptoms are not hypoxia-related. Common symptoms of hyperventilation include visual impairment, unconsciousness, lightheaded or dizzy sensations, tingling sensations, hot and cold sensations, muscle spasms. The treatment for hyperventilation involves restoring the proper carbon dioxide level in the body. Breathing normally is both the best prevention and the best cure for hyperventilation. In addition to slowing the breathing rate, breathing into a paper bag or talking aloud helps to overcome hyperventilation. Recovery is usually rapid once the breathing rate is returned to normal. Middle ear and sinus problems. During climbs and descents, the free gas formerly present in various body cavities expands due to a difference between the pressure of the air outside the body and that of the air inside the body. If the escape of the expanded gas is impeded, pressure builds up within the cavity and pain is experienced. Trapped gas expansion accounts for ear pain and sinus pain, as well as a temporary reduction in the ability to hear. The middle ear is a small cavity located in the bone of the skull. It is closed off from the external ear canal by the eardrum. Normally, pressure differences between the middle ear and the outside world are equalized by a tube leading from the inside each ear to the back of the throat on each side, called the eustachian tube. These tubes are usually closed, but open during chewing, yawning, or swallowing to equalize pressure. Even a slight difference between external pressure and middle ear pressure can cause discomfort. See Figure 16-2. During a climb, middle ear air pressure may exceed the pressure of the air in the external ear canal, causing the eardrum to bulge outward. Pilots become aware of this pressure change when they experience alternate sensations of fullness and clearing. During descent, the reverse happens. When the pressure of the air in the external ear canal increases, the middle ear cavity, which equalized with the lower pressure at altitude, is at lower pressure than the external ear canal. And this results in the higher outside pressure, causing the eardrum to bulge inward. This condition can be more difficult to relieve due to the fact that the partial vacuum tends to constrict the walls of the eustachian tube. To remedy this often painful condition, which also causes a temporary reduction in hearing sensitivity, pinch the nostrils shut, close the mouth and lips,
and blow slowly and gently in the mouth and nose.
This procedure forces air through the eustachian tube into the middle ear. It may not be possible to equalize the pressure in the ears if a pilot has a cold, an ear infection, or a sore throat. A flight in this condition can be extremely painful, as well as damaging to the eardrums. If experiencing minor congestion, nose drops or nasal sprays may reduce the risk of a painful ear blockage. Before using any medication, check with an AME to ensure that it will not affect the ability to fly. In a similar way, air pressure in the sinuses equalizes with the pressure in the flight deck through small openings that connect the sinuses to the nasal passages. An upper respiratory infection, such as a cold or sinusitis, or a nasal allergic condition can produce enough congestion around an opening to slow equalization. As the difference in pressure between the sinuses and the flight deck increases, congestion may plug the opening. This sinus block occurs most frequently during descent. Slow descent rates can reduce the associated pain. A sinus block can occur in the frontal sinuses, located above each eyebrow, or in the maxillary sinuses, located in each upper cheek. It will usually produce excruciating pain over the sinus area. A maxillary sinus block can also make the upper teeth ache. Bloody mucus may discharge from the nasal passages. Sinus block can be avoided by not flying with an upper respiratory infection or nasal allergic condition. Adequate protection is usually not provided by decongestant sprays or drops to reduce congestion around the sinus openings. Oral decongestants have side effects that can impair pilot performance. If a sinus block does not clear shortly after landing, a physician should be consulted. End of Part 1 of Chapter 16. Recording by April Walters.
Part 2 of Chapter 16 of the Pilot's Handbook. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information, or to volunteer, please visit LibriVox.org. Recording by Nathan Heck. The Pilot's Handbook of Aeronautical Knowledge by the FAA. Part 2 of Chapter 16. Spatial Disorientations and Illusions. Spatial disorientation specifically refers to the lack of orientation with regard to the position, altitude, or movement of the airplane in space. The body uses three integrated systems working together to ascertain orientation and movement in space. The vestibular system, organs found in the inner ear that sense position by the way we are balanced. The somatosensory system, nerves in the skin, muscles, and joints, which, along with hearing, sense position based on gravity, feeling, and sound. The visual system, eyes, which sense position based on what is seen. All this information comes together in the brain and, most of the time, the three streams of information agree, giving a clear idea of where and how the body is moving. Flying can sometimes cause these systems to supply conflicting information to the brain, which can lead to disorientation. During flight, in visual meteorological conditions, VMC, the eyes are the major orientation source and usually prevail over false sensations from other sensory systems. When these visual cues are removed, as they are in instrument meteorological conditions, IMC, false sensations can cause a pilot to quickly become disoriented. The vestibular system in the inner ear allows the pilot to sense movement and determine orientation in the surrounding environment. In both the left and right inner ear, 3 semicircular canals are positioned at approximate right angles to one another. See Figure 16.3. Each canal is filled with fluid and has a section full of fine hairs. Acceleration of the inner ear in any direction causes the tiny hairs to deflect, which in turn stimulates nerve impulses, sending messages to the brain. The vestibular nerve transmits the impulses from the utricle, saccule, and semicircular canals to the brain to interpret motion. The somatosensory system sends signals from the skin, joints, and muscles to the brain that are interpreted in relation to the Earth's gravitational pull. These signals determine posture. Inputs from each movement update the body's position to the brain on a constant basis. Seat of the pants flying is largely dependent upon these signals. Used in conjunction with visual and vestibular clues, these senses can be fairly reliable. However, the body cannot distinguish between acceleration forces due to gravity and those resulting from maneuvering the aircraft, which can lead to sensory illusions and false impressions of an aircraft's orientation and movement. Under normal flight conditions, when there is a visual reference to the horizon and ground, the sensory system in the inner ear helps to identify the pitch, roll, and yaw movements of the aircraft. When visual contact with the horizon is lost, the vestibular system becomes unreliable. Without visual references outside the aircraft, there are many situations in which combinations of normal motions and forces create convincing illusions that are difficult to overcome. Prevention is usually the best remedy for spatial disorientation. Unless a pilot has many hours of training in instrument flight, flight should be avoided in reduced visibility or at night when the horizon is not visible. A pilot can reduce susceptibility to disorienting illusions through training and awareness, and learning to rely totally on flight instruments. Vestibular illusions, the leans. A condition called the leans can result when a banked altitude, to the left for example, may be entered too slowly to set in motion the fluid in the roll semicircular tubes. See Figure 16.4. An abrupt correction of this altitude sets the fluid in motion, creating the illusion of a banked altitude to the right. The disoriented pilot may make the error of rolling the aircraft into the original left banked altitude, or, if level flight is maintained, will feel compelled to lean in the perceived vertical plane until this illusion subsides. Coriolis illusion. The Coriolis illusion occurs when a pilot has been in a turn long enough for the fluid in the ear canal to move at the same speed as the canal. A movement of the head in a different plane, such as looking at something in a different part of the flight deck, may set the fluid moving and create the illusion of turning or accelerating on an entirely different axis. This action causes the pilot to think the aircraft is doing a maneuver that it is not. The disoriented pilot may maneuver the aircraft into a dangerous altitude in an attempt to correct the aircraft's perceived altitude. For this reason, it is important that pilots develop an instrument cross-check or scan that involves minimal head movement. Take care when retrieving charts and other objects in the flight deck. If something is dropped, retrieve it with minimal head movement and be alert for the Coriolis illusion. Graveyard spiral. As in other illusions, a pilot in a prolonged, coordinated, constant rate turn will have the illusion of not turning. During the recovery to level flight, the pilot will experience the sensation of turning in the opposite direction. The disoriented pilot may return the aircraft to its original turn. Because an aircraft tends to lose altitude in turns unless the pilot compensates for the loss in lift, the pilot may notice a loss of altitude. The absence of any sensation of turning creates the illusion of being in a level descent. The pilot may pull back on the controls in an attempt to climb or stop the descent. This action tightens the spiral and increases the loss of altitude. This illusion is referred to as a graveyard spiral. See Figure 16.5. At some point, this could lead to a loss of aircraft control. Somatographic illusion. A rapid acceleration, such as experienced during takeoff, stimulates the otolith organs in the same way as tilting the head backwards. This action creates the somatographic illusion of being in a nose-up altitude, especially in situations without good visual references. The disoriented pilot may push the aircraft into a nose-low or dive attitude. A rapid deceleration by quick reduction of the throttle can have the opposite effect, with the disoriented pilot pulling the aircraft into a nose-up or stall attitude. Inversion illusion. An abrupt change from climb to straight and level flight can stimulate the otolith organs enough to create the illusion of tumbling backwards, or inversion illusion. The disoriented pilot may push the aircraft abruptly into a nose-low attitude, possibly intensifying this illusion. Elevator illusion. An abrupt upward vertical acceleration, as can occur in an updraft, can stimulate the otolith organs to create the illusion of being in a climb. This is called elevator illusion. The disoriented pilot may push the aircraft into a nose-low attitude. An abrupt downward vertical acceleration, usually in a downdraft, has the opposite effect, with the disoriented pilot pulling the aircraft into a nose-up attitude. Visual illusions. Visual illusions are especially hazardous because pilots rely on their eyes for correct information. Two illusions that lead to spatial disorientation, false horizon and autokinesis, are concerned with only the visual system. False horizon. A sloping cloud formation, an obscured horizon, an aurora borealis, a dark scene spread with ground lights and stars, and certain geometric patterns of ground lights can provide inaccurate visual information, or false horizon, for aligning the aircraft correctly with the actual horizon. The disoriented pilot may place the aircraft in a dangerous attitude. Autokinesis. In the dark, a stationary light will appear to move about when stared at for many seconds. The disoriented pilot could lose control of the aircraft in attempting to align it with the false movements of this light, called autokinesis. Postural considerations. The postural system sends signals from the skin, joints, and muscles to the brain that are interpreted in relation to Earth's gravitational pull. These signals determine posture. Inputs from each movement update the body's position to the brain on a constant basis. Seat of the pants flying is largely dependent upon these signals. Used in conjunction with visual and vestibular clues, these sensations can be fairly reliable. However, because of the forces acting upon the body in certain flight situations, many false sensations can occur due to acceleration forces overpowering gravity. See Figure 16.6. These situations include uncoordinated turns, climbing turns, and turbulence. Demonstration of spatial disorientation. There are a number of controlled aircraft maneuvers a pilot can perform to experiment with spatial disorientation. While each maneuver will normally create a specific illusion, any false sensation is an effective demonstration of disorientation. Thus, even if there is no sensation during any of these maneuvers, the absence of sensation is still an effective demonstration because it illustrates the inability to detect bank or roll. There are several objectives in demonstrating these various maneuvers. 1. They teach pilots to understand the susceptibility of the human system to spatial disorientation. 2. They demonstrate that judgments of aircraft attitude based on bodily sensations are frequently false. 3. They help decrease the occurrence and degree of disorientation through a better understanding of the relationships between aircraft motion, head movements, and resulting disorientation. 4. They help instill a greater confidence in relying on flight instruments for assessing true aircraft attitude. A pilot should not attempt any of these maneuvers at low altitudes, or in the absence of an instructor pilot or an appropriate safety pilot. Climbing while accelerating. With the pilot's eyes closed, the instructor pilot maintains approach airspeed and a straight and level attitude for several seconds, then accelerates while maintaining straight and level attitude. The usual illusion during this maneuver without visual references is that the aircraft is climbing. Climbing while turning. With the pilot's eyes still closed and the aircraft in a straight and level attitude, the instructor pilot now executes, with a relatively slow entry, a well-coordinated turn of about 1.5 positive g, approximately 50% bank, for 90%. While in the turn, without outside visual references and under the effect of the slight positive g, the usual illusion produced is that of a climb. Upon sensing the climb, the pilot should immediately open the eyes to see that a slowly established coordinated turn produces the same sensation as a climb. Diving while turning. Repeating the previous procedure, except the pilot's eyes should be kept closed until recovery from the turn is approximately one-half completed, can create the illusion of diving while turning. Tilting to right or left. While in a straight and level attitude, with the pilot's eyes closed, the instructor pilot executes a moderate or slight skid to the left with wings level. This creates the illusion of the body being tilted to the right. Reversal of motion. This illusion can be demonstrated in any of the three planes of motion. While straight and level, with the pilot's eyes closed, the instructor pilot smoothly and positively rolls the aircraft to approximately 45-degree bank altitude while maintaining heading and pitch attitude. This creates the illusion of a strong sense of rotation in the opposite direction. After this illusion is noted, the pilot should open his or her eyes and observe that the aircraft is in a banked attitude, diving or rolling beyond the vertical plane. This maneuver may produce extreme disorientation. While in straight and level flight, the pilot should sit normally, either with eyes closed or gaze lowered to the floor. The instructor starts a positive coordinated roll toward a 30 or 40 degree angle of bank. As this is in progress, the pilot tilts his or her head forward, looks to the right or left, then immediately returns his or her head to an upright position. The instructor pilot should time the maneuver so the roll is stopped as the pilot returns his or her head upright. An intense disorientation is usually produced by this maneuver, and the pilot experiences the sensation of falling downward into the direction of the roll. In the descriptions of these maneuvers, the instructor pilot is doing the flying, but having the pilot do the flying can also be a very effective demonstration. The pilot should close his or her eyes and tilt the head to one side. The instructor pilot tells the pilot what control inputs to perform. The pilot then attempts to establish the correct attitude or control input with eyes closed and head tilted. While it is clear that the pilot has no idea of the actual attitude, he or she will react to what the senses are saying. After a short time, the pilot will become disoriented, and the instructor pilot then tells the pilot to look up and recover. The benefit of this exercise is that the pilot experiences the disorientation while flying the aircraft. Coping with spatial disorientation. To prevent illusions and their potentially disastrous consequences, pilots can 1. Understand the causes of these illusions and remain constantly alert for them. Take the opportunity to experience spatial disorientation illusions in a device such as a Barony chair, a Vertigon, or a virtual reality spatial disorientation demonstrator. 2. Always obtain and understand pre-flight weather briefings. 3. Before flying in marginal visibility, less than 3 miles, or where a visible horizon is not evident, such as flight over open water during the night, obtain training and maintain proficiency in airplane control by reference to instruments. 4. Do not continue flight into adverse weather conditions or into dusk or darkness unless proficient in the use of flight instruments. If intending to fly at night, maintain night flight currency and proficiency. Include cross-country and local operations at various airfields. 5. Ensure that when outside visual references are used, they are reliable fixed points on the Earth's surface. 6. Avoid sudden head movement, particularly during takeoffs, turns, and approaches to landing. 7. Be physically tuned for flight into reduced visibility. That is, ensure proper rest, adequate diet, and, if flying at night, allow for night adaptation. Remember that illness, medication, alcohol, fatigue, sleep loss, and mild hypoxia are likely to increase susceptibility to spatial disorientation. 8. Most importantly, become proficient in the use of flight instruments and rely upon them. Trust the instruments and disregard your sensory perceptions. The sensations that lead to illusions during instrument flight conditions are normal perceptions experienced by pilots. These undesirable sensations cannot be completely prevented, but through training and awareness, pilots can ignore or suppress them by developing absolute reliance on the flight instruments. As pilots gain proficiency in instrument flying, they become less susceptible to these illusions and their effects. Optical illusions. Of the senses, vision is the most important for safe flight. However, various terrain features and atmospheric conditions can create optical illusions. These illusions are primarily associated with landing. Since pilots must transition from reliance on instruments to visual cues outside the flight deck for landing at the end of an instrument approach, it is imperative that they be aware of the potential problems associated with these illusions and take appropriate corrective action. The major illusions leading to landing errors are described below. Runway width illusion. A narrower than usual runway can create an illusion the aircraft is at a higher altitude than it actually is, especially when runway length to width relationships are comparable. See Figure 16.7. The pilot who does not recognize this illusion will fly a lower approach, with the risk of striking objects along the approach path or landing short. A wider than usual runway can have the opposite effect, with the risk of the pilot leveling out on the aircraft high and landing hard, or overshooting the runway. Runway and terrain slopes illusion. An upsloping runway, upsloping terrain, or both, can create an illusion that the aircraft is at a higher altitude than it actually is. See Figure 16.7. The pilot who does not recognize this illusion will fly a lower approach. Downsloping runways and downsloping approach terrain can have the opposite effect. Featureless terrain illusion. An absence of surrounding ground features, as in an overwater approach over darkened areas, or terrain made featureless by snow, can create an illusion that the aircraft is at a higher altitude than it actually is. This illusion, sometimes referred to as the black hole approach, causes pilots to fly at a lower approach than is desired. Water refraction. Rain on the windscreen can create an illusion of being at a higher altitude due to the horizon appearing lower than it is. This can result in the pilot flying a lower approach. Haze. Atmospheric haze can create an illusion of being at a greater distance and height from the runway. As a result, the pilot will have a tendency to be low on the approach. Conversely, extremely clear air, clear bright conditions of a high-altitude airport, can give the pilot the illusion of being closer than he or she actually is, resulting in a high approach, which may result in an overshoot or go-around. The diffusion of light due to water particles on the windshield can adversely affect depth perception. The lights and terrain features normally used to gauge height during landing become less effective for the pilot. Fog. Flying into fog can create an illusion of pitching up. Pilots who do not recognize this illusion will often steepen the approach quite abruptly. Ground lighting illusions. Lights along a straight path, such as a road or lights along moving trains, can be mistaken for runway and approach lights. Bright runway and approach lighting systems, especially where few lights illuminate the surrounding terrain, may create the illusion of less distance to the runway. The pilot who does not recognize this illusion will often fly a higher approach. How to prevent landing errors due to optical illusions. To prevent these illusions and their potentially disastrous consequences, pilots can 1. Anticipate the possibility of visual illusions during approaches to unfamiliar airports, particularly at night or in adverse weather conditions. Consult airport diagrams and the Airport Facility Directory, AFD, for information on runway slope, terrain, and lighting. 2. Make frequent reference to the altimeter, especially during all approaches, day and night. 3. If possible, conduct aerial visual inspection of unfamiliar airports before landing. 4. Use Visual Approach Slope Indicator, VASI, or Precision Approach Path Indicator, PAPI systems for a visual reference, or an electronic glide slope whenever they are available. 5. Utilize the Visual Descent Point, VDP, found on many non-precision instrument approach procedure charts. 6. Recognize that the chances of being involved in an approach accident increase when some emergency or other activity distracts from usual procedures. 7. Maintain optimum proficiency and landing procedures. In addition to the sensory illusions due to misleading inputs to the vestibular system, a pilot may also encounter various visual illusions during flight. Illusions rank among the most common factors cited as contributing to fatal aviation accidents. Sloping cloud formations, an obscured horizon, a dark scene spread with ground lights and stars, and certain geometric patterns of ground light can create illusions of not being aligned correctly with the actual horizon. Various surface features and atmospheric conditions encountered in landing can create illusions of being on the wrong approach path. Landing errors due to these illusions can be prevented by anticipating them during approaches, inspecting unfamiliar airports before landing, using electronic glide slope or VASI systems when available, and maintaining proficiency in landing procedures. End of Part 2 of Chapter 16. Recording by Nathan Heck.
Part 3 of Chapter 16 of Pilot's Handbook. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by April Walters. Pilot's Handbook of Aeronautical Knowledge by the FAA. Part 3 of Chapter 16.
Motion sickness.
Motion sickness, or air sickness, is caused by the brain receiving conflicting messages about the state of the body. A pilot may experience motion sickness during initial flights, but it generally goes away within the first few lessons. Anxiety and stress, which may be experienced at the beginning of flight training, can contribute to motion sickness. Symptoms of motion sickness include general discomfort, nausea, dizziness, paleness, sweating, and vomiting. It is important to remember that experiencing air sickness is no reflection on one's ability as a pilot. If prone to motion sickness, let the flight instructor know. There are techniques that can be used to overcome this problem. For example, avoid lessons in turbulent conditions until becoming more comfortable in the aircraft, or start with shorter flights and graduate to longer instruction periods. If symptoms of motion sickness are experienced during a lesson, opening fresh air vents, focusing on objects outside the airplane, and avoiding unnecessary head movements may help alleviate some of the discomfort. Although medications like Dramamine can prevent air sickness in passengers, they are not recommended while flying, since they can cause drowsiness and other problems. Carbon monoxide, CO, poisoning. CO is a colorless and odorless gas produced by all internal combustion engines. Attaching itself to the hemoglobin in the blood about 200 times more easily than oxygen, CO prevents the hemoglobin from carrying oxygen to the cells, resulting in hypemic hypoxia. The body requires up to 48 hours to dispose of CO. If severe enough, the CO poisoning can result in death. Aircraft heater vents and defrost vents may provide CO a passageway into the cabin, particularly if the engine exhaust system has a leak or is damaged. If a strong odor of exhaust gases is detected, assume that CO is present. However, CO may be present in dangerous amounts even if no exhaust odor is detected. Disposable, inexpensive CO detectors are widely available. In the presence of CO, these detectors change color to alert the pilot of the presence of CO. Some effects of CO poisoning are headache, blurred vision, dizziness, drowsiness, and/or loss of muscle power. Any time a pilot smells exhaust odor, or any time that these symptoms are experienced, immediate corrective actions should be taken. These include turning off the heater, opening fresh air vents and windows, and using supplemental oxygen if available. Tobacco smoke also causes CO poisoning. Smoking at sea level can raise the CO concentration in the blood and result in physiological effects similar to flying at 8,000 feet. Besides hypoxia, tobacco causes diseases and physiological debilitation that are medically disqualifying for pilots. Stress is the body's response to physical and psychological demands placed upon it. The body's reaction to stress includes releasing chemical hormones, such as adrenaline, into the blood and increasing metabolism to provide more energy to the muscles. Blood sugar, heart rate, respiration, blood pressure, and perspiration all increase. The term stressor is used to describe an element that causes an individual to experience stress. Examples of stressors include physical stress, noise or vibration, physiological stress, fatigue, and psychological stress, difficult work or personal situations. Stress falls into two broad categories: acute, short-term, and chronic, long-term. Acute stress involves an immediate threat that is perceived as danger. This is the type of stress that triggers a fight or flight response in an individual, whether the threat is real or imagined. Normally, a healthy person can cope with acute stress and prevent stress overload. However, ongoing acute stress can develop into chronic stress. Chronic stress can be defined as a level of stress that prevents an intolerable burden, exceeds the ability of an individual to cope, and causes individual performance to fall sharply. Unrelenting psychological pressures, such as loneliness, financial worries, and relationship or work problems, can produce a cumulative level of stress that exceeds a person's ability to cope with the situation. When stress reaches these levels, performance falls off rapidly. Pilots experiencing this level of stress are not safe and should not exercise their airman privileges. Pilots who suspect they are suffering from chronic stress should consult a physician. Fatigue. Fatigue is frequently associated with pilot error. Some of the effects of fatigue include degradation of attention and concentration, impaired coordination, and decreased ability to communicate. These factors seriously influence the ability to make effective decisions. Physical fatigue results from sleep loss, exercise, or physical work. Factors such as stress and prolonged performance of cognitive work result in mental fatigue. Like stress, fatigue falls into two broad categories, acute and chronic. Acute fatigue is short-term and is a normal occurrence in everyday living. It is the kind of tiredness people feel after a period of strenuous effort, excitement, or lack of sleep. Rest after exertion and 8 hours of sound sleep ordinarily cures this condition. A special type of acute fatigue is skill fatigue. This type of fatigue has two main effects on performance. Timing disruption, appearing to perform a task as usual, but the timing of each component is slightly off. This makes the pattern of operation less smooth because the pilot performs each component as though it were separate instead of part of an integrated activity. Disruption of the perceptual field, concentrating attention upon movements or objects in the center of vision and neglecting those in the periphery. This is accompanied by loss of accuracy and smoothness in control movements. Acute fatigue has many causes, but the following are among the most important for the pilot. Mild hypoxia, oxygen deficiency, physical stress, psychological stress, and depletion of physical energy resulting from psychological stress, sustained psychological stress. Sustained psychological stress accelerates the glandular secretions that prepare the body for quick reactions during an emergency. These secretions make the circulatory and respiratory systems work harder, and the liver releases energy to provide the extra fuel needed for brain and muscle work. When this reserve energy supply is depleted, the body lapses into generalized and severe fatigue. Acute fatigue can be prevented by proper diet and adequate rest and sleep. A well-balanced diet prevents the body from needing to consume its own tissues as an energy source. Adequate rest maintains the body's store of vital energy. Chronic fatigue, extending over a long period of time, usually has psychological roots, although an underlying disease is sometimes responsible. Continuous high stress levels produce chronic fatigue. Chronic fatigue is not relieved by proper diet and adequate rest and sleep, and usually requires treatment by a physician. An individual may experience this condition in the form of weakness, tiredness, palpitations of the heart, breathlessness, headaches, or irritability. Sometimes chronic fatigue even creates stomach or intestinal problems and generalized aches and pains throughout the body. When the condition becomes serious enough, it leads to emotional illness. If suffering from acute fatigue, stay on the ground. If fatigue occurs in the flight deck, no amount of training or experience can overcome the detrimental effects. Getting adequate rest is the only way to prevent fatigue from occurring. Avoid flying without a full night's rest after working excessive hours or after an especially exhausting or stressful day. Pilots who suspect they are suffering from chronic fatigue should consult a physician. Dehydration and heat stroke. Dehydration is the term given to critical loss of water from the body. Causes of dehydration are hot flight decks and flight lines, wind, humidity, and diuretic drinks, coffee, tea, alcohol, and caffeinated soft drinks. Some common signs of dehydration are headache, fatigue, cramps, sleepiness, and dizziness. The first noticeable effect of dehydration is fatigue, which in turn makes top physical and mental performance difficult, if not impossible. Flying for long periods in hot summer temperatures or at high altitudes increases the susceptibility to dehydration because these conditions tend to increase the rate of water loss from the body. To help prevent dehydration, drink 2 to 4 quarts of water every 24 hours. Since each person is physiologically different, this is only a guide. Most people are aware of the 8 glasses a day guide. If each glass of water is 8 ounces, this equates to 64 ounces, which is 2 quarts. If this fluid is not replaced, fatigue proceeds to dizziness, weakness, nausea, tingling of hands and feet, abdominal cramps, and extreme thirst. The key for pilots is to be continually aware of their condition. Most people become thirsty with a 1.5 quart deficit, or loss of 2% of total body weight. This level of dehydration triggers the thirst mechanism. The problem is that the thirst mechanism arrives too late and is turned off too easily. A small amount of fluid in the mouth will turn this mechanism off, and the replacement of needed body fluid is delayed. Other steps to prevent dehydration include carrying a container in order to measure daily water intake, staying ahead, not relying on the thirst sensation of an alarm. If plain water is offensive, add some sport drink flavoring to make it more acceptable. Limiting daily intake of caffeine and alcohol. Both are diuretics and stimulate increased production of urine. Heat stroke is a condition caused by any inability of the body to control its temperature. Onset of this condition may be recognized by the symptoms of dehydration, but also has been known to be recognized only by complete collapse. To prevent these symptoms, it is recommended that an ample supply of water be carried and used at frequent intervals on any long flight, whether thirsty or not. The body normally absorbs water at the rate of 1.2 to 1.5 quarts per hour. Individuals should drink 1 quart per hour for severe heat stress conditions or 1 pint per hour for moderate stress conditions. If the aircraft has a canopy or roof window, wearing light-colored porous clothing and a hat will help provide protection from the sun. Keeping the flight deck well ventilated aids in dissipating excess heat. Alcohol. Alcohol impairs the efficiency of the human body. See Figure 16-8. Studies have proved that drinking and performance deterioration are closely linked. Pilots must make hundreds of decisions, some of them time-critical, during the course of a flight. The safe outcome of any flight depends on the ability to make the correct decisions and take the appropriate actions during routine occurrences, as well as abnormal situations. The influence of alcohol drastically reduces the chances of completing a flight without incident. Even in small amounts, alcohol can impair judgment, decrease sense of responsibility, affect coordination, constrict visual field, diminish memory, reduce reasoning power, and lower attention span. As little as 1 ounce of alcohol can decrease the speed and strength of muscular reflexes, lengthen the efficiency of eye movements while reading, and increase the frequency at which errors are committed. Impairments in vision and hearing occur at alcohol blood levels due to as little as 1 drink. Figure 16-8. Impairment scale with alcohol use. Type of beverage. Table wine. A typical serving of 4 ounces has 0.48 ounces of pure alcohol content. Light beer. A typical serving of 12 ounces has 0.48 ounces pure alcohol content. Aperitif liquor. Typical serving 1.5 ounces has 0.38 ounces of pure alcohol content. Champagne. Typical serving of 4 ounces has 0.48 ounces of pure alcohol content. Vodka. Typical serving 1 ounce has pure alcohol content of 0.50 ounces. Whiskey. Typical serving 1.25 ounces has a pure alcohol content of 0.50 ounces. 0.01 to 0.05 blood alcohol content, which is 10 to 50 milligrams of alcohol per deciliter of blood. Average individual appears normal. 0.03 to 0.12 blood alcohol content, or 30 to 120 milligrams of alcohol per deciliter of blood. Symptoms include mild euphoria, talkativeness, decreased inhibitions, decreased attention, impaired judgment, increased reaction time. From 0.09 to 0.25 blood alcohol content, or 90 to 250 milligrams of alcohol per deciliter of blood. Symptoms include emotional instability, loss of critical judgment, impairment of memory and comprehension, decreased sensory response, mild muscular incoordination. At 0.18 to 0.30 blood alcohol content, or 180 to 300 milligrams of alcohol per deciliter of blood, symptoms include confusion, dizziness, exaggerated emotions, anger, fear, grief, impaired visual perception, decreased pain sensation, impaired balance, staggering gait, slurred speech, moderate muscular incoordination. From 0.27 to 0.40 blood alcohol content, or 270 to 400 milligrams of alcohol per deciliter of blood, symptoms include apathy, impaired consciousness, stupor, significantly decreased response to stimulation, severe muscular incoordination, inability to stand or walk, vomiting, incontinence of urine and feces. From 0.35 to 0.50 blood alcohol content, or 350 to 500 milligrams of alcohol per deciliter of blood. Symptoms include unconsciousness, depressed or abolished reflexes, abnormal body temperature, coma, possible death from respiratory paralysis at 450 milligrams of alcohol or above. Note, legal limit for motor vehicle operation in most states is 0.08 or 0.10% or 80 to 100 milligrams of alcohol per deciliter of blood. The alcohol consumed in beer and mixed drinks is ethyl alcohol, a central nervous system depressant. From a medical point of view, it acts on the body much like a general anesthetic. The dose is generally much lower and more slowly consumed in the case of alcohol, but the basic effects on the human body are similar. Alcohol is easily and quickly absorbed by the digestive tract. The bloodstream absorbs about 80 to 90% of the alcohol in a drink within 30 minutes when ingested on an empty stomach. The body requires about 3 hours to rid itself of all the alcohol contained in one mixed drink or one beer. While experiencing a hangover, a pilot is still under the influence of alcohol. Although a pilot may think he or she is functioning normally, motor and mental response impairment is still present. Considerable amounts of alcohol can remain in the body for over 16 hours, so pilots should be cautious about flying too soon after drinking. Altitude multiplies the effects of alcohol on the brain. When combined with altitude, the alcohol from 2 drinks may have the same effect as 3 or 4 drinks. Alcohol interferes with the brain's ability to utilize oxygen, producing a form of histotoxic hypoxia. The effects are rapid because alcohol passes quickly into the bloodstream. In addition, the brain is a highly vascular organ that is immediately sensitive to changes in the blood's composition. For a pilot, the lower oxygen availability at altitude and the lower capability of the brain to use what oxygen is there add up to a deadly combination. Intoxication is determined by the amount of alcohol in the bloodstream. This is usually measured as a percentage by weight in the blood. 14 CFR Part 91 requires that the blood alcohol level be less than 0.04% and that 8 hours pass between drinking alcohol and piloting an airplane. A pilot with a blood alcohol level of 0.04% or greater after 8 hours cannot fly until the blood alcohol falls below that amount. Even though the blood alcohol may be well below 0.04%, a pilot cannot fly sooner than 8 hours after drinking alcohol. Although the regulations are quite specific, it is a good idea to be more conservative than the regulations. Drugs. Pilot performance can be seriously degraded by both prescription and over-the-counter medications, as well as by the medical conditions for which they are taken. Many medications, such as tranquilizers, sedatives, strong pain relievers, and cough suppressants, have primary effects that may impair judgment, memory alertness, coordination, vision, and the ability to make calculations. See Figure 16-9. Others, such as antihistamines, blood pressure drugs, muscle relaxants, and agents to control diarrhea and motion sickness, have side effects that may impair the same critical functions. Any medicine that depresses the nervous system, such as a sedative, tranquilizer, or antihistamine, can make a pilot more susceptible to hypoxia. Painkillers are grouped into 2 broad categories: analgesics and anesthetics. Analgesics are drugs that reduce pain, while anesthetics are drugs that deaden pain or cause loss of consciousness. Over-the-counter analgesics, such as acetylacetic acid, aspirin, acetaminophen, Tylenol, and ibuprofen, Advil, have few side effects when taken in the correct dosage. Although some people are allergic to certain analgesics or may suffer from stomach irritation, flying usually is not restricted when taking these drugs. However, flying is almost always precluded while using prescription analgesics, such as drugs containing propoxyphene, e.g. Darvon, oxycodone, e.g. Percodan, meperidine, e.g. Demerol, and codeine, since these drugs are known to cause side effects such as mental confusion, dizziness, headaches, nausea, and vision problems. Anesthetic drugs are commonly used for dental and surgical procedures. Most local anesthetics used for minor dental and outpatient procedures wear off within a relatively short period of time. The anesthetic itself may not limit flying as much as the actual procedure and subsequent pain. Stimulants are drugs that excite the central nervous system and produce an increase in alertness and activity. Amphetamines, caffeine, and nicotine are all forms of stimulants. Common uses of these drugs include appetite suppression, fatigue reduction, and mood elevation. Some of these drugs may cause a stimulant reaction, even though this reaction is not their primary function. In some cases, stimulants can produce anxiety and mood swings, both of which are dangerous when flying. Depressants are drugs that reduce the body's functioning in many areas. These drugs lower blood pressure, reduce mental processing, and slow motor and reaction responses. There are several types of drugs that can cause a depressing effect on the body, including tranquilizers, motion sickness medication, some types of stomach medication, decongestants, and antihistamines. The most common depressant is alcohol. Some drugs that are classified as neither stimulants nor depressants have adverse effects on flying. For example, some antibiotics can produce dangerous side effects, such as balance disorders, hearing loss, nausea, and vomiting. While many antibiotics are safe for use while flying, the infection requiring the antibiotic may prohibit flying. In addition, unless specifically prescribed by a physician, do not take more than one drug at a time, and never mix drugs with alcohol, because the effects are often unpredictable. The dangers of illegal drugs are also well documented. Certain illegal drugs can have hallucinatory effects that occur days or weeks after the drug is taken. Obviously, these drugs have no place in the aviation community. 14 CFR prohibits pilots from performing crew member duties while using any medication that affects the body in any way contrary to safety. The safest rule is not to fly as a crew member while taking any medication unless approved to do so by the FAA. If there is any doubt regarding the effects of any medication, consult an AME before flying. Figure 16-9. Adverse effects of various drugs. Alcohol, such as beer, wine, hard liquor. Range of effects from relaxation, lowered inhibitions, reduced intensity of physical sensations, digestive upsets, body heat loss, and reduced muscular coordination, to loss of body control, passing out, also causing physical injuries, susceptibility to pneumonia, cessation of breathing. Development of tolerance, moderate. Prolonged use of large amounts, liver damage, ulcers, chronic diarrhea, amnesia, vomiting, brain damage, internal bleeding, debilitation. Withdrawal symptoms after prolonged use. Convulsions, shakes, hallucinations, loss of memory, uncontrolled muscular spasms, psychosis. Sedative hypnotics, such as barbiturates, Nembutal, phenobarbital, Seconal, and tranquilizers such as Valium, Librium, Quaaludes. Range of effects from relaxation, lowered inhibitions, reduced intensity of physical sensations, digestive upsets, body heat loss, reduced muscular coordination, to passing out, loss of body control, stupor, severe depression of respiration, possible death. Effects are exaggerated when used in combination with alcohol, synergistic effect. Development of tolerance, moderate. Prolonged use of large amounts, amnesia, confusion, drowsiness, personality changes. Withdrawal symptoms after prolonged use, convulsions, shakes, hallucinations, loss of memory, uncontrolled muscular spasms, psychosis. Opiates, such as opium, morphine, heroin, codeine, Dilaudid, Percodan, Darvon, methadone. Range of effects from suppression of pain, lowered blood pressure and respiratory rate, constipation, disruption of menstrual cycle, hallucinations, and sleep, to clammy skin, convulsions, coma, respiratory depression, possible death. Development of tolerance, high. Prolonged use of large amounts leads to depressed sexual drive, lethargy, general physical debilitation, infections, hepatitis. Withdrawal symptoms after prolonged use include watery eyes, runny nose, severe back pains, stomach cramps, sleeplessness, nausea, diarrhea, sweating, and muscle spasms. Stimulants such as dexedrine, methamphetamine, diet pills, Ritalin, cocaine, caffeine. Range of effects from increased blood pressure and pulse rate, appetite loss, increased alertness, dilated and dried out bronchi, restlessness and insomnia. 2. Paranoid reaction, temporary psychosis, irritability, convulsions, palpitations, not generally true for caffeine. Development of tolerance, high. Prolonged use of large amounts can lead to psychosis, insomnia, paranoia, nervous system damage, not generally true for caffeine. Withdrawal symptoms after prolonged use include severe depression, both physical and mental, not true for caffeine. Psychedelics, such as LSD, mescaline, psilocybin, and PCP. Range of effects, from distorted perceptions, hallucinations, confusions, and vomiting, to psychosis, hallucinations, vomiting, anxiety, panic, stupor, with PCP, aggressive behavior, catatonia, convulsions, coma, high blood pressure. Development of tolerance, high. Prolonged use of large amounts can lead to psychosis, continued hallucinations, mental disruption. Withdrawal symptoms after prolonged use, occasional flashback phenomena, depression. THC, such as marijuana, hashish. Range of effects, sedation, euphoria, increased appetite, altered mental processes. 2. Distorted perception, anxiety, panic. Development of tolerance, moderate. Prolonged use of large amounts can lead to amotivation or loss of drive. Withdrawal symptoms after prolonged use, no true withdrawal symptoms except possible depression. End of Section 16, Part 3. Recording by April Walters.
Part 4 of Chapter 16 of Pilot's Handbook. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Arthur Flavel. Pilot's Handbook of Aeronautical Knowledge, Part 4 of Chapter 16, Aeromedical Factors. Altitude-Induced Decompression Sickness, DCS. Decompression sickness, DCS, describes a condition characterized by a variety of symptoms resulting from exposure to low barometric pressures that cause inert gases, mainly nitrogen, normally dissolved in body fluids and tissues, to come out of physical solution and form bubbles. Nitrogen is an inert gas normally stored throughout the human body, tissues and fluids, in physical solution. When the body is exposed to decreased barometric pressures, as in flying an unpressurized aircraft to altitude or during a rapid decompression, the nitrogen dissolved in the body comes out of solution. If the nitrogen is forced to leave the solution too rapidly, bubbles form in different areas of the body, causing a variety of signs and symptoms. The most common symptom is joint pain, which is known as the bends. Refer to Figure 16-10. What to do when altitude-induced DCS occurs. Put on oxygen mask immediately and switch the regulator to 100% oxygen. Begin an emergency descent and land as soon as possible. Even if the symptoms disappear during descent, land and seek medical evaluation while continuing to breathe oxygen. If one of the symptoms is joint pain, keep the affected area still. Do not try to work pain out by moving the joint around. Upon landing, seek medical assistance from an FAA medical officer, AME, military flight surgeon, or a hyperbaric medicine specialist. Be aware that a physician not specialized in aviation or hyperbaric medicine may not be familiar with this type of medical problem. Definitive medical treatment may involve the use of a hyperbaric chamber operated by specially trained personnel. Delayed signs and symptoms of altitude-induced DCS can occur after return to ground level, regardless of presence during flight. DCS after scuba diving. Scuba diving subjects the body to increased pressure, which allows more nitrogen to dissolve in body tissues and fluids. Refer to Figure 16-11. The reduction of atmospheric pressure that accompanies flying can produce physical problems for scuba divers. A pilot or passenger who intends to fly after scuba diving should allow the body sufficient time to rid itself of excess nitrogen absorbed during diving. If not, DCS due to evolved gas can occur during exposure to low altitude and create a serious in-flight emergency. The recommended waiting time before going to flight altitudes of up to 8,000 feet is at least 12 hours after diving that does not require controlled ascent, non-decompression stop diving, and at least 24 hours after diving that does require controlled ascent, decompression stop diving. The waiting time before going to altitudes above 8,000 feet should be at least 24 hours after any scuba dive. These recommended altitudes are actual flight altitudes above mean sea level, AMSL, and not pressurized cabin altitudes. This takes into consideration the risk of decompression of the aircraft during flight. Vision in flight. Of all the senses, vision is the most important for safe flight. Most of the things perceived while flying are visual or heavily supplemented by vision. As remarkable and vital as it is, vision is subject to limitations, such as illusions and blind spots. The more a pilot understands about the eyes and how they function, the easier it is to use vision effectively and compensate for potential problems. The eye functions much like a camera. Its structure includes an aperture, a lens, a mechanism for focusing, and a surface for registering images. Light enters through the cornea at the front of the eyeball, travels through the lens, and falls on the retina. The retina contains light-sensitive cells that convert light energy into electrical impulses that travel through nerves to the brain. The brain interprets the electrical signals to form images. There are two kinds of light-sensitive cells in the eyes: rods and cones. Refer to Figure 16-12. The cones are responsible for all color vision, from appreciating a glorious sunset to discerning the subtle shades in a fine painting. Cones are present throughout the retina, but are concentrated toward the center of the field of vision at the back of the retina. There is a small pit, called the fovea, where almost all the light-sensing cells are cones. This is the area where most looking occurs, the center of the visual field, where detail, color sensitivity, and resolution are highest. While the cones and their associated nerves are well suited to detecting fine detail and color in high light levels, the rods are better able to detect movement and provide vision in dim light. The rods are unable to discern color, but are very sensitive at low light levels. The trouble with rods is that a large amount of light overwhelms them, and they take a long time to reset and adapt to the dark again. There are so many cones in the fovea that the very center of the visual field has virtually no rods at all. So in low light, the middle of the visual field is not very sensitive. But farther from the fovea, the rods are more numerous and provide the major portion of night vision. The area where the optic nerve enters the eyeball has no rods or cones, leaving a blind spot in the field of vision. Normally, each eye compensates for the other's blind spot. Figure 16-13 provides a dramatic example of the eye's blind spot. Cover the right eye and hold this page out at arm's length. Focus the left eye on the X on the right side of the windshield and notice what happens to the airplane while slowly bringing the page closer to the eye. Empty field myopia. Empty field myopia is a condition that usually occurs when flying above the clouds or in a haze layer that provides nothing specific to focus on outside the aircraft. This causes the eyes to relax and seek a comfortable focal distance, which may range from 10 to 30 feet. For the pilot, this means looking without seeing, which is dangerous. Searching out and focusing on distant light sources, no matter how dim, helps prevent the onset of empty field myopia. Night vision. It is estimated that once fully adapted to darkness, the rods are 10,000 times more sensitive to light than the cones, making them the primary receptors for night vision. Since the cones are concentrated near the fovea, the rods are also responsible for much of the peripheral vision. The concentration of cones in the fovea can make a night blind spot in the center of the field of vision. To see an object clearly at night, the pilot must expose the rods to the image. This can be done by looking 5 degrees to 10 degrees off-center of the object to be seen. This can be tried in a dim light in a darkened room. When looking directly at the light, it dims or disappears altogether. When looking slightly off-center, it becomes clearer and brighter. Refer to Figure 16-14. When looking directly at an object, the image is focused mainly on the fovea, where detail is best seen. At night, the ability to see an object in the center of the visual field is reduced as the cones lose much of their sensitivity and the rods become more sensitive. Looking off-center can help compensate for this night blind spot. Along with the loss of sharpness, acuity, and color at night, depth perception and judgment of size may be lost. While the cones adapt rapidly to changes in light intensities, the rods take much longer. Walking from bright sunlight into a dark movie theater is an example of this dark adaptation period experience. The rods can take approximately 30 minutes to fully adapt to darkness. A bright light, however, can completely destroy night adaptation, leaving night vision severely compromised while the adaptation process is repeated. Hypoxia also affects vision. Sharp, clear vision, with the best being equal to 20/20 vision, requires significant oxygen, especially at night. As altitude increases, the available oxygen decreases, degrading night vision. Compounding the problem is fatigue, which minimizes physiological well-being. Adding fatigue to high-altitude exposure is a recipe for disaster. In fact, if flying at night at an altitude of 12,000 feet, the pilot may actually see elements of his or her normal vision missing or not in focus. Missing visual elements resemble the missing pixels in a digital image, while unfocused vision is dim and washed out. For the pilot suffering the effects of hypoxic hypoxia, a simple descent to a lower altitude may not be sufficient to reestablish vision. For example, a climb from 8,000 feet to 12,000 feet for 30 minutes does not mean a descent to 8,000 feet will rectify the problem. Visual acuity may not be regained for over an hour. Thus, it is important to remember, altitude and fatigue have a profound effect on a pilot's ability to see. Several things can be done to keep the eyes adapted to darkness. The first is obvious. Avoid bright lights before and during flight. For 30 minutes before a night flight, avoid any bright light sources, such as headlights, landing lights, strobe lights, or flashlights. If a bright light is encountered, close one eye to keep it light sensitive. This allows the use of that eye to see again when the light is gone. Red flight deck lighting also helps preserve night vision, but red light severely distorts some colors and completely washes out the color red. This makes reading an aeronautical chart difficult. A dim white light or a carefully directed flashlight can enhance night reading ability. While flying at night, keep the instrument panel and interior lights turned up no higher than necessary. This helps to see outside references more easily. If the eyes become blurry, blinking more frequently often helps. Diet and general physical health have an impact on how well a pilot can see in the dark. Deficiencies in vitamins A and C have been shown to reduce night acuity, Other factors, such as carbon monoxide poisoning, smoking, alcohol, certain drugs, and a lack of oxygen, can also greatly decrease night vision. Night vision illusions. There are many different types of visual illusions that commonly occur at night. Anticipating and staying aware of them is usually the best way to avoid them. Autokinesis. Autokinesis is caused by staring at a single point of light against a dark background for more than a few seconds. After a few moments, the light appears to move on its own. To prevent this illusion, focus the eyes on objects at varying distances and avoid fixating on one target. Be sure to maintain a normal scan pattern. False horizon. A false horizon can occur when the natural horizon is obscured or not readily apparent. It can be generated by confusing bright stars and city lights. It can also occur while flying toward the shore of an ocean or a large lake. Because of the relative darkness of the water, the lights along the shoreline can be mistaken for stars in the sky. Refer to Figure 16-15. Night landing illusions. Landing illusions occur in many forms. Above featureless terrain at night, there is a natural tendency to fly a lower-than-normal approach. Elements that cause any type of visual obscurities, such as rain, haze, or a dark runway environment, can also cause low approaches. Bright lights, steep surrounding terrain, and a wide runway can produce the illusion of being too low, with a tendency to fly a higher-than-normal approach. A set of regularly spaced lights along a road or highway can appear to be runway lights. Pilots have even mistaken the lights on moving trains as runway or approach lights. Bright runway or approach lighting systems can create the illusion that the airplane is closer to the runway, especially where few lights illuminate the surrounding terrain. Pilots who are flying at night should strongly consider oxygen supplementation at altitudes and times not required by the FAA, especially at night when critical judgment and hand-eye coordination is necessary, for example IFR, or if a smoker or not perfectly healthy. Chapter Summary. This chapter provides an introduction to aeromedical factors relating to flight activities. More detailed information on the subjects discussed in this chapter is available in the Aeronautical Information Manual, AIM, and online at www.faa.gov/pilots/safety/pilot safety brochures. End of Part 4 of Chapter 16. Part 1 of Chapter 17 of Pilot's Handbook. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Arthur Flavel. Pilot's Handbook of Aeronautical Knowledge by the FAA, Part 1 of Chapter 17, Aeronautical Decision-Making. Introduction. Aeronautical decision-making, ADM, is decision-making in a unique environment, aviation. It is a systematic approach to the mental process used by pilots to consistently determine the best course of action in response to a given set of circumstances. It is what a pilot intends to do based on the latest information he or she has. The importance of learning and understanding effective ADM skills cannot be overemphasized. While progress is continually being made in the advancement of pilot training methods, aircraft equipment and systems, and services for pilots, accidents still occur. Despite all the changes in technology to improve flight safety, one factor remains the same: the human factor, which leads to errors. It is estimated that approximately 80% of all aviation accidents are related to human factors, and the vast majority of these accidents occur during landing, 24.1%, and takeoff, 23.4%. Refer to Figure 17-1. ADM is a systematic approach to risk assessment and stress management. To understand ADM is to also understand how personal attitudes can influence decision-making and how those attitudes can be modified to enhance safety in the flight deck. It is important to understand the factors that cause humans to make decisions and how the decision-making process not only works, but can be improved. This chapter focuses on helping the pilot improve his or her ADM skills with the goal of mitigating the risk factors associated with flight. Advisory Circular AC 60-22, Aeronautical Decision Making, provides background references, definitions, and other pertinent information about ADM training in the general aviation GA environment. Refer to Figure 17-2. History of ADM. For over 25 years, the importance of good pilot judgment, or aeronautical decision-making, ADM, has been recognized as critical to the safe operation of aircraft, as well as accident avoidance. The airline industry, motivated by the need to reduce accidents caused by human factors, developed the first training programs based on improving ADM. Crew Resource Management, CRM, training for flight crews is focused on the effective use of all available resources, human resources, hardware, and information supporting ADM to facilitate crew cooperation and improve decision-making. The goal of all flight crews is good ADM, and the use of CRM is one way to make good decisions. Research in this area prompted the Federal Aviation Administration, FAA, to produce training directed at improving the decision-making of pilots and led to current FAA regulations that require that decision-making be taught as part of the pilot training curriculum. ADM research, development, and testing culminated in 1987 with the publication of 6 manuals oriented to the decision-making needs of variously rated pilots. These manuals provided multifaceted materials designed to reduce the number of decision-related accidents. The effectiveness of these materials was validated in independent studies where student pilots received such training in conjunction with the standard flying curriculum. When tested, the pilots who had received ADM training made fewer in-flight errors than those who had not received ADM training. The differences were statistically significant and ranged from about 10 to 50% fewer judgment errors. In the operational environment, an operator flying about 400,000 hours annually demonstrated a 54% reduction in accident rate after using these materials for recurrency training. Contrary to popular opinion, good judgment can be taught. Tradition held that good judgment was a natural byproduct of experience, but as pilots continued to log accident-free flight hours, a corresponding increase of good judgment was assumed. Building upon the foundation of conventional decision-making, ADM enhances the process to decrease the probability of human error and increase the probability of a safe flight. ADM provides a structured, systematic approach to analyzing changes that occur during a flight and how these changes might affect a flight's safe outcome. The ADM process addresses all aspects of decision-making in the flight deck and identifies the steps involved in good decision-making. Steps for good decision-making are 1. Identifying personal attitudes hazardous to safe flight. 2. Learning behavior modification techniques. 3. Learning how to recognize and cope with stress. 4. Developing risk assessment skills. 5. Using all resources. And 6. Evaluating the effectiveness of one's ADM skills. Risk management is an important component of ADM. When a pilot follows good decision-making practices, the inherent risk in a flight is reduced or even eliminated. The ability to make good decisions is based upon direct or indirect experience and education. Consider automotive seatbelt use. In just 2 decades, seatbelt use has become the norm, placing those who do not wear seatbelts outside the norm. But this group may learn to wear a seatbelt by either direct or indirect experience. For example, a driver learns through direct experience about the value of wearing a seatbelt when he or she is involved in a car accident that leads to a personal injury. An indirect learning experience occurs when a loved one is injured during a car accident because he or she failed to wear a seatbelt. While poor decision-making in everyday life does not always lead to tragedy, the margin for error in aviation is thin. Since ADM enhances management of an aeronautical environment, all pilots should become familiar with and employ ADM. Crew Resource Management, CRM, and Single Pilot Resource Management. While CRM focuses on pilots operating in crew environments, many of the concepts apply to single pilot operations. Many CRM principles have been successfully applied to single pilot aircraft and led to the development of Single Pilot Resource Management, SRM. SRM is defined as the art and science of managing all the resources, both on board the aircraft and from outside sources, available to a single pilot, prior and during flight, to ensure the successful outcome of the flight. SRM includes the concepts of ADM, Risk Management, RM, Task Management, TM, Automation Management, AM, Controlled Flight into Terrain, CFIT, awareness, and Situational Awareness, SA. SRM training helps the pilot maintain situational awareness by managing the automation and associated aircraft control and navigation tasks. This enables the pilot to accurately assess and manage risk and make accurate and timely decisions. SRM is all about helping pilots learn how to gather information, analyze it, and make decisions. Although the flight is coordinated by a single person and not an onboard flight crew, the use of available resources such as air traffic control, ATC, and flight service station, FSS, replicates the principles of CRM. Hazard and risk. Two defining elements of ADM are hazard and risk. Hazard is a real or perceived condition, event, or circumstance that a pilot encounters. When faced with a hazard, the pilot makes an assessment of that hazard based upon various factors. The pilot assigns a value to the potential impact of the hazard, which qualifies the pilot's assessment of the hazard, risk. Therefore, risk is an assessment of the single or cumulative hazard facing a pilot. However, different pilots see hazards differently. For example, the pilot arrives to pre-flight and discovers a small, blunt-type nick in the leading edge at the middle of the aircraft's prop. Since the aircraft is parked on the tarmac, the nick was probably caused by another aircraft's prop wash blowing some type of debris into the propeller. The nick is the hazard, a present condition. The risk is prop fracture if the engine is operated with damage to a prop blade. The seasoned pilot may see the nick as a low risk. He realizes this type of nick diffuses stress over a large area, is located in the strongest portion of the propeller, and based on experience he doesn't expect it to propagate a crack, which can lead to high-risk problems. He does not cancel his flight. The inexperienced pilot may see the nick as a high-risk factor because he is unsure of the effect the nick will have on the prop's operation, and he has been told that damage to a prop could cause a catastrophic failure. This assessment leads him to cancel his flight. Therefore, elements or factors affecting individuals are different and profoundly impact decision-making. These are called human factors and can transcend education, experience, health, physiological aspects, etc. Another example of risk assessment was the flight of a Beechcraft King Air equipped with de-icing and anti-icing. The pilot deliberately flew into moderate to severe icing conditions while ducking under cloud cover. A prudent pilot would assess the risk as high and beyond the capabilities of the aircraft. Yet this pilot did the opposite. Why did the pilot take this action? Past experience prompted the action. The pilot had successfully flown into these conditions repeatedly, although the icing conditions were previously forecast 2,000 feet above the surface. This time the conditions were forecast from the surface. Since the pilot was in a hurry and failed to factor in the difference between the forecast altitudes, he assigned a low risk to the hazard and took a chance. He and the passengers died from a poor risk assessment of the situation. Hazardous attitudes and antidotes. Being fit to fly depends on more than just a pilot's physical condition and recent experience. For example, attitude will affect the quality of decisions. Attitude is a motivational predisposition to respond to people, situations, or events in a given manner. Studies have identified 5 hazardous attitudes that can interfere with the ability to make sound decisions and exercise authority properly: anti-authority, impulsivity, invulnerability, macho, and resignation. Refer to Figure 17-3. Hazardous attitudes contribute to poor pilot judgment, but can be effectively counteracted by redirecting the hazardous attitude so the correct action can be taken. Recognition of hazardous thoughts is the first step toward neutralizing them. After recognizing a thought as hazardous, the pilot should label it as hazardous, then state the corresponding antidote. Antidotes should be memorized for each of the hazardous attitudes so they automatically come to mind when needed. Risk. During each flight, the single pilot makes many decisions under hazardous conditions. To fly safely, the pilot needs to assess the degree of risk and determine the best course of action to mitigate risk. Assessing risk. For the single pilot, assessing risk is not as simple as it sounds. For example, the pilot acts as his or her own quality control in making decisions. If a fatigued pilot who has flown 16 hours is asked if he or she is too tired to continue flying, the answer may be no. Most pilots are goal-oriented, and when asked to accept a flight, there is a tendency to deny personal limitations while adding weight to issues not germane to the mission. For example, pilots of helicopter emergency services, EMS, have been known, more than other groups, to make flight decisions that add significant weight to the patient's welfare. These pilots add weight to intangible factors, the patient in this case, and fail to appropriately quantify actual hazards such as fatigue or weather when making flight decisions. The single pilot who has no other crew member for consultation must wrestle with the intangible factors that draw one into a hazardous position. Therefore, he or she has a greater vulnerability than a full crew. Examining National Transportation Safety Board (NTSB) reports and other accident research can help a pilot learn to assess risk more effectively. For example, the accident rate during night VFR decreases by nearly 50% once a pilot obtains 100 hours, and continues to decrease until the 1,000-hour level. The data suggests that for the first 500 hours, pilots flying VFR at night might want to establish higher personal limitations than are required by the regulations, and, if applicable, apply instrument flying skills in this environment. Several risk assessment models are available to assist in the process of assessing risk. The models, all taking slightly different approaches, seek a common goal of assessing risk in an objective manner. 2 are illustrated below. The most basic tool is the risk matrix. Refer to Figure 17-4. It assesses 2 items: the likelihood of an event occurring and the consequence of that event. Likelihood of an event. Likelihood is nothing more than taking a situation and determining the probability of its occurrence. It is rated as probable, occasional, remote, or improbable. For example, a pilot is flying from point A to point B, 50 miles, in marginal visual flight rules and VFR conditions. The likelihood of encountering potential instrument meteorological conditions, IMC, is the first question the pilot needs to answer. The experiences of other pilots coupled with the forecast might cause the pilot to assign occasional to determine the probability of encountering IMC. The following are guidelines for making assignments. Probable. An event will occur several times. Occasional. An event will probably occur sometime. Remote. An event is unlikely to occur, but is possible. Improbable. an event is highly unlikely to occur. Severity of an event. The next element is the severity or consequence of a pilot's action or actions. It can relate to injury and/or damage. If the individual in the example above is not an Instrument Flight Rules IFR pilot, what are the consequences of him or her encountering inadvertent IMC conditions? In this case, because the pilot is not IFR rated, the consequences are catastrophic. The following are guidelines for this assignment. Catastrophic. Results in fatalities, total loss. Critical. Severe injury, major damage. Marginal. Minor injury, minor damage. Negligible. Less than minor injury, less than minor system damage. Simply connecting the two factors, as shown in Figure 17-4, indicates the risk is high and the pilot must either not fly or fly only after finding ways to mitigate, eliminate, or control the risk. Although the matrix in Figure 17-4 provides a general viewpoint of a generic situation, a more comprehensive program can be made that is tailored to a pilot's flying. Refer to Figure 17-5. This program includes a wide array of aviation-related activities specific to the pilot and assesses health, fatigue, weather, capabilities, etc. The scores are added, and the overall score falls into various ranges, with the range representative of actions that a pilot imposes upon himself or herself. Mitigating risk. Risk assessment is only part of the equation. After determining the level of risk, the pilot needs to mitigate the risk. For example, the pilot flying from point A to point B, 50 miles, in MVFR conditions, has several ways to reduce risk. Wait for the weather to improve to good visual flight rules VFR conditions. Take a pilot who is certified as an IFR pilot. Delay the flight. Cancel the flight. Drive. One of the best ways single pilots can mitigate the risk is to use the I Am Safe checklist to determine physical and mental readiness for flying. Illness. Am I sick? Illness is an obvious pilot risk. Medication. Am I taking any medicines that might affect my judgment or make me drowsy? Stress. Am I under psychological pressure from the job? Do I have money, health, or family problems? Stress causes concentration and performance problems. While the regulations list medical conditions that require grounding, stress is not among them. The pilot should consider the effects of stress on performance. Alcohol. Have I been drinking within 8 hours? Within 24 hours? As little as 1 ounce of liquor, 1 bottle of beer, or 4 ounces of wine can impair flying skills. Alcohol also renders a pilot more susceptible to disorientation and hypoxia. Fatigue. Am I tired and not adequately rested? Fatigue continues to be one of the most insidious hazards to flight safety, as it may not be apparent to a pilot until serious errors are made. Emotion. Am I emotionally upset? End of Part 1 of Chapter 17. Part 2 of Chapter 17 of Pilot's Handbook. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Arthur Flavel. Pilot's Handbook of Aeronautical Knowledge by the FAA. Part 2 of Chapter 17, Aeronautical Decision Making. The PAVE Checklist. Another way to mitigate risk is to perceive hazards. By incorporating the PAVE checklist into pre-flight planning, the pilot divides the risks of flight into 4 categories. Pilot in command, PIC, aircraft, environment, and external pressures, PAVE, which form part of a pilot's decision-making process. With the PAVE checklist, pilots have a simple way to remember each category to examine for risk prior to each flight. Once a pilot identifies the risks of a flight, he or she needs to decide whether the risk or combination of risks can be managed safely and successfully. If not, make the decision to cancel the flight. If the pilot decides to continue with the flight, he or she should develop strategies to mitigate the risks. One way a pilot can control the risks is to set personal minimums for items in each risk category. These are limits unique to that individual pilot's current level of experience and proficiency. For example, the aircraft may have a maximum crosswind component of 15 knots listed in the Aircraft Flight Manual, AFM, and the pilot has experience with 10 knots of direct crosswind. It could be unsafe to exceed a 10-knot crosswind component without additional training. Therefore, the 10 knots crosswind experience level is that pilot's personal limitation until additional training with a certificated flight instructor, CFI, provides the pilot with additional experience for flying in crosswinds that exceed 10 knots. One of the most important concepts that safe pilots understand is the difference between what is legal in terms of the regulations and what is smart or safe in terms of pilot experience and proficiency. P equals pilot in command, PIC. The pilot is one of the risk factors in a flight. The pilot must ask, am I ready for this trip, in terms of experience, recency, currency, physical, and emotional condition? The I Am Safe checklist provides the answers. A equals aircraft. What limitations will the aircraft impose upon the trip? Ask the following questions. Is this the right aircraft for the flight? Am I familiar with and current in this aircraft? Aircraft performance figures in the AFM are based on a brand new aircraft flown by a professional test pilot. Keep that in mind while assessing personal and aircraft performance. Is this aircraft equipped for the flight? Instruments, lights, navigation, and communications equipment adequate? Can this aircraft use the runways available for the trip with an adequate margin of safety under the conditions to be flown? Can this aircraft carry the planned load? Can this aircraft operate at the altitudes needed for the trip? Does this aircraft have sufficient fuel capacity, with reserves, for trip legs planned? Does the fuel quantity delivered match the fuel quantity ordered? V equals environment. Weather. Weather is a major environmental consideration. Earlier, it was suggested pilots set their own personal minimums, especially when it comes to weather. As pilots evaluate the weather for a particular flight, they should consider the following. What are the current ceiling and visibility? In mountainous terrain, consider having higher minimums for ceiling and visibility, particularly if the terrain is unfamiliar. Consider the possibility that the weather may be different than forecast. Have alternative plans and be ready and willing to divert should an unexpected change occur. Consider the winds at the airports being used and the strength of the crosswind component. If flying in mountainous terrain, consider whether there are strong winds aloft. Strong winds in mountainous terrain can cause severe turbulence and downdrafts and be very hazardous for aircraft even when there is no other significant weather. Are there any thunderstorms present or forecast? If there are clouds, is there any icing, current, or forecast? What is the temperature dew point spread and the current temperature at altitude? Can descent be made safely all along the route? If icing conditions are encountered, is the pilot experienced at operating the aircraft's de-icing or anti-icing equipment? Is this equipment in good condition and functional? For what icing conditions is the aircraft rated, if any? Terrain. Evaluation of terrain is another important component of analyzing the flight environment. To avoid terrain and obstacles, especially at night or in low visibility, determine safe altitudes in advance by using the altitude shown on VFR and IFR charts during pre-flight planning. Use maximum elevation figures, MEFs, and other easily obtainable data to minimize chances of an in-flight collision with terrain or obstacles. Airport. What lights are available at the destination and alternate airports? VASI or PAPI or ILS glide slope guidance? Is the terminal airport equipped with them? Are they working? Will the pilot need to use the radio to activate the airport lights? Check the notices to airmen, NOTAMs, for closed runways or airports. Look for runway or beacon lights out, nearby towers, etc. Choose the flight route wisely. An engine failure gives the nearby airports supreme importance. Are there shorter or obstructed fields at the destination and/or alternate airports? Airspace. If the trip is over remote areas, are appropriate clothing, water, and survival gear on board in the event of a forced landing? If the trip includes flying over water or unpopulated areas with a chance of losing visual reference to the horizon, the pilot must be prepared to fly IFR. Check the airspace and any temporary flight restriction, TFRs, along the route of flight. Nighttime. Night flying requires special consideration. If the trip includes flying at night over water or unpopulated areas with a chance of losing visual reference to the horizon, the pilot must be prepared to fly IFR. Will the flight conditions allow a safe emergency landing at night? Pre-flight all aircraft lights, interior and exterior, for a night flight. Carry at least 2 flashlights, one for exterior pre-flight and a smaller one that can be dimmed and kept nearby. E equals external pressures. External pressures are influences external to the flight that create a sense of pressure to complete a flight, often at the expense of safety. Factors that can be external pressures include the following: someone waiting at the airport for the flight's arrival, a passenger the pilot does not want to disappoint, the desire to demonstrate pilot qualifications, the desire to impress someone. Probably the 2 most dangerous words in aviation are, "Watch this." The desire to satisfy a specific personal goal, get home-itis, get there-itis, and let's go-itis. The pilot's general goal completion orientation. Emotional pressure associated with acknowledging that skill and experience levels may be lower than a pilot would like them to be. Pride can be a powerful external factor. Managing external pressures. Management of external pressure is the single most important key to risk management because it is the one risk factor category that can cause a pilot to ignore all the other risk factors. External pressures put time-related pressure on the pilot and figure into a majority of accidents. The use of Personal Standard Operating Procedures, SOPs, is one way to manage external pressures. The goal is to supply a release for the external pressures of a flight. These procedures include, but are not limited to, allow time on a trip for an extra fuel stop, or to make an unexpected landing because of weather. Have alternate plans for a late arrival, or make backup airline reservations for must-be-there trips. For really important trips, plan to leave early enough so that there would still be time to drive to the destination. Advise those who are waiting at the destination that the arrival may be delayed. Know how to notify them when delays are encountered. Manage passengers' expectations. Make sure passengers know that they might not arrive on a firm schedule, and if they must arrive by a certain time, they should make alternative plans. Eliminate pressure to return home, even on a casual day flight, by carrying a small overnight kit containing prescriptions, contact lens solutions, toiletries, or other necessities on every flight. The key to managing external pressure is to be ready for and accept delays. Remember that people get delayed when traveling on airlines, driving a car, or taking a bus. The pilot's goal is to manage risk, not create hazards. Refer to Figure 17-6. Human behavior. Studies of human behavior have tried to determine an individual's predisposition to taking risks and the level of an individual's involvement in accidents. In 1951, a study regarding injury-prone children was published by Elizabeth Mecham Fuller and Helen B. Bond of the University of Minnesota. The study was comprised of two separate groups of second-grade students. 55 students were considered accident repeaters and 48 students had no accidents. Both groups were from the same school of 600, and their family demographics were similar. The accident-free group showed a superior knowledge of safety, were considered industrious and cooperative with others, but were not considered physically inclined. The accident repeater group had better gymnastic skills, were considered aggressive and impulsive, demonstrated rebellious behavior when under stress, were poor losers, and liked to be the center of attention. One interpretation of this data, an adult predisposition to injury stems from childhood behavior and environment, leads to the conclusion that any pilot group should be comprised only of pilots who are safety-conscious, industrious, and cooperative. Clearly, this is not only an inaccurate inference, it is impossible. Pilots are drawn from the general population and exhibit all types of personality traits. Thus, it is important that good decision-making skills be taught to all pilots. Historically, the term pilot error has been used to describe an accident in which an action or decision made by the pilot was the cause or a contributing factor that led to the accident. This definition also includes the pilot's failure to make a correct decision or take proper action. From a broader perspective, the phrase human factors related more aptly describes these accidents. A single decision or event does not lead to an accident, but a series of events and the resultant decisions together form a chain of events leading to an outcome. In his article, Accident-Prone Pilots, Dr. Patrick R. Valetti uses the history of Captain Everyman to demonstrate how aircraft accidents are caused more by a chain of poor choices rather than one single poor choice. In the case of Captain Everyman, after a gear-up landing accident, he became involved in another accident while taxiing a Beech 58P Baron out of the ramp. Interrupted by a radio call from the dispatcher, Everyman neglected to complete the fuel crossfeed check before taking off. Everyman, who was flying solo, left the right fuel selector in the crossfeed position. Once aloft and cruising, he noticed a right roll tendency and corrected with aileron trim. He did not realize that both engines were feeding off the left wing's tank, making the wing lighter. After 2 hours of flight, the right engine quit when Everyman was flying along a deep canyon gorge. While he was trying to troubleshoot the cause of the right engine's failure, the left engine quit. Everyman landed the aircraft on a river sandbar, but it sank into 10 feet of water. Several years later, Everyman flew a de Havilland Twin Otter to deliver supplies to a remote location. When he returned to home base and landed, the aircraft veered sharply to the left, departed the runway, and ran into a marsh 375 feet from the runway. The airframe and engines sustained considerable damage. Upon inspecting the wreck, accident investigators found the nose wheel steering tiller in the fully deflected position. Both the after takeoff and before landing checklists required the tiller to be placed in the neutral position. Everyman had overlooked this item. Now, is Everyman accident-prone or just unlucky? Skipping details on a checklist appears to be a common theme in the preceding accidents. While most pilots have made similar mistakes, these errors were probably caught prior to a mishap due to extra margin, good warning systems, a sharp co-pilot, or just good luck. What makes a pilot less prone to accidents? The successful pilot possesses the ability to concentrate, manage workloads, monitor, and perform several simultaneous tasks. Some of the latest psychological screenings used in aviation test applicants for their ability to multitask, measuring both accuracy as well as the individual's ability to focus attention on several subjects simultaneously. The FAA oversaw an extensive research study on the similarities and dissimilarities of accident-free pilots and those who were not. The project surveyed over 4,000 pilots, half of whom had clean records, while the other half had been involved in an accident. 5 traits were discovered in pilots prone to having accidents. These pilots have disdain toward rules, have very high correlation between accidents on their flying records and safety violations on their driving records, frequently fall into the thrill and adventure-seeking personality category, are impulsive rather than methodical and disciplined, both in their information gathering and in the speed and selection of actions to be taken. A disregard for and underutilization of outside sources of information, including co-pilots, flight attendants, flight service personnel, flight instructors, and air traffic controllers. End of Part 2 of Chapter 17. Part 3 of Chapter 17 of Pilot's Handbook. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Arthur Flavel. Pilot's Handbook of Aeronautical Knowledge by the FAA. Part 3 of Chapter 17, Aeronautical Decision-Making. The Decision-Making Process. An understanding of the decision-making process provides the pilot with a foundation for developing ADM and SRM skills. While some situations, such as engine failure, require an immediate pilot response using established procedures, there is usually time during a flight to analyze any changes that occur, gather information, and assess risk before reaching a decision. Risk management and risk intervention is much more than the simple definitions of the term might suggest. Risk management and risk intervention are decision-making processes designed to systematically identify hazards, assess the degree of risk, and determine the best course of action. These processes involve the identification of hazards, followed by assessments of the risks, analysis of the controls, making control decisions, using the controls, and monitoring the results. The steps leading to this decision constitute a decision-making process. 3 models of a structured framework for problem-solving and decision-making are the 5P, the 3P, the 3 with care and team, the OODA, and DECIDE models. They provide assistance in organizing the decision process. All these models have been identified as helpful to the single pilot in organizing critical decisions. SRM and the 5P check. SRM is about how to gather information, analyze it, and make decisions. Learning how to identify problems, analyze the information, and make informed and timely decisions is not as straightforward as the training involved in learning specific maneuvers. Learning how to judge a situation and how to think in the endless variety of situations encountered while flying out in the real world is more difficult. There is no one right answer in ADM. Rather, each pilot is expected to analyze each situation in light of experience level, personal minimums, and current physical and mental readiness level, and make his or her own decision. SRM sounds good on paper, but it requires a way for pilots to understand and use it in their daily flights. One practical application is called the 5 Ps. Refer to Figure 17-7. The 5 Ps consist of the plan, the plane, the pilot, the passengers, and the programming. Each of these areas consists of a set of challenges and opportunities that face a single pilot, and each can substantially increase or decrease the risk of successfully completing the flight based on the pilot's ability to make informed and timely decisions. The 5 Ps are used to evaluate the pilot's current situation at key decision points during the flight, or when an emergency arises. These decision points include pre-flight, pre-takeoff, hourly or at the midpoint of the flight, pre-descent, and just prior to the final approach fix, or for visual flight rules, VFR, operations, just prior to entering the traffic pattern. The 5 Ps are based on the idea that pilots have essentially 5 variables that impact his or her environment and that can cause the pilot to make a single critical decision or several less critical decisions that when added together can create a critical outcome. These variables are the plan, the plane, the pilot, the passengers, and the programming. This concept stems from the belief that current decision-making models tended to be reactionary in nature. A change has to occur and be detected to drive a risk management decision by the pilot. For instance, many pilots use risk management sheets that are filled out by the pilot prior to takeoff. These form a catalog of risks that may be encountered that day and turn them into numerical values. If the total exceeds a certain level, the flight is altered or canceled. Informal research shows that while these are useful documents for teaching risk factors, they are almost never used outside of formal training programs. The 5P concept is an attempt to take the information contained in those sheets and in other available models and use it. The 5P concept relies on the pilot to adopt a scheduled review of the critical variables at points in the flight where decisions are most likely to be effective. For instance, the easiest point to cancel a flight due to bad weather is before the pilot and passengers walk out the door and load the aircraft. So, the first decision point is pre-flight in the flight planning room, where all the information is readily available to make a sound decision, and where communication and fixed base operator (FBO) services are readily available to make alternate travel plans. The second easiest point in the flight to make a critical safety decision is just prior to takeoff. Few pilots have ever had to make an emergency takeoff. While the point of the 5P check is to help the pilot fly, the correct application of the 5P before takeoff is to assist in making a reasoned go, no-go decision based on all the information available. That decision will usually be to go, with certain restrictions and changes, but may also be a no-go. The key point is that these 2 points in the process of flying are critical go-no-go points on each and every flight. The third place to review the 5Ps is at the midpoint of the flight. Often, pilots may wait until the Automated Terminal Information Service, ATIS, is in range to check weather. Yet at this point in the flight, many good options have already passed behind the aircraft and pilot. Additionally, fatigue and low-altitude hypoxia serve to rob the pilot of much of his or her energy by the end of a long and tiring flight day. This leads to a transition from a decision-making mode to an acceptance mode on the part of the pilot. If the flight is longer than 2 hours, the 5P check should be conducted hourly. The last 2 decision points are just prior to descent into the terminal area and just prior to the final approach fix, or if VFR just prior to entering the traffic pattern as preparations for landing commence. Most pilots execute approaches with the expectation that they will land out of the approach every time. A healthier approach requires the pilot to assume that changing conditions, the 5Ps again, will cause the pilot to divert or execute the missed approach on every approach. This keeps the pilot alert to all manner of conditions that may increase risk and threaten the safe conduct of the flight. Diverting from cruise altitude saves fuel, allows unhurried use of the autopilot, and is less reactive in nature. Diverting from the final approach fix, while more difficult, still allows the pilot to plan and coordinate better rather than executing a futile missed approach. Let's look at a detailed discussion of each of the 5Ps. The plan. The plan can also be called the mission or the task. It contains the basic elements of cross-country planning, weather, route, fuel, publications, currency, etc. The plan should be reviewed and updated several times during the course of the flight. A delayed takeoff due to maintenance, fast-moving weather, and a short-notice TFR may all radically alter the plan. The plan is not only about the flight plan, but also all the events that surround the flight and allow the pilot to accomplish the mission. The plan is always being updated and modified and is especially responsive to changes in the other 4 remaining Ps. If for no other reason, the 5P check reminds the pilot that the day's flight plan is real life and subject to change at any time. Obviously, weather is a huge part of any plan. The addition of data link weather information gives the advanced avionics pilot a real advantage in inclement weather, but only if the pilot is trained to retrieve and evaluate the weather in real time without sacrificing situational awareness. And of course, weather information should drive a decision even if that decision is to continue on the current plan. Pilots of aircraft without data link weather should get updated weather in flight through a flight service station, FSS, and or Flight Watch. The plane. Both the plan and the plane are fairly familiar to most pilots. The plane consists of the usual array of mechanical and cosmetic issues that every aircraft pilot, owner, or operator can identify. With the advent of advanced avionics, the plane has expanded to include database currency, automation status, and emergency backup systems that were unknown a few years ago. Much has been written about single-pilot IFR flight, both with and without an autopilot. While this is a personal decision, it is just that, a decision. Low IFR in a non-autopilot-equipped aircraft may depend on several of the other P's to be discussed. Pilot proficiency, currency, and fatigue are among them. The pilot. Flying, especially when used for business transportation, can expose the pilot to high-altitude flying, long distance and endurance, and more challenging weather. An advanced avionics aircraft, simply due to their advanced capabilities, can expose a pilot to even more of these stresses. The traditional I Am Safe checklist, see page 17-6, is a good start. The combination of late night, pilot fatigue, and the effects of sustained flight above 5,000 feet may cause pilots to become less discerning, less critical of information, less decisive, and more compliant and accepting. Just as the most critical portion of the flight approaches, for instance, a night instrument approach in the weather after a 4-hour flight, the pilot's guard is down the most. The 5P process helps a pilot recognize the physiological situation at the end of the flight before takeoff, and continues to update personal conditions as the flight progresses. Once risks are identified, the pilot is in an infinitely better place to make alternate plans that lessen the effect of these factors and provide a safer solution. The passengers. One of the key differences between CRM and SRM is the way passengers interact with the pilot. The pilot of a highly capable single-engine aircraft has entered into a very personal relationship with the passengers. In fact, the pilot and passengers sit within an arm's reach all of the time. The desire of the passengers to make airline connections or important business meetings easily enters into this pilot's decision-making loop. Done in a healthy and open way, this can be a positive factor. Consider a flight to Dulles Airport, and the passengers, both close friends and business partners, need to get to Washington, D.C. for an important meeting. The weather is VFR all the way to Southern Virginia, then turns to low IFR as the pilot approaches Dulles. A pilot employing the 5P approach might consider reserving a rental car at an airport in northern North Carolina or Southern Virginia to coincide with a refueling stop. Thus, the passengers have a way to get to Washington, and the pilot has an out to avoid being pressured into continuing the flight if the conditions do not improve. Passengers can also be pilots. If no one is designated as pilot in command, PIC, and unplanned circumstances arise, the decision-making styles of several self-confident pilots may come into conflict. Pilots also need to understand that non-pilots may not understand the level of risk involved in the flight. There is an element of risk in every flight. That is why SRM calls it risk management, not risk elimination. While a pilot may feel comfortable with the risk present in a night IFR flight, the passengers may not. A pilot employing SRM should ensure the passengers are involved in the decision-making and given tasks and duties to keep them busy and involved. If, upon factual description of the risks present, the passengers decide to buy an airline ticket or rent a car, then a good decision has generally been made. This discussion also allows the pilot to move past what he or she thinks the passengers want to do and find out what they actually want to do. This removes self-induced pressure from the pilot. The programming. The advanced avionics aircraft adds an entirely new dimension to the way general aviation aircraft are flown. The electronic instrument displays, GPS, and autopilot reduce pilot workload and increase pilot situational awareness. While programming and operation of these devices are fairly simple and straightforward, unlike the analog instruments they replace, they tend to capture the pilot's attention and hold it for long periods of time. To avoid this phenomenon, the pilot should plan in advance when and where the programming for approaches, route changes, and airport information gathering should be accomplished, as well as times it should not. Pilot familiarity with the equipment, the route, the local air traffic control environment, and personal capabilities vis-a-vis the automation should drive when, where, and how the automation is programmed and used. The pilot should also consider what his or her capabilities are in response to last-minute changes of the approach and the reprogramming required, and ability to make large-scale changes, a reroute for instance, while hand-flying the aircraft. Since formats are not standardized, simply moving from one manufacturer's equipment to another should give the pilot pause and require more conservative planning and decisions. The SRM process is simple. At least 5 times before and during the flight, the pilot should review and consider the plan, the plane, the pilot, the passengers, and the programming, and make the appropriate decision required by the current situation. It is often said that failure to make a decision is a decision. Under SRM and the 5 Ps, even the decision to make no changes to the current plan is made through a careful consideration of all the risk factors present. End of Part 3 of Chapter 17. Part 4 of Chapter 17 of Pilot's Handbook. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Arthur Flavel. Pilot's Handbook of Aeronautical Knowledge by the FAA, Part 4 of Chapter 17, Aeronautical Decision-Making. Perceive, Process, Perform, 3P. The Perceive, Process, Perform 3P model for ADM offers a simple, practical, and systematic approach that can be used during all phases of flight. To use it, the pilot will perceive the given set of circumstances for a flight, process by evaluating their impact on flight safety, perform by implementing the best course of action. In the first step, the goal is to develop situational awareness by perceiving hazards, which are present events, objects, or circumstances that could contribute to an undesired future event. In this step, the pilot will systematically identify and list hazards associated with all aspects of the flight: pilot, aircraft, environment, and external pressures. It is important to consider how individual hazards might combine. Consider, for example, the hazard that arises when a new instrument pilot with no experience in actual instrument conditions wants to make a cross-country flight to an airport with low ceilings in order to attend an important business meeting. In the second step, the goal is to process this information to determine whether the identified hazards constitute risk, which is defined as the future impact of a hazard that is not controlled or eliminated. The degree of risk posed by a given hazard can be measured in terms of exposure, number of people or resources affected, severity, extent of possible loss, and probability, the likelihood that a hazard will cause a loss. If the hazard is low ceilings, for example, the level of risk depends on a number of other factors such as pilot training and experience, aircraft equipment and fuel capacity, and others. In the third step, the goal is to perform by taking action to eliminate hazards or mitigate risk, and then continuously evaluate the outcome of this action. With the example of low ceilings at destination, for instance, the pilot can perform good ADM by selecting a suitable alternate, knowing where to find good weather, and carrying sufficient fuel to reach it. This course of action would mitigate the risk. The pilot also has the option to eliminate it entirely by waiting for better weather. Once the pilot has completed the 3P decision process and selected a course of action, the process begins anew because now the set of circumstances brought about by the course of action requires analysis. The decision-making process is a continuous loop of perceiving, processing, and performing. With practice and consistent use, running through the 3P cycle can become a habit that is as smooth, continuous, and automatic as a well-honed instrument scan. This basic set of practical risk management tools can be used to improve risk management. The 3P model has been expanded to include the care and team models, which offers pilots another way to assess and reduce risks associated with flying. Perceive, process, perform with care and team. Most flight training activities take place in the time-critical time frame for risk management. Figures 17-8 and 17-9 combine the 6 steps of risk management into an easy-to-remember 3P model for practical risk management. Perceive, process, perform, with the care and team models. Pilots can help perceive hazards by using the PAVE checklist of pilot, aircraft, environment, and external pressures. They can process hazards by using the care checklist of consequences, alternatives, reality, external factors. Finally, pilots can perform risk management by using the team choice list of transfer, eliminate, accept, or mitigate. These concepts are relatively new in the general aviation training world, but have been shown to be extraordinarily useful in lowering accident rates in the world of air carriers. Forming good safety habits. While the 3P model is similar to other methods, there are 2 good reasons to use the 3P model. First, the 3P model gives pilots a structured, efficient, and systematic way to identify hazards, assess risk, and implement effective risk controls. Second, practicing risk management needs to be as automatic in general aviation flying as basic aircraft control. As is true for other flying skills, risk management thinking habits are best developed through repetition and consistent adherence to specific procedures. The OODA loop. Colonel John Boyd, United States Air Forces retired, coined the term and developed the concept of the OODA loop: observation, orientation, decision, action. The ideas, words, and phrases contained in Boyd's briefings have penetrated not only the United States military services, but the business community and worldwide academia. The OODA loop is now used as a standard description of decision-making cycles. The loop is an interlaced decision model which provides immediate feedback through the decision-making process. For SRM purposes, an abbreviated version of the concept, refer to Figure 17-10, provides an easily understood tool for the pilot. The first node of the loop, observe, reflects the need for situational awareness. A pilot must be aware of those things around him or her that may impact the flight. Continuous monitoring of aircraft controls, weather, etc., provides a constant reference point by which the pilot knows his or her starting point on the loop, which permits the ability to immediately move to the next step. Orient, the second node of the loop, focuses the pilot's attention on one or more discrepancies in the flight. For example, there is a low oil pressure reading. The pilot is aware of this deviation and considers available options in view of potential hazards to continued flight. The pilot then moves to the third node, decide, in which he or she makes a positive determination about a specific effect. That decision is made based on experience and knowledge of potential results, and to take that particular action will produce the desired result. The pilot then acts on that decision, making a physical input to cause the aircraft to react in the desired fashion. Once the loop has been completed, the pilot is once again in the observed position. The assessment of the resulting action is added to the previously perceived aspects of the flight to further define the flight's progress. The advantage of the OODA loop model is that it may be cumulative as well as having the potential of allowing for multiple progressions to occur at any given point in the flight. The DECIDE model. Using the acronym DECIDE, the six-step process DECIDE model is another continuous loop process that provides the pilot with a logical way of making decisions. Refer to Figure 17-11. DECIDE means to detect, estimate, choose a course of action, identify solutions, do the necessary actions, and evaluate the effects of the actions. First, consider a recent accident involving a Piper Apache, PA-23. The aircraft was substantially damaged during impact with terrain at a local airport in Alabama. The Certificated Airline Transport Pilot, ATP, received minor injuries, and the certificated private pilot was not injured. The private pilot was receiving a check ride from the ATP, who was also a designated examiner, for a commercial pilot certificate with a multi-engine rating. After performing air work at altitude, they returned to the airport, and the private pilot performed a single-engine approach to a full-stop landing. He then taxied back for takeoff, performed a short field takeoff, and then joined the traffic pattern to return for another landing. During the approach for the second landing, the ATP simulated a right engine failure by reducing power on the right engine to zero thrust. This caused the aircraft to yaw right. The procedure to identify the failed engine is a two-step process. First, bring power to maximum controllable on both engines. Because the left engine is the only engine delivering thrust, the yaw increases to the right, which necessitates application of additional left rudder. The failed engine is the side that requires no rudder pressure, in this case the right engine. Second, having identified the failed right engine, the procedure is to feather the right engine and adjust power to maintain descent angle to a landing. However, in this case, the pilot feathered the left engine because he assumed the engine failure was a left engine failure. During twin-engine training, the left engine out is emphasized more than the right engine because the left engine on most light twins is the critical engine. This is due to multi-engine airplanes being subject to P-factor, as are single-engine airplanes. The descending propeller blade of each engine will produce greater thrust than the ascending blade when the airplane is operated under power and at positive angles of attack. The descending propeller blade of the right engine is also a greater distance from the center of gravity, and therefore has a longer moment arm than the descending propeller blade of the left engine. As a result, failure of the left engine will result in the most asymmetrical thrust, adverse yaw, because the right engine will be providing the remaining thrust. Many twins are designed with a counter-rotating right engine. With this design, the degree of asymmetrical thrust is the same with either engine inoperative. Neither engine is more critical than the other. Since the pilot never executed the first step of identifying which engine failed, he feathered the left engine and set the right engine at zero thrust. This essentially restricted the aircraft to a controlled glide. Upon realizing that he was not going to make the runway, the pilot increased power to both engines, causing an enormous yaw to the left. The left propeller was feathered, whereupon the aircraft started to turn left. In desperation, the instructor closed both throttles and the aircraft hit the ground and was substantially damaged. This case is interesting because it highlights two particular issues. First, taking action without forethought can be just as dangerous as taking no action at all. In this case, the pilot's actions were incorrect, yet there was sufficient time to take the necessary steps to analyze the simulated emergency. The second and more subtle issue is that decisions made under pressure are sometimes executed based on limited experience, and the actions taken may be incorrect, incomplete, or insufficient to handle the situation. Detect the problem. Problem detection is the first step in the decision-making process. It begins with recognizing a change occurred or an expected change did not occur. A problem is perceived first by the senses, and then it is distinguished through insight and experience. These same abilities, as well as an objective analysis of all available information, are used to determine the nature and severity of the problem. One critical error made during the decision-making process is incorrectly detecting the problem. In the example above, the change that occurred was a yaw. Estimate the need to react. In the engine-out example, the aircraft yawed right. The pilot was on final approach, and the problem warranted a prompt solution. In many cases, overreaction and fixation excludes a safe outcome. For example, what if the cabin door of a Mooney suddenly opened in flight while the aircraft climbed through 1,500 feet on a clear sunny day? The sudden opening would be alarming, but the perceived hazard the open door presents is quickly and effectively assessed as minor. In fact, the door's opening would not impact safe flight and can almost be disregarded. Most likely, a pilot would return to the airport to secure the door after landing. The pilot flying on a clear day faced with this minor problem may rank the open door as a low risk. What about the pilot on an IFR climb-out in IMC conditions with light intermittent turbulence in rain who is receiving an amended clearance from Air Traffic Control, ATC? The open cabin door now becomes a higher risk factor. The problem is not changed, but the perception of risk a pilot assigns it changes because of the multitude of ongoing tasks and the environment. Experience, discipline, awareness, and knowledge will influence how a pilot ranks a problem. Choose a course of action. After the problem has been identified and its impact estimated, the pilot must determine the desirable outcome and choose a course of action. In the case of the multi-engine pilot given the simulated failed engine, the desired objective is to safely land the airplane. Identify solutions. The pilot formulates a plan that will take him or her to the objective. Sometimes there may be only one course of action available. In the case of the engine failure, already at 500 feet or below, the pilot solves the problem by identifying one or more solutions that lead to a successful outcome. It is important for the pilot not to become fixated on the process to the exclusion of making a decision. Do the necessary actions. Once pathways to resolution are identified, the pilot selects the most suitable one for the situation. The multi-engine pilot given the simulated failed engine must now safely land the aircraft. Evaluate the effect of the action. Finally, after implementing a solution, evaluate the decision to see if it was correct. If the action taken does not provide the desired results, the process may have to be repeated. End of Part 4 of Chapter 17. Part 5 of Chapter 17 of Pilot's Handbook. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Arthur Flavel. Pilot's Handbook of Aeronautical Knowledge by the FAA. Part 5 of Chapter 17, Aeronautical Decision-Making. Decision-making in a dynamic environment. The common approach to decision-making has been through the use of analytical models such as 5P, 3P, OODA, and DECIDE. Good decisions result when pilots gather all available information, review it, analyze the options, rate the options, select a course of action, and evaluate that course of action for correctness. In some situations, there isn't always time to make decisions based on analytical decision-making skills. A good example is a quarterback whose actions are based upon a highly fluid and changing situation. He intends to execute a plan, but new circumstances dictate decision-making on the fly. This type of decision-making is called automatic decision-making or naturalized decision-making. Refer to Figure 17-11b. Automatic decision-making. In an emergency situation, a pilot might not survive if he or she rigorously applied analytical models to every decision made. There is not enough time to go through all the options. But under these circumstances, does he or she find the best possible solution to every problem? For the past several decades, research into how people actually make decisions has revealed that when pressed for time, experts faced with a task loaded with uncertainty first assess whether the situation strikes them as familiar. Rather than comparing the pros and cons of different approaches, they quickly imagine how one or a few possible courses of action in such situations will play out. Experts take the first workable option they can find. While it may not be the best of all possible choices, it often yields remarkably good results. The terms naturalistic and automatic decision-making have been coined to describe this type of decision-making. The ability to make automatic decisions holds true for a range of experts from firefighters to chess players. It appears the expert's ability hinges on the recognition of patterns and consistencies that clarify options in complex situations. Experts appear to make provisional sense of a situation without actually reaching a decision by launching experience-based actions that in turn trigger creative revisions. This is a reflexive type of decision-making anchored in training and experience, and is most often used in times of emergencies when there is no time to practice analytical decision-making. Naturalistic or automatic decision-making improves with training and experience, and a pilot will find himself or herself using a combination of decision-making tools that correlate with individual experience and training. Operational pitfalls. Although more experienced pilots are likely to make more automatic decisions, there are tendencies or operational pitfalls that come with the development of pilot experience. These are classic behavioral traps into which pilots have been known to fall. More experienced pilots, as a rule, try to complete a flight as planned, please passengers, and meet schedules. The desire to meet these goals can have an adverse effect on safety and contribute to an unrealistic assessment of piloting skills. All experienced pilots have fallen prey to, or have been tempted by, one or more of these tendencies in their flying careers. These dangerous tendencies or behavior patterns, which must be identified and eliminated, include the operational pitfalls shown in Figure 17-12. Stress management. Everyone is stressed, to some degree, almost all of the time. A certain amount of stress is good, since it keeps a person alert and prevents complacency. Effects of stress are cumulative, and if the pilot does not cope with them in an appropriate way, they can eventually add up to an intolerable burden. Performance generally increases with the onset of stress, peaks, and then begins to fall off rapidly as stress levels exceed a person's ability to cope. The ability to make effective decisions during flight can be impaired by stress. There are two categories of stress: acute and chronic. These are both explained in Chapter 16, Aeromedical Factors. Factors referred to as stressors can increase a pilot's risk of error in the flight deck. Refer to Figure 17-13. Remember the cabin door that suddenly opened in flight on the Mooney climbing through 1,500 feet on a clear sunny day? It may startle the pilot, but the stress would wane when it became apparent the situation was not a serious hazard. Yet, if the cabin door opened in IMC conditions, the stress level makes significant impact on the pilot's ability to cope with simple tasks. The key to stress management is to stop, think, and analyze before jumping to a conclusion. There is usually time to think before drawing unnecessary conclusions. There are several techniques to help manage the accumulation of life stresses and prevent stress overload. For example, to help reduce stress levels, set aside time for relaxation each day, or maintain a program of physical fitness. To prevent stress overload, learn to manage time more effectively to avoid pressures imposed by getting behind schedule and not meeting deadlines. Use of resources. To make informed decisions during flight operations, a pilot must also become aware of the resources found inside and outside the flight deck. Since useful tools and sources of information may not always be readily apparent, learning to recognize these resources is an essential part of ADM training. Resources must not only be identified, but a pilot must also develop the skills to evaluate whether there is time to use a particular resource and the impact its use will have upon the safety of flight. For example, the assistance of ATC may be very useful if a pilot becomes lost, but in an emergency situation, there may be no time available to contact ATC. Internal resources. One of the most underutilized resources may be the person in the right seat, even if the passenger has no flying experience. When appropriate, the PIC can ask passengers to assist with certain tasks, such as watching for traffic or reading checklist items. Some other ways a passenger can assist. Provide information in an irregular situation, especially if familiar with flying. A strange smell or sound may alert a passenger to a potential problem. Confirm after the pilot that the landing gear is down. Learn to look at the altimeter for a given altitude in a descent. Listen to logic or lack of logic. Also, the process of a verbal briefing, which can happen whether or not passengers are aboard, can help the PIC in the decision-making process. For example, assume a pilot provides a lone passenger a briefing of the forecast landing weather before departure. When the Automatic Terminal Information Service, ATIS, is picked up, the weather has significantly changed. The discussion of this forecast change can lead the pilot to re-examine his or her activities and decision-making. Refer to Figure 17-14. Other valuable internal resources include ingenuity, aviation knowledge, and flying skill. Pilots can increase flight deck resources by improving these characteristics. When flying alone, another internal resource is verbal communication. It has been established that verbal communication reinforces an activity. Touching an object while communicating further enhances the probability an activity has been accomplished. For this reason, many solo pilots read the checklist out loud. When they reach critical items, they touch the switch or control. For example, to ascertain the landing gear is down, the pilot can read the checklist, but if he or she touches the gear handle during the process, a safe extension of the landing gear is confirmed. It is necessary for a pilot to have a thorough understanding of all the equipment and systems in the aircraft being flown. Lack of knowledge, such as knowing if the oil pressure gauge is direct reading or uses a sensor, is the difference between making a wise decision or poor one that leads to a tragic error. Checklists are essential flight deck internal resources. They are used to verify the aircraft instruments and systems are checked, set, and operating properly, as well as ensuring the proper procedures are performed if there is a system malfunction or in-flight emergency. Students reluctant to use checklists can be reminded that pilots at all levels of experience refer to checklists, and that the more advanced the aircraft is, the more crucial checklists become. In addition, the Pilot's Operating Handbook, POH, is required to be carried on board the aircraft and is essential for accurate flight planning and resolving in-flight equipment malfunctions. However, the most valuable resource a pilot has is the ability to manage workload, whether alone or with others. External resources. Air traffic controllers and flight service specialists are the best external resources during flight. In order to promote the safe, orderly flow of air traffic around airports and along flight routes, the ATC provides pilots with traffic advisories, radar vectors, and assistance in emergency situations. Although it is the PIC's responsibility to make the flight as safe as possible, a pilot with a problem can request assistance from ATC. Refer to Figure 17-15. For example, if a pilot needs to level off, be given a vector, or decrease speed, ATC assists and becomes integrated as part of the crew. The services provided by ATC can not only decrease pilot workload, but also help pilots make informed in-flight decisions. The flight service stations are air traffic facilities that provide pilot briefing, en route communications, VFR search and rescue services, assist lost aircraft and aircraft in emergency situations, relay ATC clearances, originate notices to airmen, NOTAM, broadcast aviation weather and National Airspace System NAS information, receive and process IFR flight plans, and monitor navigational aids, NavAids. In addition, at selected locations, flight service stations provide en route flight advisory service, Flight Watch, issue airport advisories, and advise Customs and Immigration of transborder flights. Selected flight service stations in Alaska also provide T-Web recordings and make weather observations. End of Part 5 of Chapter 17. Part 6 of Chapter 17 of Pilot's Handbook. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Arthur Flavel. Pilot's Handbook of Aeronautical Knowledge by the FAA. Part 6 of Chapter 17, Aeronautical Decision-Making. Situational Awareness. Situational awareness is the accurate perception and understanding of all the factors and conditions within the 5 fundamental risk elements of flight, pilot, aircraft, environment, and type of operation that comprise any given aviation situation that affect safety before, during, and after the flight. Monitoring radio communications for traffic, weather discussion, and ATC communications can enhance situational awareness by helping the pilot develop a mental picture of what is happening. Maintaining situational awareness requires an understanding of the relative significance of all flight-related factors and their future impact on the flight. When a pilot understands what is going on and has an overview of the total operation, he or she is not fixated on one perceived significant factor. Not only is it important for a pilot to know the aircraft's geographical location, it is also important he or she understand what is happening. For instance, while flying above Richmond, Virginia towards Dulles Airport or Leesburg, the pilot should know why he or she is being vectored and be able to anticipate spatial location. A pilot who is simply making turns without understanding why has added an additional burden to his or her management in the event of an emergency. To maintain situational awareness, all of the skills involved in ADM are used. Obstacles to maintaining situational awareness. Fatigue, stress, and work overload can cause a pilot to fixate on a single perceived important item and reduce an overall situational awareness of the flight. A contributing factor in many accidents is the distraction that diverts the pilot's attention from monitoring the instruments or scanning outside the aircraft. Many flight deck distractions begin as a minor problem, such as a gauge that is not reading correctly, but result in accidents as the pilot diverts attention to the perceived problem and neglects to properly control the aircraft. Workload management. Effective workload management ensures essential operations are accomplished by planning, prioritizing, and sequencing tasks to avoid work overload. Refer to Figure 17-16. As experience is gained, a pilot learns to recognize future workload requirements and can prepare for high workload periods during times of low workload. Reviewing the appropriate chart and setting frequencies well in advance of when they're needed helps reduce workload as the flight nears the airport. In addition, a pilot should listen to ATIS, Automated Surface Observation System, ASOS, or Automated Weather Observing System, AWOS, if available, and then monitor the tower frequency or Common Traffic Advisory Frequency, CTAF, to get a good idea of what traffic conditions to expect. Checklists should be performed well in advance so there is time to focus on traffic and ATC instructions. These procedures are especially important prior to entering a high-density traffic area, such as Class B airspace. Recognizing a work overload situation is also an important component of managing workload. The first effect of high workload is that the pilot may be working harder but accomplishing less. As workload increases, attention cannot be devoted to several tasks at one time, and the pilot may begin to focus on one item. When a pilot becomes task-saturated, there is no awareness of input from various sources, so decisions may be made on incomplete information, and the possibility of error increases. Refer to Figure 17-17. When a work overload situation exists, a pilot needs to stop, think, slow down, and prioritize. It is important to understand how to decrease workload. For example, in the case of the cabin door that opened in VFR flight, the impact on workload should be insignificant. If the cabin door opens under IFR conditions, its impact on workload will change. Therefore, placing a situation in the proper perspective, remaining calm, and thinking rationally are key elements in reducing stress and increasing the capacity to fly safely. This ability depends upon experience, discipline, and training. Managing risks. The ability to manage risk begins with preparation. Here are some things a pilot can do to manage overall risk. Assess the flight's risk based upon experience. Use some form of risk assessment. For example, if the weather is marginal and the pilot has low IMC training, it is probably a good idea to cancel the flight. Brief passengers using the safety list. S. Seatbelts fastened for takeoff, taxi, landing. Shoulder harness fastened for takeoff, landing. Seat position adjusted and locked in place. A. Air vents, location and operation. All environmental controls discussed. Action in case of any passenger discomfort. F. Fire extinguisher, location and operation. E. Exit doors, how to secure, how to open. Emergency evacuation plan. Emergency or survival kit location and contents. T. Traffic, scanning, spotting, notifying pilot. Talking, sterile flight deck expectations. Y. Your questions? Speak up. In addition to the safety list, discuss with passengers whether or not smoking is permitted, flight route altitudes, time en route, destination, weather during flight, expected weather at the destination, controls and what they do, and the general capabilities and limitations of the aircraft. Use a sterile flight deck, one that is completely silent with no pilot communication with passengers or by passengers from the time of departure to the first intermediate altitude and clearance from the local airspace. Use a sterile flight deck during arrival from the first radar vector for approach or descent for the approach. Keep the passengers informed during times when the workload is low. Consider using the passenger in the right seat for simple tasks such as holding the chart. This relieves the pilot of a task. Automation. In the general aviation community, an automated aircraft is generally comprised of an integrated advanced avionics system consisting of a primary flight display, PFD, a multifunction flight display, MFD, including an instrument-certified global positioning system, GPS, with traffic and terrain graphics, and a fully integrated autopilot. This type of aircraft is commonly known as an advanced avionics aircraft. In an advanced avionics aircraft, there are typically two displays, computer screens, PFD, left display screen, and the MFD. Automation is the single most important advance in aviation technologies. Electronic flight displays, EFDs, have made vast improvements in how information is displayed and what information is available to the pilot. pilots can access electronic databases that contain all of the information traditionally contained in multiple handbooks, reducing clutter in the flight deck. Refer to Figure 17-18 with errata. Multifunction displays, MFDs, are capable of displaying moving maps that mirror sectional charts. These detailed displays depict all airspace, including temporary flight restrictions, TFRs. MFDs are so descriptive that many pilots fall into the trap of relying solely on the moving maps for navigation. Pilots also draw upon the database to familiarize themselves with departure and destination airport information. More pilots now rely on electronic databases for flight planning and use automated flight planning tools rather than planning the flight by the traditional methods of laying out charts, drawing the course, identifying navigation points, assuming a VFR flight, and using the pilot's operating handbook to figure out the weight and balance and performance charts. Whichever method a pilot chooses to plan a flight, it is important to remember to check and confirm calculations. Although automation has made flying safer, automated systems can make some errors more evident, and sometimes hide other errors or make them less evident. There are concerns about the effect of automation on pilots. In a study published in 1995, the British Airline Pilots Association officially voiced its concern that airline pilots increasingly lack basic flying skills as a result of reliance on automation. This reliance on automation translates into a lack of basic flying skills that may affect the pilot's ability to cope with an in-flight emergency, such as sudden mechanical failure. The worry that pilots are becoming too reliant on automated systems and are not being encouraged or trained to fly manually has grown with the increase in the number of MFD flight decks. As automated flight decks began entering everyday line operations, instructors and check airmen grew concerned about some of the unanticipated side effects. Despite the promise of reducing human mistakes, the flight managers reported the automation actually created much larger errors at times. In the terminal environment, the workload in an automated flight deck actually seemed higher than in the older analog flight decks. At other times, the automation seemed to lull the flight crews into complacency. Over time, concern surfaced that the manual flying skills of the automated flight crew deteriorated due to over-reliance on computers. The flight crew managers said they worried that pilots would have less stick and rudder proficiency when those skills were needed to manually resume direct control of the aircraft. A major study was conducted to evaluate the performance of two groups of pilots. The control group was composed of pilots who flew an older version of a common twin-jet airliner equipped with analog instrumentation, and the experimental group was composed of pilots who flew the same aircraft, but newer models equipped with an electronic flight instrument system, EFIS, and a flight management system, FMS. The pilots were evaluated in maintaining aircraft parameters such as heading, altitude, airspeed, glide slope, and localizer deviations, as well as pilot control inputs. These were recorded during a variety of normal, abnormal, and emergency maneuvers during 4 hours of simulator sessions. Results of the study. When pilots who had flown EFIS for several years were required to fly various maneuvers manually, the aircraft parameters and flight control inputs clearly showed some erosion of flying skills. During normal maneuvers, such as turns to headings without a flight director, the EFIS group exhibited somewhat greater deviations than the analog group. Most of the time, the deviations were within the practical test standards, PTS, but the pilots definitely did not keep on the localizer and glide slope as smoothly as the analog group. The differences in hand flying skills between the two groups became more significant during abnormal maneuvers, such as slam dunks. When given close crossing restrictions, the analog crews were more adept at the mental math and usually maneuvered the aircraft in a smoother manner to make the restriction. On the other hand, the EFIS crews tended to go heads down and tried to solve the crossing restriction on the FMS. Refer to Figure 17-19 with errata. Another situation used in the simulator experiment reflected real-world changes in approach that are common and can be assigned on short notice. Once again, the analog crews transitioned more easily to the parallel runways localizer, whereas the EFIS crews had a much more difficult time, with the pilot going head down for a significant amount of time trying to program the new approach into the FMS. While a pilot's lack of familiarity with the EFIS is often an issue, the approach would have been made easier by disengaging the automated system and manually flying the approach. At the time of this study, the general guidelines in the industry were to let the automated system do as much of the flying as possible. That view has since changed, and it is recommended that pilots use their best judgment when choosing which level of automation will most efficiently do the task, considering the workload and situational awareness. Emergency maneuvers clearly broaden the difference in manual flying skills between the two groups. In general, the analog pilots tended to fly raw data, so when they were given an emergency such as an engine failure and were instructed to fly the maneuver without a flight director, they performed it expertly. By contrast, SOP for EFIS operations at the time was to use the flight director. When EFIS crews had their flight directors disabled, their eye scan again began a more erratic searching pattern, and their manual flying subsequently suffered. Those who reviewed the data saw that the EFIS pilots who better managed the automation also had better flying skills. While the data did not reveal whether those skills preceded or followed automation, it did indicate that automation management needed to be improved. Recommended best practices and procedures have remedied some of the earlier problems with automation. Pilots need to maintain their flight skills and ability to maneuver aircraft manually within the standards set forth in the PTS. It is recommended that pilots of automated aircraft occasionally disengage the automation and manually fly the aircraft to maintain stick and rudder proficiency. It is imperative pilots understand that the EFD adds to the overall quality of the flight experience, but it can also lead to catastrophe if not utilized properly. At no time is the moving map meant to substitute for a VFR sectional or low-altitude en route chart. End of Part 6 of Chapter 17. Part 7 of Chapter 17 of Pilot's Handbook. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Arthur Flavel. Pilot's Handbook of Aeronautical Knowledge by the FAA. Part 7 of Chapter 17, Aeronautical Decision-Making. Equipment Use. Autopilot Systems. In a single-pilot environment, an autopilot system can greatly reduce workload. Refer to Figure 17-20. As a result, the pilot is free to focus his or her attention on other flight deck duties. This can improve situational awareness and reduce the possibility of a CFIT accident. While the addition of an autopilot may certainly be considered a risk control measure, the real challenge comes in determining the impact of an inoperative unit. If the autopilot is known to be inoperative prior to departure, this may factor into the evaluation of other risks. For example, the pilot may be planning for a VHF omnidirectional range (VOR) approach down to minimums on a dark night into an unfamiliar airport. In such a case, the pilot may have been relying heavily on a functioning autopilot capable of flying a coupled approach. This would free the pilot to monitor aircraft performance. A malfunctioning autopilot could be the single factor that takes this from a medium to a serious risk. At this point, an alternative needs to be considered. On the other hand, if the autopilot were to fail at a critical, high workload portion of this same flight, the pilot must be prepared to take action. Instead of simply being an inconvenience, this could quickly turn into an emergency if not properly handled. The best way to ensure a pilot is prepared for such an event is to carefully study the issue prior to departure and determine well in advance how an autopilot failure is to be handled. Familiarity. As previously discussed, pilot familiarity with all equipment is critical in optimizing both safety and efficiency. If a pilot is unfamiliar with any aircraft systems, this will add to the workload and may contribute to a loss of situational awareness. This level of proficiency is critical and should be looked upon as a requirement, not unlike carrying an adequate supply of fuel. As a result, pilots should not look upon unfamiliarity with the aircraft and its systems as a risk control measure, but instead as a hazard with a high risk potential. Discipline is key to success. Respect for onboard systems. Automation can assist the pilot in many ways, but a thorough understanding of the system or systems in use is essential to gaining the benefits it can offer. Understanding leads to respect, which is achieved through discipline and the mastery of the onboard systems. It is important to fly the airplane using minimal information from the primary flight display, PFD. This includes turns, climbs, descents, and being able to fly approaches. Reinforcement of onboard suites. The use of an electronic flight display may not seem intuitive, but competency becomes better with understanding and practice. Computer-based software and incremental training help the pilot become comfortable with the onboard suites. Then, the pilot needs to practice what was learned in order to gain experience. Reinforcement not only yields dividends in the use of automation, it also reduces workload significantly. Getting beyond rote workmanship. The key to working effectively with automation is getting beyond the sequential process of executing an action. If a pilot has to analyze what key to push next, or always uses the same sequence of keystrokes when others are available, he or she may be trapped in a rote process. This mechanical process indicates a shallow understanding of the system. Again, the desire is to become competent and know what to do without having to think about what keystroke is next. Operating the system with competency and comprehension benefits a pilot when situations become more diverse and tasks increase. Understanding the platform. Contrary to popular belief, flight in aircraft equipped with different electronic management suites requires the same attention as aircraft equipped with analog instrumentation and a conventional suite of avionics. The pilot should review and understand the different ways in which the EFD are used in a particular aircraft. Refer to Figure 17-21. 2 simple rules for use of an EFD. Be able to fly the aircraft to the standards in the PTS. Although this may seem insignificant, knowing how to fly the aircraft to a standard makes a pilot's airmanship smoother and allows him or her more time to attend to the system instead of managing multiple tasks. Read and understand the installed electronic flight systems manuals to include the use of the autopilot and other onboard electronic management tools. Managing aircraft automation. Before any pilot can master aircraft automation, he or she must first know how to fly the aircraft. Maneuvers training remains an important component of flight training because almost 40% of all general aviation accidents take place in the landing phase, one realm of flight that still does not involve programming a computer to execute. Another 15% of all general aviation accidents occurs during takeoff and initial climb. An advanced avionics safety issue identified by the FAA concerns pilots who apparently develop an unwarranted over-reliance in their avionics and the aircraft, believing that the equipment will compensate for pilot shortcomings. Related to the over-reliance is the role of ADM, which is probably the most significant factor in the general aviation accident record of high-performance aircraft used for cross-country flight. The FAA Advanced Avionics Aircraft Safety Study found that poor decision-making seems to afflict new advanced avionics pilots at a rate higher than that of general aviation as a whole. The review of advanced avionics accidents cited in this study shows the majority are not caused by something directly related to the aircraft, but by the pilot's lack of experience and a chain of poor decisions. One consistent theme in many of the fatal accidents is continued VFR flight into IMC. Thus, pilot skills for normal and emergency operations hinge not only on mechanical manipulation of the stick and rudder, but also include the mental mastery of the EFD. 3 key flight management skills are needed to fly the advanced avionics safely: information, automation, and risk. Information management. For the newly transitioning pilot, the PFD, MFD, and GPS/VHF navigator screens seem to offer too much information presented in colorful menus and submenus. In fact, the pilot may be drowning in information but unable to find a specific piece of information. It might be helpful to remember these systems are similar to computers, which store some folders on a desktop and some within a hierarchy. The first critical information management skill for flying with advanced avionics is to understand the system at a conceptual level. Remembering how the system is organized helps the pilot manage the available information. It is important to understanding that learning knob and dial procedures is not enough. Learning more about how advanced avionics systems work leads to better memory for procedures and allows pilots to solve problems they have not seen before. There are also limits to understanding. It is generally impossible to understand all of the behaviors of a complex avionics system. Knowing to expect surprises and to continually learn new things is more effective than attempting to memorize mechanical manipulation of the knobs. Simulation software and books on the specific system used are of great value. The second critical information management skill is to stop, look, and read. Pilots new to advanced avionics often become fixated on the knobs and try to memorize each and every sequence of button pushes, pulls, and turns. A far better strategy for accessing and managing the information available in advanced avionics computers is to stop, look, and read. Reading before pushing, pulling, or twisting can often save a pilot some trouble. Once behind the display screens on an advanced avionics aircraft, the pilot's goal is to meter, manage, and prioritize the information flow to accomplish specific tasks. Certificated flight instructors, CFIs, as well as pilots transitioning to advanced avionics, will find it helpful to corral the information flow. This is possible through such tactics as configuring the aspects of the PFD and MFD screens according to personal preferences. For example, most systems offer map orientation options that include north up, track up, DTK, desired track up, and heading up. Another tactic is to decide, when possible, how much or how little information to display. Pilots can tailor the information displayed to suit the needs of a specific flight. Information flow can also be managed for a specific operation. The pilot has the ability to prioritize information for a timely display of exactly the information needed for any given flight operation. Examples of managing information display for a specific operation include program map scale settings for en route versus terminal area operation, utilize the terrain awareness page on the MFD for a night or IMC flight in or near the mountains, use the nearest airport's inset on the PFD at night or over inhospitable terrain, program the weather data link set to show echoes and METAR status flags. Enhanced situational awareness. An advanced avionics aircraft offers increased safety with enhanced situational awareness. Although aircraft flight manuals, AFM, explicitly prohibit using the moving map, topography, terrain awareness, traffic, and weather data link displays as the primary data source, these tools nonetheless give the pilot unprecedented information for enhanced situational awareness. Without a well-planned information management strategy, these tools also make it easy for an unwary pilot to slide into the complacent role of passenger in command. Consider the pilot whose navigational information management strategy consists solely of following the magenta line on the moving map. He or she can easily fly into geographic or regulatory disaster if the straight-line GPS course goes through high terrain or prohibited airspace, or if the moving map display fails. A good strategy for maintaining situational awareness information management should include practices that help ensure that awareness is enhanced by the use of automation, not diminished. Two basic procedures are to always double-check the system and verbal callouts. At a minimum, ensure the presentation makes sense. Was the correct destination fed into the navigation system? Callouts, even for single pilot operations, are an excellent way to maintain situational awareness as well as manage information. Other ways to maintain situational awareness include: perform verification check of all programming. Before departure, check all information programmed while on the ground. Check the flight routing. Before departure, ensure all routing matches the planned flight route. Enter the planned route and legs to include headings and leg length on a paper log. Use this log to evaluate what has been programmed. If the two do not match, do not assume the computer data is correct. Double-check the computer entry. Verify waypoints. Make use of all onboard navigation equipment. For example, use VOR to back up GPS and vice versa. Match the use of the automated system with pilot proficiency. Stay within personal limitations. Plan a realistic flight route to maintain situational awareness. For example, although the onboard equipment allows a direct flight from Denver, Colorado to Destin, Florida, the likelihood of rerouting around Eglin Air Force Base's airspace is high. Be ready to verify computer data entries. For example, incorrect keystrokes could lead to loss of situational awareness because the pilot may not recognize errors made during a high workload period. Automation management. Advanced avionics offer multiple levels of automation, from strictly manual flight to highly automated flight. No one level of automation is appropriate for all flight situations, but in order to avoid potentially dangerous situations when flying with advanced avionics, the pilot must know how to manage the course deviation indicator, CDI, the navigation source, and the autopilot. It is important for a pilot to know the peculiarities of the particular automated system being used. This ensures the pilot knows what to expect, how to monitor for proper operation, and promptly take appropriate action if the system does not perform as expected. For example, at the most basic level, managing the autopilot means knowing at all times which modes are engaged and which modes are armed to engage. The pilot needs to verify that armed functions, for example, navigation tracking or altitude capture, engage at the appropriate time. Automation management is another good place to practice the call-out technique, especially after arming the system to make a change in course or altitude. In advanced avionics aircraft, proper automation management also requires a thorough understanding of how the autopilot interacts with other systems. For example, with some autopilots, changing the navigation source on the EHSI from GPS to LOC or VOR while the autopilot is engaged in nav, the course tracking mode, will cause the autopilot's nav mode to disengage. The autopilot's lateral control will default to ROL, wing level, until the pilot takes action to re-engage the nav mode to track the desired navigation source. Risk management. Risk management is the last of the three management skills needed for mastery of the glass flight deck aircraft. The enhanced situational awareness and automation capabilities offered by a glass flight deck airplane vastly expand its safety and utility, especially for personal transportation use. At the same time, there is some risk that lighter workloads could lead to complacency. Humans are characteristically poor monitors of automated systems. When asked to passively monitor an automated system for faults, abnormalities, or other infrequent events, humans perform poorly. The more reliable the system, the poorer the human performance. For example, the pilot only monitors a backup alert system rather than the situation that the alert system is designed to safeguard. It is a paradox of automation that technically advanced avionics can both increase and decrease pilot awareness. It is important to remember that electronic flight displays do not replace basic flight knowledge and skills. They are a tool for improving flight safety. Risk increases when the pilot believes the gadgets will compensate for lack of skill and knowledge. It is especially important to recognize there are limits to what the electronic systems in any light general aviation aircraft can do. Being PIC requires sound ADM, which sometimes means saying no to a flight. Risk is also increased when the pilot fails to monitor the systems. By failing to monitor the systems and failing to check the results of the processes, the pilot becomes detached from the aircraft operation and slides into the complacent role of passenger in command. Complacency led to tragedy in a 1999 aircraft accident. In Colombia, a multi-engine aircraft crewed with 2 pilots struck the face of the Andes Mountains. Examination of their FMS revealed they entered a waypoint into the FMS incorrectly by 1 degree, resulting in a flight path taking them to a point 60 nautical miles off their intended course. The pilots were equipped with the proper charts, their route was posted on the charts, and they had a paper navigation log indicating the direction of each leg. They had all the tools to manage and monitor their flight, but instead allowed the automation to fly and manage itself. The system did exactly what it was programmed to do. It flew on a programmed course into a mountain, resulting in multiple deaths. The pilots simply failed to manage the system and inherently created their own hazard. Although this hazard was self-induced, what is notable is the risk the pilots created through their own inattention. By failing to evaluate each turn made at the direction of automation, the pilots maximized risk instead of minimizing it. In this case, a totally avoidable accident became a tragedy through simple pilot error and complacency. For the general aviation pilot transitioning to automated systems, it is helpful to note that all human activity involving technical devices entails some element of risk. Knowledge, experience, and mission requirements tilt the odds in favor of safe and successful flights. The advanced avionics aircraft offers many new capabilities and simplifies the basic flying tasks, but only if the pilot is properly trained and all the equipment is working as advertised. Chapter Summary. This chapter focuses on helping the pilot improve his or her ADM skills with the goal of mitigating the risk factors associated with flight in both classic and automated aircraft. In the end, the discussion is not so much about aircraft, but about the people who fly them. End of Part 7 of Chapter 17.
Part 1 of Appendix 1 of Pilot's Handbook. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please go to LibriVox.org. Recording by Robert Sherman, Jr. Pilot's Handbook of Aeronautical Knowledge by the FAA. Appendix 1, Part 1. Runway Incursion Avoidance. Introduction. Runway safety is a significant challenge and a top priority for everyone in aviation. In the United States, an average of 3 runway incursions occur daily. Each of these incidents have the potential to cause significant damage to both persons and property. Runway incursions are a serious safety concern and have involved air carrier aircraft, military aircraft, general aviation or GA, and pedestrian vehicles. See Figure 1-1. Several runway incursions have resulted in collisions and fatalities. Fatalities have occurred at both towered and non-towered airports. A few seconds of inattention can cause a runway incursion. You are expected to taxi an airplane safely whether moving to or from a runway or otherwise moving about the airport. Scenarios such as bad weather, low visibility, construction, airport unfamiliarity, time of day, distractions, fatigue, and miscommunications with air traffic control or ATC add greatly to the challenge of surface navigation. This chapter is designed to help you attain an understanding of the risks associated with surface navigation and is intended to provide you with basic information regarding the safe operation of aircraft at towered and non-towered airports. This chapter focuses on the following major areas: runway incursion overview, taxi route planning, taxi procedures, communications, airport signs, markings, and lighting. Each section identifies best practices to help you avoid errors that may potentially lead to runway incursions. Although the chapter pertains mostly to surface movements for single pilot operations, all of the information is relevant for flight crew operations as well. Additional information about surface operations is available through the following sources: Federal Aviation Administration FAA Runway Safety website, www.faa.gov/go/runway safety. FAA National Aeronautical Navigation Services, Aeronav, formerly known as the National Aeronautical Charting Office, NACO, www.faa.gov/air_traffic/flight_info/AERONAV. Airport Facility Directory, AFD, www.faa.gov/air_traffic/flight_info/aeronav/product catalog/supplemental charts/airport directory. Automatic Terminal Information Service, ATIS. Notice to Airmen, NOTAMs, http://www.faa.gov/pilots/FLT_PLAN/NOTAMs. Advisory Circular AC 91-73, Part 91 and Part 135, Single Pilot and Flight School Procedures During Taxi Operations. Aeronautical Information Manual, AIM, www.faa.gov/air_traffic/publications/atpubs/AIM. AC 120-74, Parts 91, 121, 125, and 135, Flight Crew Procedures During Taxi Operations. Runway Incursion Overview. Approximately 3 runway incursions occur each day at towered airports within the United States. The potential that these numbers present for a catastrophic accident is unacceptable. A runway incursion is formally defined by the FAA as, quote, an occurrence at an aerodrome involving the incorrect presence of an aircraft, vehicle, or person on the protected area of a surface designated for the landing and takeoff of aircraft, end quote. The following are examples of pilot deviations, operational incidents, OI, and vehicle, driver deviations that may lead to runway incursions. Pilot deviations. Crossing a runway hold marking without clearance from ATC, taking off without clearance, landing without clearance. Operational incidents, OI. Clearing an aircraft onto a runway while another aircraft is landing on the same runway, issuing a takeoff clearance while the runway is occupied by another aircraft or vehicle. Vehicle, driver deviations. Crossing a runway hold marking without ATC clearance. According to FAA data, approximately 65% of all runway incursions are caused by pilots. Additionally, 75% of the 65% of runway incursions are caused by GA pilots. Causal factors of runway incursions. Detailed investigations of runway incursions over the past 10 years have identified 3 major areas contributing to these events: failure to comply with ATC instructions, lack of airport familiarity, nonconformance with standard operating procedures. Clear, concise, and effective pilot-controller communication is paramount to safe airport surface operations. You must fully understand and comply with all ATC instructions. It is mandatory to read back all runway hold short instructions verbatim. Taxiing on an unfamiliar airport can be very challenging, especially during hours of darkness or low visibility. Ensure you have a current airport diagram, remain heads up with eyes outside, and devote your entire attention to surface navigation per ATC clearance. All checklists should be completed while the aircraft is stopped. There is no place for non-essential chatter or other activities while maintaining vigilance during taxi. See Figure 1-2. Runway confusion. Runway confusion is a subset of runway incursions and often results in you unintentionally taking off or landing on a taxiway or wrong runway. Generally, you are unaware of the mistake until after it has occurred. In August 2006, the flight crew of a commercial regional jet was cleared for takeoff on runway 22, but mistakenly lined up and departed on runway 26, a much shorter runway. As a result, the aircraft crashed off the end of the runway. Causal factors of runway confusion. There are three major factors that increase the risk of runway confusion and can lead to a wrong runway departure: airport complexity, close proximity of runway thresholds, joint use of a runway as a taxiway. Not only can airport complexity contribute to a runway incursion, it can also play a significant role in runway confusion. If you are operating at an unfamiliar airport and need assistance in executing the taxi clearance, do not hesitate to ask ATC for help. Always carry a current airport diagram and trace or highlight your taxi route to the departure runway prior to leaving the ramp. If you are operating from an airport with runway thresholds in close proximity to one another, exercise extreme caution when taking the runway. Figure 1-3 shows a perfect example of a taxiway leading to a runway and a runway with a displaced threshold. If departing on runway 36, ensure that you set your aircraft heading bug to 360 degrees and align your aircraft to the runway heading to avoid departing from the wrong runway. Before adding power, make one last instrument scan to ensure that the aircraft heading and runway heading are aligned. Under certain circumstances, it may be necessary to use a runway as a taxiway. For example, during airport construction, some taxiways may be closed, requiring rerouting of traffic onto runways. In other cases, departing traffic may be required to back taxi on the runway in order to utilize the full runway length. It is important to remain extremely cautious and maintain situational awareness, SA. When instructed to use a runway as a taxiway, do not become confused and take off on the runway you are using as a taxiway. Taxi route planning. Thorough planning is essential for safe taxi operations. Give as much attention to planning the airport surface movement as is given to other phases of flight. See Figure 1-4. Notices to airmen, NOTAMs. Time-critical aeronautical information, which is of a temporary nature or not sufficiently known in advance to permit publication on aeronautical charts or in other operational publications, receives immediate dissemination by the NOTAM system. The NOTAM information could affect your decision to make the flight. It includes such information as taxiway and runway closures, construction, communications, changing in status of navigational aids, and other information essential to planned en route, terminal, or landing operations. Exercise good judgment and common sense by carefully regarding the information readily available in NOTAMs. For more detailed information on NOTAMs, refer back to Chapter 1 of this handbook. Automated Terminal Information Service, ATIS. The Automated Terminal Information Service, ATIS, is a recording of the local weather conditions and other pertinent non-control information broadcast on a local frequency in a looped format. It is normally updated once per hour, but is updated more often when changing local conditions warrant. Important information is broadcast on ATIS, including weather, runways in use, specific ATC procedures, and any airport construction activity that could affect taxi planning. When the ATIS is recorded, it is given a code. This code is changed with every ATIS update. For example, ATIS Alpha is replaced by ATIS Bravo. The next hour, ATIS Charlie is recorded, followed by ATIS Delta, and progresses down the alphabet with every update starting back at Alpha after a break in service of 12 hours or more. Prior to calling ATC, tune to the ATIS frequency and listen to the recorded broadcast. The broadcast ends with a statement containing the ATIS code. For example, advise on initial contact, you have information Bravo. Upon contacting the tower controller, state information Bravo was received. This allows the tower controller to verify the pilot has the current local weather and airport information without having to state it all to each pilot who calls. This also clears the tower frequency from being overtaken by the constant relay of the same information, which will result without an ATIS broadcast. The use of ATIS broadcasts at departure and arrival airports is not only a sound practice but a wise decision. Airport Facility Directory, AFD. The Airport Facility Directory, AFD, is a pilot's manual that provides information on airports and other aviation facilities. The directory includes data that cannot be readily depicted in graphic form, including airport hours, runway widths, lighting codes, and fuel available. See Figure 1-5. Airport Diagram. It is essential to have a current airport diagram available for the departure airport as well as the arrival airport for safe operations. See Figure 1-6. In the back section of each AFD volume are full-page airport diagrams that can help you plan surface operations. Time should be taken to study the airport diagram and anticipated taxi routes based on the information provided from the ATIS and NOTAMs. You should not take for granted that the anticipated taxi route will be the same taxi route received from ATC, which is why it is so important to write down and read back the taxi clearance from ATC. Current airport diagrams are available for download at www.faa.gov/airports/runway_safety/diagrams. Hotspots. An airport hotspot is typically a complex or confusing taxiway/taxiway or taxiway/runway intersection. This area of increased risk has either a history of or potential for runway incursions or surface incidents due to a variety of causes, including airport layout, traffic flow, airport marking, signage, and lighting. You should pay special attention to any complex intersections or areas designated on the airport diagram as hotspots to reduce the risk of a runway incursion. Hotspots are depicted on airport diagrams as open circles or polygons designated as HS1, HS2, etc. See Figure 1-7. Hotspots will remain charted on airport diagrams until the increased risk has been reduced or eliminated. Being proactive by knowing all possible taxi routes and maintaining taxi route awareness helps mitigate runway incursions, especially when navigating through complex intersections, known hotspot areas, and intervening runways. End of Part 1 of Appendix 1. Recording by Robert Sherman, Jr., Washington, D.C., www.nyckidd.com. Part 2 of Appendix 1 of Pilot's Handbook. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Robert Sherman, Jr. Pilot's Handbook of Aeronautical Knowledge, Appendix 1, Part 2, Taxi Procedures. It is important for you to learn and understand how to safely follow taxi procedures. This section addresses specific ATC instructions that may be issued while taxiing and procedures that you should follow. For more information on detailed taxi procedures to be followed at towered airports, refer to Chapter 4 of the Aeronautical Information Manual, AIM. Situational Awareness, SA. Situational Awareness, SA, means understanding what is going on around you. Also, understanding is more than just information gathering. It requires gathering the right information, being able to analyze it, and making decisions. SA should be used at all times when operating on an airfield. For example, prior to brake release for taxi, minimize cockpit tasks, observe sterile flight deck procedures, and always practice a heads-up, eyes-out mode while taxiing. Remain especially vigilant of hold short crossing clearances and hotspots if applicable. When taxiing, be aware of your location as it relates to the intended taxi route, other aircraft that are taxiing, and vehicles operating on the airport. See Figure 1-8. If in doubt, stop, remain clear of the runway, and contact ATC. The following excerpt, taken from the AFD, is an example of information available to you that helps mitigate the loss of SA. Taxiing aircraft should use caution in early morning and late afternoon hours. Sun glare may make visual recognition of signs and pavement markings difficult. See Figure 1-9. Movement and non-movement area boundary. At towered airports, the airport surface is divided into two parts, non-movement area and movement area. The non-movement area is defined as ramps and aprons and is not controlled by ATC, which means you may move or taxi the airplane without clearance or communication with the control tower. The movement area is defined as all taxiways and runways and is under the jurisdiction of the control tower, so a taxi clearance is required prior to entering into the movement area. The boundary between the ramp and the taxiways is called the non-movement area boundary and is defined by two yellow lines, one solid and one dashed. See Figure 1-10. The solid line is located on the non-movement area side, while the dashed yellow line is located on the movement area side. Once you are ready to taxi, ATC should be contacted for taxi instructions. After a taxi clearance is received, movement to cross the non-movement area boundary marking and onto the taxiway is authorized. ATC instructions. Title 14 of the Code of Federal Regulations, 14 CFR, Part 91, Section 91.123, requires you to follow all ATC clearances and instructions. Request clarification if you are unsure of the clearance or instruction to be followed. If you are unfamiliar with the airport or unsure of a taxi route, ask ATC for a progressive taxi. Progressive taxi requires the controller to provide step-by-step taxi instructions. The final decision to act on ATC's instruction rests with you. If you cannot safely comply with any of ATC's instructions, inform them immediately by using the word unable. There is nothing wrong with telling a controller that you are unable to safely comply with the clearance. Another way to mitigate the risk of runway incursions is to write down all taxi instructions as soon as they are received from ATC. See Figure 1-11. It is also helpful to monitor ATC clearances and instructions that are issued to other aircraft. You should be especially vigilant if another aircraft has a similar sounding call sign, so there is no mistake about who ATC is contacting or to whom they are giving instructions and clearances. Read back your complete ATC clearance with your aircraft call sign. This gives ATC the opportunity to clarify any misunderstandings and ensure that instructions were given to the correct aircraft. If, at any time, there is uncertainty about any ATC instructions or clearances, ask ATC to say again or ask for progressive taxi instructions. ATC instructions, hold short. The most important sign and marking on the airport is the hold sign and hold marking. These are located on a stub taxiway leading directly to a runway. They depict the holding position or the location where the aircraft is to stop so as not to enter the runway environment. See Figure 1-12. For example, Figure 1-13 shows the holding position sign and marking for runway 13 and runway 31. When ATC issues a hold short clearance, you are expected to taxi up to but not cross any part of the runway holding marking. At a towered airport, runway hold markings should never be crossed without explicit ATC instructions. Do not enter a runway at a towered airport unless instructions are given from ATC to cross, take off from, or line up and wait on that specific runway. ATC is required to obtain a readback from the pilot of all runway hold short instructions. Therefore, you must read back the entire clearance and hold short instruction to include runway identifier and your call sign. Figure 1-14 shows an example of a controller's taxi and hold short instruction and the reply from the pilot. ATC instructions, explicit runway crossing. As of June 30th, 2010, ATC is required to issue explicit instructions to cross or hold short of each runway. Instructions to cross a runway are normally issued one at a time, and an aircraft must have crossed the previous runway before another runway crossing is issued. Exceptions may apply for closely spaced runways that have less than 1,000 feet between center lines. This applies to all runways to include active, inactive, or closed. Figure 1-15 shows communication between ATC and a pilot who is requesting a taxi clearance. Extra caution should be used when directed by ATC to taxi onto or across a runway, especially at night and during reduced visibility conditions. Always comply with hold short or crossing instructions when approaching an entrance to a runway. Scan the full length of the runway and the final approaches before entering or crossing any runway, even if ATC has issued a clearance. ATC instructions, line up and wait, LUAW. ATC now uses the line up and wait, LUAW, instruction when a takeoff clearance cannot be issued immediately due to traffic or other reasons. The words line up and wait have replaced position and hold in directing you to taxi onto a runway and await takeoff clearance. An ATC instruction to line up and wait is not a clearance for takeoff. It is only a clearance to enter the runway and hold in position for takeoff. Under LUAW phraseology, the controller states the aircraft call sign, departure runway, and line up and wait. Be aware that traffic holding in position will continue to be used to advise other aircraft that traffic has been authorized to line up and wait on an active runway. Pay close attention when instructed to line up and wait, especially at night or during periods of low visibility. Before entering the runway, remember to scan the full length of the runway and its approach end for other aircraft. There have been collisions and incidents involving aircraft instructed to line up and wait while ATC waits for the necessary conditions to issue a takeoff clearance. An OI caused a 737 to land on a runway occupied by a twin-engine turboprop. The turboprop was holding in position awaiting takeoff clearance. Upon landing, the 737 collided with the twin-engine turboprop. When ATC instructs you to line up and wait, they should advise you of any delay in receiving your takeoff clearance. Possible reasons for ATC takeoff clearance delays may include other aircraft landing and/or departing, wake turbulence, or traffic crossing an intersecting runway. If landing traffic is a factor, ATC is required to inform you of the closest traffic requesting a full stop, touch and go, stop and go, option, or unrestricted low approach on the same runway. Advise the landing traffic that traffic is holding in position on the same runway. If advised of a reason for the delay or the reason is clearly visible, expect an imminent takeoff clearance once the reason is no longer an issue. If a takeoff clearance is not received within 90 seconds after receiving the line up and wait instruction, contact ATC immediately. When ATC issues intersection line up and wait instructions and takeoff clearances, the taxiway designator is included. Note, at night or in low visibility, consider lining up slightly left or right of centerline when holding for takeoff so that your aircraft is visible and can be differentiated from runway lights. ATC instructions, runway shortened. You should review NOTAMs in your pre-flight planning to determine any airport changes that will affect your departure or arrival. When the available runway length has been temporarily or permanently shortened due to construction, the ATIS includes the words warning and shortened in the text of the message. For the duration of the construction when the runway is temporarily shortened, ATC will include the word shortened in their clearance instructions. Furthermore, the use of the term full length will not be used by ATC during this period of the construction. Some examples of ATC instructions are Runway 36 shortened, line up and wait. Runway 36 shortened, cleared for takeoff. Runway 36 shortened, cleared to land. When an intersection departure is requested on a temporarily or permanently shortened runway during the construction, the remaining length of runway is included in the clearance. For example, runway 36 at Echo, intersection departure, 5,600 feet available. If following the construction, the runway is permanently shortened, ATC will include the word shortened until the AFD is updated to include the permanent changes to the runway length. Pre-landing, landing, and after landing. While en route and after receiving the destination airport ATIS/landing information, review the airport diagram and brief yourself as to your exit taxiway. Determine the following. Are there any runway hold markings in close proximity to the exit taxiway? Do not cross any hold markings or exit onto any runways without ATC clearance. After landing, use the utmost caution where the exit taxiways intersect another runway, and do not exit onto another runway without ATC authorization. Do not accept last-minute turn-off instructions from the control tower unless you clearly understand the instructions and are at a speed that ensures you can safely comply. Finally, after landing and upon exiting the runway, ensure your aircraft has completely crossed over the runway hold markings. Once all parts of the aircraft have crossed the runway holding position markings, you must hold unless further instructions have been issued by ATC. Do not initiate non-essential communications or actions until the aircraft has stopped and the brakes set. Aircraft lights. The use of aircraft exterior lights during all flight operations make an aircraft operating on the airport surface more conspicuous and help convey location and intent to you and ATC. Some examples of aircraft exterior light usage are listed below and shown in Figure 1-16. Engines running. Before starting engines, turn on the rotating beacon. Taxiing. Prior to commencing taxi, turn on navigation/position, strobe, only if the use of them does not adversely affect other aircraft, taxi, and logo lights if available. Crossing a runway. Illuminate all external lights when crossing a runway. You should consider any possible adverse effects that illuminating the forward-facing lights may have on the vision of other pilots or ground personnel during runway crossings. Line up and wait. When entering the departure runway without takeoff clearance, turn on all exterior lights except landing lights to make your aircraft more conspicuous. Departure runway. When entering the departure runway after takeoff clearance is received, or when commencing takeoff roll, turn on landing lights. Non-towered airports. Many GA airports, even those with operating ATC towers, may not have airport signage and markings that are required at airports certified by the FAA. In fact, you may observe a wide range of airport signage and markings from one GA airport to the next. There is no substitute for alertness while in the vicinity of an airport. It is essential that pilots be alert and look for other traffic and exchange traffic information when approaching or departing an airport without an operating control tower. This is of particular importance since other aircraft may not have communication capability or, in some cases, pilots may not communicate their presence or intentions when operating into or out of such airports. To achieve the greatest degree of safety, it is essential that all radio-equipped aircraft transmit and receive on a common frequency identified for the purpose of airport advisories. An airport may have a full or part-time tower or flight service station located on the airport, a full or part-time Unicom station, or no aeronautical station at all. There are 3 ways for pilots to communicate their intention and obtain aircraft and traffic information when operating at an airport that does not have an operating tower: by communicating with an FSS, a Unicom operator, or by making a self-announced broadcast. Many airports are now providing completely automated weather, radio check capability, and airport advisory information on an automated Unicom system. These systems offer a variety of features, typically selectable by microphone clicks on the Unicom frequency. Availability of the automated Unicom is published in the AFD and approach charts. Note: line up and wait/holding in position is not recommended at non-towered airports. End of Part 2 of Appendix 1. Recording by Robert Sherman, Jr., Washington, D.C. www.nyckidd.com. Part 3 of Appendix 1 of Pilot's Handbook. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Robert Sherman, Jr. Pilot's Handbook of Aeronautical Knowledge, Appendix 1, Part 3, Communications. Communications. In order to have safe surface operations, it is imperative that you maintain good communication with ATC. The controller's understanding can be enhanced by you responding appropriately and using standard phraseology. Figure 1-17 shows a detailed glossary of phraseology that is commonly used in surface operations. Guidelines for clear and accurate communications include the use of proper communication procedures when contacting ATC. Your initial transmission to ATC should contain the following elements: who you are, aircraft's complete call sign, where you are on the airport, what you want, you should think about what you want to say before communicating it, alphabetical code for the ATIS. Note: you must be alert for stuck microphones. Prior to contacting ATC, transmissions should be well thought out before keying the transmitter. Know what needs to be said and always check the radio frequencies to ensure that the proper one is being used to transmit. Communication with ATC should be concise and to the point. For unusual situations or lengthy communications, initial contact should be established. Then, in the next transmission, describe the situation. Keep in mind that other aircraft are waiting to contact ATC, so transmissions should be kept to a minimum unless it is an emergency situation. While communicating with ATC, focus on what the controller is instructing and do not perform any non-essential tasks. Refer to the AIM, Chapter 5, Section 5, Pilot Controller Roles and Responsibilities. Read back any hold short of runway instructions issued by ATC. This readback should include the specific runway designator and taxiway intersection when appropriate, so if there are any misunderstandings or errors, they are obvious to ATC. A readback presents the first and most efficient opportunity to catch any miscommunications. It provides a reality check in two ways. It tells the controller, this is what the pilot heard, and it provides the controller the opportunity to reaffirm that is what he or she meant to say. For detailed information about radio communication phraseology and techniques, refer to Chapter 4, Section 2 of the AIM. Understanding the NOTAMs for the airport is very important when communicating with ATC. NOTAMs provide information regarding taxiway runway closures. With proper knowledge of the airport's NOTAMs, you can assist ATC. For example, if ATC clears you to taxi on a closed taxiway or runway, you can inform them. If you are unsure of any portion of the taxi clearance, request clarification and/or progressive taxi instructions. It is important for you to know that you can request assistance. Note, when instructed to monitor a particular frequency, listen on the frequency and stand by for instructions. Under normal circumstances, do not initiate communications. Examples of taxi instructions. Initial call-up with specific requests. Pilot, Teterboro Ground, Gulfstream November 322 Zulu Quebec, Acme Aviation, with information Alpha, request taxi to runway 19er. Controller, November 322 Zulu Quebec, Teterboro Ground, runway 19er, taxi via Lima. Line up and wait. Controller, November 523 Quebec, Quebec, runway 27, line up and wait, traffic landing runway 3 right. Pilot, November 523 Quebec, Quebec, runway 27, line up and wait. Line up and wait on intersecting runways. Line up and wait can be authorized on intersecting runways. When this is done, traffic advisories shall be issued to both aircraft. Departure instructions for two aircraft. Controller, November 523 Quebec, Quebec, runway 36 at Golf 4, line up and wait, traffic departing runway 27. Pilot, November 523 Quebec, Quebec, runway 36 at Golf 4, line up and wait. Controller, November 144 November Mike, runway 27, cleared for takeoff, traffic holding in position runway 36. Departure and arrival instructions for two aircraft. Controller, November 477 Zulu Alpha, runway 6, line up and wait, traffic landing runway 27. Pilot, November 477 Zulu Alpha, runway 6, line up and wait. Controller, November 234 Alpha Golf, runway 27, cleared to land, traffic holding in position runway 6. Intersection departure clearance. ATC must state the name of the intersection to you before a line up and wait instruction. You should question ATC if this does not happen. You should state that they are at an intersection when requesting a takeoff clearance. A controller must also state the name of the intersection when issuing a takeoff clearance. Controller, November 477 Zulu Alpha, runway 4, taxiway Bravo, line up and wait. Pilot, line up and wait, runway 4, taxiway Bravo, November 477 Zulu Alpha. Ensure that when you read back a clearance for an intersection line up and wait, or intersection takeoff, that you state the name of the intersection, even if the controller did not include it in the clearance. Landing clearance. ATC may withhold or rescind a landing clearance when an aircraft is in line up and wait on the runway. Landing clearance withheld. Controller, November 477 Zulu Alpha, runway 4, continue, traffic holding in position. Landing clearance canceled. Controller, November 477 Zulu Alpha, landing clearance canceled, traffic holding in position, continue. Takeoff clearance, landing clearance. Read back all landing and takeoff clearances with a call sign, including the runway designator. Controller, November 123 Quebec Yankee, Charlotte Tower, runway 4 right, cleared to land. Pilot, November 123 Quebec Yankee, cleared to land, runway 4 right. Controller, November 123 Quebec Yankee, Charlotte Tower, runway 5, cleared for takeoff. Pilot, November 123 Quebec Yankee, cleared for takeoff, runway 5. Land and hold short clearance. Land and hold short instructions require your acceptance and readback. Controller. November 123 Quebec Yankee, Waterloo Tower, runway 36, cleared to land, hold short runway 30 for departing traffic. Pilot. November 123 Quebec Yankee, cleared to land runway 36, hold short runway 30. Figure 1-18A and B shows an example of the land and hold short holding position. Runway exiting clearance. After landing and reaching taxi speed, you are expected to exit the runway at the first available taxiway or as instructed by ATC. You should remain on the tower frequency until advised to contact ground control. Controller. Unity 32, turn right on taxiway Golf 2 and contact ground point Niner when clear of the runway. Pilot. Unity 32, right on Golf 2, ground point Niner. Initial contact after landing and clearing the runway. Pilot, Lincoln Ground, November 123 Quebec Yankee, clear of runway 2 at Bravo, taxi to the ramp. Controller, November 123 Quebec Yankee, Lincoln Ground, taxi to the ramp via Bravo. Light gun signals. ATC has a backup system if radio communication fails. Controllers use a light gun that flashes different colors to instruct you what to do. Refer to the Pilot's Handbook of Aeronautical Knowledge, Chapter 13, Airport Operations, for a light gun signal illustration. Even a failed radio transmission is not an excuse for proceeding without a proper clearance. If you are on a runway or taxiway and radio communication with ATC fails, you should 1. Turn toward the tower. 2. Flash your landing lights several times. 3. Wait for the light signal from ATC. 4. Be patient. If ATC's attention is diverted, it may take a few minutes for a response. 5. If your radios are working, try a frequency other than the one you are currently using. 6. Call ATC via cell phone if you have the number available. Signs, markings, and lighting. It is important for you to know the meanings of the signs, markings, and lights that are used on airports as surface navigational aids. All airport markings are painted on the surface, whereas some signs are vertical and some are painted on the surface. An overview of the most common signs and markings are described on the following pages. For more detailed information on runway signs and markings, refer to the AIM. Runway holding position sign. Non-compliance with the runway holding position sign may result in the FAA filing a pilot deviation against you. A runway holding position sign is an airport version of a stop sign. See Figure 1-19. It may be seen as a sign and/or its characters painted on the airport pavement. The sign has white characters outlined in black on a red background. It is always co-located with the surface painted holding position markings and is located where taxiways intersect runways. On taxis that intersect the threshold of the takeoff runway, only the designation of the runway may appear on the sign. If a taxiway intersects a runway somewhere other than at the threshold, the sign has the designation of the intersecting runway. The runway numbers on the sign are arranged to correspond to the relative location of the respective runway thresholds. Figure 1-20 shows 18-36 to indicate the threshold for runway 18 is to the left and the threshold for runway 36 is to the right. The sign also indicates that you are located on taxiway Alpha. If the runway holding position sign is located on a taxiway at the intersection of two runways, the designations for both runways are shown on the sign along with arrows showing the approximate alignment of each runway. See Figures 1-21A and B. In addition to showing the approximate runway alignment, the arrows indicate the direction to the threshold of the runway whose designation is immediately next to each corresponding arrow. This type of taxiway and runway/runway intersection geometry can be very confusing and create navigational challenges. Extreme caution must be exercised when taxiing onto or crossing this type of intersection. Figure 1-21A and B shows a depiction of a taxiway, runway intersection and is also designated as a hotspot on the airport diagram. In the example, taxiway Bravo intersects with two runways, 31-13 and 35-17, which cross each other. Surface-painted runway holding position signs may also be used to aid you in determining the holding position. These markings consist of white characters with a black border on a red background and are painted on the left side of the taxiway centerline. Figure 1-22 shows a surface-painted runway holding position sign that is the holding point for runway 32R-14L. You should never allow any part of your aircraft to cross the runway holding position sign, either a vertical or surface-painted sign, without a clearance from ATC. Doing so poses a hazard to yourself and others. When the tower is closed or you are operating at a non-towered airport, you may taxi past the runway holding position sign only when the runway is clear of aircraft, and there are no aircraft on final approach. You may then proceed with extreme caution. Runway holding position marking. Noncompliance with a runway holding position marking may result in the FAA filing a pilot deviation against you. Runway holding position markings consist of 4 yellow lines, 2 solid and 2 dashed, that are painted on the surface and extend across the width of the taxiway to indicate where the aircraft should stop when approaching a runway. These markings are painted across the entire taxiway pavement, are in alignment, and are co-located with the holding position sign as described above. As you approach the runway, 2 solid yellow lines and 2 dashed lines will be visible. Prior to reaching the solid lines, it is imperative to stop and ensure that no portion of the aircraft intersects the first solid yellow line. Do not cross the double solid lines until a clearance from ATC has been received. See Figure 1-23. When the tower is closed or when operating at a non-towered airport, you may taxi onto or across the runway only when the runway is clear and there are no aircraft on final approach. You should use extreme caution when crossing or taxiing onto the runway and always look both ways. When exiting the runway, the same markings will be seen except the aircraft will be approaching the double dashed lines. See Figure 1-24. In order to be clear of the runway, the entire aircraft must cross both the dashed and solid lines. An ATC clearance is not needed to cross this marking when exiting the runway. Enhanced taxiway centerline markings. At most towered airports, the enhanced taxiway centerline marking is used to warn you of an upcoming runway. It consists of yellow dashed lines on either side of the normal solid taxiway centerline, and the dashes extend up to 150 feet prior to a runway holding position marking. See Figures 1-25A and B. They are used to aid you in maintaining awareness during surface movement to reduce runway incursions. Elevated runway guard lights. Elevated runway guard lights, ERGL, commonly known as wigwag lights, are co-located with the runway hold position signs and surface-painted hold position markings. They consist of a pair of elevated flashing yellow lights installed on either side of the taxiway near the holding position sign. See Figure 1-26A. Alternatively, they may be a row of in-pavement yellow lights installed across the runway at the holding position marking. See Figure 1-26B. Runway guard lights are effective visual aids for helping you identify the runway holding position. Runway Safety Area Boundary Sign. In addition to the runway hold marking, some taxiway stubs also have a runway safety area boundary sign that faces the runway and is visible to you only when exiting the runway. This sign has a yellow background with black markings and is typically used at towered airports where a controller commonly requests you to report clear of a runway. This sign is intended to provide you with another visual cue that is used as a guide to determine when you are clear of the runway safety boundary area. The sign shown in Figure 1-27 is what you would see when exiting the runway at taxiway Kilo and is out of the runway safety area boundary when the entire aircraft passes the sign and the accompanying surface painted marking. End of Section 3 of Appendix 1. Recording by Robert Sherman, Jr., Washington, D.C., www.nyckidd.com. Part 4 of Appendix 1 of Pilot's Handbook. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Robert Sherman, Jr. Pilot's Handbook of Aeronautical Knowledge, Appendix 1, Part 4, Land and Hold Short Operations. Land and Hold Short Operations, LAHSO. When simultaneous operations, takeoffs and landings, are being conducted on intersecting runways, land and hold short operations, LAHSO, may also be in effect. LAHSO is an ATC procedure that may require your participation and compliance. As Pilot in Command, PIC, you have the final authority to accept or decline any LAHSO clearance. If issued a land and hold short clearance, you must be aware of the reduced runway distances and whether or not you can comply before accepting a land and hold short clearance. You do not have to accept a LAHSO clearance. Pilots should only receive a LAHSO clearance when there is a minimum ceiling of 1,000 feet and 3 statute miles of visibility. Runway holding position signs and markings are installed only on those runways used for LAHSO. The signs and markings are placed at the LAHSO point to aid you in determining where to stop and hold the aircraft and are located prior to the runway-runway intersection. See Figure 1-28. The holding position sign has a white inscription with black border around the numbers on a red background and is installed adjacent to the holding position markings. If you accept a land and hold short clearance, you must comply so that no portion of the aircraft extends beyond these hold markings. If receiving cleared to land instructions from ATC, you are authorized to use the entire landing length of the runway and should disregard any LAHSO holding position markings located on the runway. If you receive and accept LAHSO instructions, you must stop short of the intersecting runway prior to the LAHSO signs and markings. Below is a list of items which, if thoroughly understood and complied with, will ensure that LAHSO operations are conducted properly. No landing distance available. Be advised by ATC as to why LAHSO are being conducted. Advise ATC if you cannot comply with LAHSO. Know what signs and markings are at the LAHSO point. LAHSO are not authorized for student pilots who are performing a solo flight. Generally, LAHSO are not authorized with air carrier operations. Generally, LAHSO are not authorized at night. LAHSO are not authorized on wet runways. If you accept the following clearance from ATC, cleared to land runway 36, hold short runway 23-5, you must either exit runway 36 or stop at the holding position prior to runway 23-5. Location signs and markings. Taxiway location signs and markings and runway location signs aid you in identifying the taxiway or runway on which you are currently located. They have a black background with yellow characters. These signs may stand alone or be co-located with direction or runway holding position signs. See Figures 1-29A and B. Runway location signs are intended to complement the information available to you through your aircraft magnetic compass. They are installed in areas where the proximity of 2 or more runways could cause you to be confused. Figure 1-29A and B shows that Taxiway Alpha and Runway 36 are standalone location signs and are not associated with any other sign. Complex airport geometry, a single taxiway leading up to multiple runway thresholds, and/or the close proximity of multiple runway thresholds can lead to confusion and a higher risk of you departing on the wrong runway. At airports where these risk factors are present and the proximity of 2 runway thresholds could cause confusion, runway location signs may be present. Cross-check your aircraft compass heading with the assigned takeoff runway heading prior to brake release. Figure 1-29C shows the thresholds of runway 30 and runway 36, which are co-located. Runway location signs are present on these runways along with the runway designation numbers. Note: runway designation surface painted markings are large white block numbers and are located at the threshold of the runway. Surface painted taxiway location markings are normally located on airports where there has been a history of navigation confusion. See Figure 1-30. These signs and markings are designed to help you navigate difficult or potentially confusing intersections. If ever in doubt about your taxi clearance, ask ATC for help. Taxiway direction signs and marking. Taxiway direction signs have a yellow background and black characters, which identifies the designation or intersecting taxiways. Arrows indicate the direction of turn that would place the aircraft on the designated taxiway. See Figure 1-31. Direction signs are normally located on the left side of the taxiway and prior to the intersection. These signs and markings, with a yellow background and black characters, indicate the direction toward a different taxiway leading off a runway or out of an intersection. Figure 1-31 shows Taxiway Delta and how Taxiway Bravo intersects ahead at 90 degrees both left and right. Taxiway direction signs can also be displayed as surface-painted markings. Figure 1-32 shows taxiway Bravo as proceeding straight ahead while taxiway Alpha turns to the right at approximately 45 degrees. Figure 1-33A and B shows an example of a direction sign at a complex taxiway intersection. Figure 1-33A and B shows taxiway Bravo intersects with taxiway Sierra at 90 degrees, but at 45 degrees with taxiway Foxtrot. This type of array can be displayed with or without the taxiway location sign, which in this case would be taxiway Bravo. Destination signs. Destination signs have black characters on a yellow background indicating a destination at the airport. These signs always have an arrow showing the direction of the taxi route to that destination. See Figure 1-34. When the arrow on the destination sign indicates a turn, the sign is located prior to the intersection. Destinations commonly shown on these types of signs include runways, aprons, terminals, military areas, civil aviation areas, cargo areas, international areas, and fixed base operators. When the inscription for two or more destinations having a common taxi route are placed on a sign, the destinations are separated by a dot, and one arrow would be used as shown in Figure 1-35. When the inscription on a sign contains two or more destinations having different taxi routes, each destination is accompanied by an arrow and separated from the other destinations on the sign with a vertical black message divider as shown in Figure 1-35. The example shown in Figure 1-35 shows two signs. The sign in the foreground explains that runway 20 threshold is to the left, and runways 32, 2, and 14 are to the right. The sign in the background indicates that you are located on taxiway Bravo, and taxiway November will take you to those runways. Holding position signs and markings for an instrument landing system, ILS. The Instrument Landing System, ILS, broadcasts signals to arriving instrument aircraft to guide them to the runway. Each of these ILSs has a critical area that must be kept clear of all obstacles in order to ensure quality of the broadcast signal. At many airports, taxiways extend into the ILS critical area. Most of the time, this is of no concern. However, during times of poor weather, an aircraft on approach may depend on a good signal quality. When necessary, ATC will protect the ILS critical area for arrival instrument traffic by instructing taxiing aircraft to hold short of this critical area. The ILS critical area boundary sign has white characters outlined in black on a red background and is installed adjacent to the ILS holding position markings. See Figure 1-36. The holding position markings for the ILS critical area appear on the pavement as a horizontal ladder and consist of two solid yellow lines spaced 2 feet apart connected by pairs of solid lines spaced 10 feet apart extending across the width of the taxiway. When instructed to hold short of the ILS critical area, you must ensure that no portion of the aircraft extends beyond these markings. If ATC does not instruct you to hold at this point, then you may bypass the ILS critical area hold position markings and continue with your taxi. Figure 1-36 shows that the ILS hold sign is located on taxiway Golf and the ILS ladder hold position marking is adjacent to the hold sign. Runway approach area holding position signs and markings. At some airports, it is necessary to hold an aircraft on a taxiway located in the approach or departure area for a runway so the aircraft does not interfere with operations on that runway. In these situations, a sign with a designation of the approach end of the runway followed by a dash and letters APCH will be located at the holding position on the taxiway. Holding position markings will be located on the taxiway pavement. See Figure 1-37. In this example, the sign may protect the approach to runway 32 and/or the departure for runway 14. If you are expected to hold short of a runway approach APCH area, ATC will issue instructions. Holding position markings for taxiway intersections. Holding position markings for taxiway intersections consist of a single dashed yellow line extending across the width of the taxiway. See Figure 1-38. They are painted on taxiways where ATC normally holds aircraft short of a taxiway intersection. When instructed by ATC, hold short of taxiway X, you should stop so that no part of your aircraft extends beyond the holding position marking. When the marking is not present, you should stop your aircraft at a point that provides adequate clearance from an aircraft on the intersecting taxiway. Marking and lighting of permanently closed runways and taxiways. For runways and taxiways that are permanently closed, the lighting circuits are disconnected. The runway threshold, runway designation, and touchdown markings are obliterated and yellow X's are placed at each end of the runway and at 1,000-foot intervals. Temporarily closed runways and taxiways. For temporarily closed runways and taxiways, a visual indication is often provided with yellow X's or raised lighted yellow X's placed at each end of the runway. Depending on the reason for the closure, duration of closure, airfield configuration, and the existence and the hours of operation of an ATC tower, a visual indication may not be present. As discussed previously in the chapter, you must always check NOTAMs and ATIS for runway and taxiway closure information. Figure 1-39A shows an example of a yellow X laid flat with an adequate number of heavy rubber weights to keep the wind from getting under and displacing the vinyl material. The black rubber weights are positioned along the edge, giving the appearance of a black outline. A very effective and preferable visual aid to depict temporary closure is the lighted X placed on or near the runway designation numbers. See Figure 1-39B and C. This device is much more discernible to approaching aircraft than the other materials described above. Runway edge and centerline lights. The runway edge lights are white except on instrument runways where yellow replaces white on the last 2,000 feet or half the runway length, whichever is less, to form a caution zone for landings. The lights marking the ends of the runway emit red light toward the runway to indicate the end of a runway to a departing aircraft, and emit green outward from the runway end to indicate the threshold to landing aircraft. Centerline lights are located along the runway centerline and are spaced at 50-foot intervals. When viewed from the landing threshold, the runway centerline lights are white until the last 3,000 feet of the runway. The white lights begin to alternate with red for the next 2,000 feet. For the last 1,000 feet of the runway, all centerline lights are red. See Figure 1-40. Taxiway edge lights or reflectors. Taxiway edge lights or reflectors are blue in color and used to outline the edges of taxiways. See Figure 1-41. Runway designation marking. Runway numbers and letters are determined from the approach direction. The runway number is the whole number nearest 1/10 the magnetic azimuth of the centerline of the runway, measured clockwise from the magnetic north. In the case where there are parallel runways, the letters differentiate between left, L, right, R, or center, C. See Figure 1-42. For example, if there are two parallel runways, they would show the designation number and then either L or R beneath it. For three parallel runways, the designation number would be presented with L, C, or R beneath it. End of Part 4 of Appendix 1. Recording by Robert Sherman, Jr., Washington, D.C., www.nyckidd.com. End of Pilot's Handbook of Aeronautical Knowledge, FAA-H-8083-25A, by Federal Aviation Administration.